dopo lo misuriamo così.
Okay. Good morning, friends. My name is Erio Tosatti. Among many privileges that I had in my life, I can mention three. One has been to start the condensed matter group here 48 years ago at the request of Abdus Salam. It's a privilege to be a member of this, I dare say, peerless institution, of which I'm totally proud. The second privilege has been to be asked to chair this incredible morning in this incredible meeting. I've never seen any meeting like this. The third privilege is to have been a member of the same group a long time ago of the first speaker here, Duncan Haldane, when he was a student. I was a postdoc, and we've been friends for life on that occasion. So we're now to his first talk of the morning, quantum Hall effect and quantum geometry.
Thank you. Switch on. Thank you. It's on? Good. Okay, I'm going to give you a rapid tour through this talk because there's too much material as usual. But one of the things which hasn't been mentioned so far is the Berry phase, the Berry curvature, etc., which was a really important development in the last probably 40 years ago now. But it's led to tremendous developments, at least in condensed matter. Okay, so as we know, the laws of quantum mechanics were 100 years old, and nothing's changed about them in the sense that they've all stood the test of time, and they prove correct. But just because we know the laws doesn't mean that we immediately know everything that they allow to happen. So there's been a whole series of surprises about discovering what quantum mechanics actually lets happen. Okay. So around about 1980, condensed matter physicists thought they had a basic understanding of, broken symmetry, conductors, insulators, etc. And of course, when you believe you know most stuff, and diagrammatic perturbation theory was a tool to solve everything. When you think you know everything, you get nature and gives you a surprise because at that time, two apparently disconnected surprises happened. The main one was, of course, the discovery of the quantum Hall effect by Klaus von Klitzing. But also I came across a kind of magnetic state that was different from what people were expecting. And it turns out both of these two things are examples of what we now call topological quantum matter. And in some sense, quantum entanglement is playing a key role in these systems. And of course, many more kinds of topological quantum matter have been discovered in the last, in fact, 2 decades. Okay. So soon after these discoveries, Michael Berry discovered the importance of the Berry phase in adiabatic quantum mechanics. And the Berry phase turned out to be an important ingredient for understanding both of the two strange topological states. And of course, the Berry phase is that the simple original formulation of the Berry phase pointed out by Berry is that if I take a spin and align it with a Zeeman field along some direction, and then I slowly drag the spin by moving the Zeeman field around sufficiently slowly so it stays aligned. And when I get back to where I started from, the state, the state of the phase of the state has changed relative to the phase of a state that was not transported. And you get this nice result that for a spin S object, you pick up a phase which is 2s times the solid angle subtended by the path on the sphere. Now, the solid angle on the sphere is ambiguous up to a multiple of 4 pi, because what is inside the path and what is outside the path is your opinion. But that means that everything is fine provided 2s is exactly quantized to be an integer. And now we would say that for this system, the Chern number is 2s. Okay. So this is this really follows from Dirac's monopole quantization of the magnetic monopole can be put into the framework of this problem. And okay, so it shows an importance in general for whether the spin to take even or integer or half integer values. Okay, so adiabatic quantum mechanics considers a system where I've got a Hamiltonian which depends on some set of classical parameters that control it, and these parameters are probably being manipulated by a classical agent behind the curtain who's dragging X around. So the adiabatic limit is when the state psi of t, it starts off very close to a non-degenerate instantaneous eigenstate of the Hamiltonian at point X and stays that way. So the projection of the state onto the instantaneous eigenstate is always very close to 1. And that can be achieved by doing the adiabatic motion sufficiently slowly. And there's what one might call a Berry gauge ambiguity. So it'll turn out all this Berry stuff is very similar to electromagnetism in 3 dimensions. In fact, electromagnetism can be viewed as a special case of the Berry phase. If I have a pointer with a little potential well, say this cup or something, at the end of it, and I move it around. If it was a teacup, I'd have to move it sufficiently slowly to stop it spilling. Well, if I move the thing sufficiently slowly to leave a particle in that well in its ground state and not shake it out of it, then that's an adiabatic process as I move it around. And it'll turn out that what's here, the Berry connection, is just E over h bar times the magnetic vector potential, assuming there's some electric and magnetic fields in the background. And the energy level will go up and down because you'll have to add to it the scalar electromagnetic potential times the charge at each point. So it actually picks up an exact. So the simplest example of Berry is actually just a particle in a well that you're moving around. So not a particle zooming around on its own, an unbound particle, but a bound particle bound in a well at a position that you're controlling. Okay, so the phase of the wave function, of course, has an arbitrary choice. So we have this U1 ambiguity, and the Berry connection is just the gradient, the overlap of the wave function with the gradient, with its own gradient, etc. And we can, because that depends on the gauge, we can pull out what's called a gauge covariant derivative, which is down here, by basically subtracting off the part of the wave function that's unchanged, and we get to a simple formula from second order perturbation theory for the change in the wave function. And this has been a very profound object. So I take this covariant derivative, and basically by construction it transforms under gauge transformations the same way as a state. So overlaps are on a gauge invariant, and the Berry connection then enters in the Berry phase exactly. In fact, the Bohm-Majorana phase is just a special example of this formula in a three-dimensional background, okay? But of course, this works in an arbitrary n-dimensional background, and the coordinates don't have to be positions. They could be anything else. They could be shapes or whatever. And out of this thing, then, we also get the Berry curvature, which is just the analog of the Faraday tensor. And in fact, we also get something called the quantum geometric tensor, where there's a metric. So the geometry, the natural geometry of quantum mechanics, this is the Burroughs metric, or the pure state version of the Burroughs metric, is basically just given by a distance measure, a dimensionless distance between 0 and 1, and orthogonal states, a distance 1 apart, and states which are equal to each other up to a phase, which is arbitrary, have distance 0. And interestingly, the formulas for the Lorentz force is if I'm moving this object around by dragging the pointer around, of course, if I'm moving it up and down the electromagnetic scalar potential, I'll be doing work on it, so I'll feel the force backwards, but I'll also feel a sideways force depending on the speed. So there's a complete 100% correspondence with the Lorentz force in space, because the Lorentz force is just a special example of the quantum Lorentz force, at least in this context. So this has kind of been very useful for many things, okay. So the Berry connection for a spin S object provides an action. The Berry connection is just enters in the action, which is linear in time derivatives. And this is something new because okay, so there's the Hamiltonian, but the parts linear in the time derivatives vanish when I convert to a Hamiltonian formulation. And the crucial thing here is that this number S, 2S, must be an integer. So when I started in my career and as a student, no one in condensed matter had ever heard of actions, or we had in our mechanics classes, but it didn't have any role in what we were thinking about, because everyone was using Hamiltonian formulations where these topological terms, which were proportional to the linear in time derivatives, are completely gone, right? And the role of the spin was at that time really thought to be as like Planck's constant. The s to the minus 1 was thought of as sort of as a continuous number that when it was small or s was very big was a kind of classical limit, and quantumness goes like 1 over s continuously. And at that time it was known from Bether's exact solution that he kind of stumbled upon in 1931 with an ansatz that turned out to be correct and exact. It was known that the spin half Heisenberg antiferromagnetic chain in one dimension, sorry, I didn't put that in there, was gapless, and therefore it was believed that it was just, everything was just continuous, that just larger spin was a bit less quantum, the fluctuations were less or something. And in fact, Phil Anderson, my boss, even believed that, and he wrote it somewhere in a paper that there was the only difference between spin a half and spin wave theory for large spin was a factor of pi in the spin wave velocity. It turns out beta solution was very complicated, and the people who understood physics didn't understand beta solution, and more or less the people who understood beta solution didn't understand physics. It was kind of math versus. So the physicists kind of were told something is exact, and they uncritically say, well, that's that. But in fact, exact results are often they're usually true, but they're often misleading. The Kosterlitz-Thouless, for example, was against the theorem that you can't have long range order in 2 dimensions with a continuous parameter. Okay. So in 1981, I discovered that a spin-1 magnetic chain could have a novel state, which turns out to have at least local entanglement, that's now understood as the simplest of the topological states. Previously, people thought of magnetic order, you just line the spins up in different directions, but you stack them together. You can assemble it by assembling magnetic atoms and putting them place to place, but with no change really. But it turns out that, of course, when things change, you start to get some rearrangement of the electronic state. And the interesting thing here was that the spin-1 chain, the spin-1s split up, leaving half of a spin-1 or a spin-half at one end of the chain and the other at the other half, which is now typical of topological states. I guess that was pretty shocking and provoked a lot of controversy to people in the community. But of course, science has to be put to the test, and eventually material scientists come to the rescue and actually make stuff, and that's what's happening now. Material scientists are able to make toy models. Toy models were usually approximations to stuff in nature. Now the material scientists can actually build the toy models to fit the theory in some certain way. Okay, so topological matter differs from ordinary matter because there's some properties typically connected with entanglement in some way that can be described by whole numbers, and states of matter characterized by different whole numbers can't change continuously from one to the other, so there has to be something discontinuous and interesting happening at the boundary between the two regions, which are where there's matter in 2 different topological states. So in this particular, the spin chain, I'll come back to this picture if I get around to discussing Majorana zero modes and Majorana 1, the chip, which we're going to hear more about, I suppose. But basically, you would say that hands always come in pairs unless you've been unfortunately deprived of one by an accident. So, but you can actually separate the pair by having a chain of people where they all hold hands, and there's one leftover hand on each end of the chain. Okay, so of course the quantum Hall fluids are perhaps the clearest example of the topological states, and they're originally found in large magnetic fields, but now we've actually discovered both integer and fractional quantum Hall effect in the absence of magnetic fields. They just require time reversal breaking, which you can get with ferromagnetism as opposed to fields. And of course, we heard about that yesterday, and there's the Kibble balance, and this is the death of the Emperor Napoleon's French imperialism, because you don't have to go to Paris and knock on the door to check your weight against the platinum cylinder if a market trader swindled you. Okay, so it took a long time. It took quite a bit of time for the topological nature of the quantum Hall effect to become clear, but it should have been immediately obvious. Okay, and here's a picture that you see all the time, and I'm going to come back to this picture again and again. You have the electrons bound on a 2-dimensional surface with some magnetic flux through it, and the electrons are going around in quantized Landau orbits in the bulk, but if they're close to the edge, they hit the edge and they skip around it. And the key thing here, we've got one-way edge states. And here's the picture. Before, we used to think you need impurities or dirt to give a quantum Hall effect, but in principle, although the plateaus are kind of small, in principle, depending on the bulk to boundary ratio, if I have a clean system, the Landau level energies will be deformed. They'll go up at the bulk because you don't make complete rotations anymore at the edge. And if the Fermi level is pinned at the edge, you will have a bulk gap and you will get a quantum Hall effect and edge states. And in fact, the remarkable thing, von Klitzing, like all these discoveries, my discoveries and others' discoveries, they were all serendipity, good accidents, right? Because no one's expecting an unexpected discovery when you make it. You just have to be able to recognize it. And of course, von Klitzing recognized it because he put his sample, he put a sample at constant, with a constant current generator on it into the magnetic field and switched on the magnetic field. You never get to exactly the same magnetic field, but as long as you get somewhere, so the field is such that you get the Fermi level somewhere in the gap, you will get the numbers out. And von Klitzing noticed that the digital numbers were correct, were always the same to about four places of decimals or something. And presumably after first wondering, is my voltmeter completely screwed up? You know, he actually realized he had a completely unexpected thing. The same experiment had been done, I think, in Japan some years earlier, but they put it into the constant magnetic field and then ramped up the current. You'll never get the same digits. You'll never get the same voltage because the current will never be the same, and so they never noticed this thing. So again. So what does that picture show? The topological directional edge states are actually the key property of quantum Hall states. They're the most remarkable property. And their one-way character derives from the broken time reversal symmetry. And this is actually why you actually don't need a magnetic field. You just need the time reversal breaking from ferromagnetism, for example. And if I now think about the edge states, I've got the periodic boundary conditions around the edge, because it goes round and round. But as I change the magnetic flux through the bulk, the boundary conditions change, and then states either, if you're increasing the magnetic field strength, states flow down from above the Fermi energy into the bulk. And it's not so much that charge is flowing in. The charge comes in each time a state goes through the chemical potential and picks up charge from the reservoir. But what this is showing is the central feature, well, to my mind, the central feature of the quantum Hall state, both in Landau levels and in band insulators with a Chern invariant. The orbitals are free to move. This is something we don't experience in band insulators. In band insulators, the local basis of orbitals, the Wannier-type orbitals, are kind of glued down at specific places inside the unit cell, and they're just glued in. The electrons hop between the local Wannier orbitals, sure, and in a band they don't move because there's no place to hop without jumping out. But the orbitals in both Landau levels and in Chern insulators where the Wannier construction fails are mobile, provided in the Chern band it's flat. Okay, so the spectral flow. So the most remarkable property then of the straight anomaly is a direct consequence of this is it's not so much that the current has a precise the whole voltage and the current have this precise relation. The current, of course, contains dissipative aspects from hopping between impurities and whatever. Conductivity has got both symmetric and anti-symmetric components to it. But the Strader relation is a relation between the charge density and the flux through the surface. So it's preferable to use, I find it preferable to use the Faraday tensor rather than magnetic field because there's no arbitrary right-hand rules there. I mean, we teach all that stuff. It makes right-hand rules make it easy to add fields, magnetic fields from different sources together as vectors. But fundamentally, the magnetic field is an anti-symmetric tensor, and I always make a point of putting indices in the correct places, even though people are not trained to do that in condensed matter. And so the Strader relation is saying you hold the potential fixed, and in this case in a gap at zero temperature. The rate of change of the charge density with the flux density is this. And this is purely anti-symmetric with no dissipative aspect to it at all. So it's a fundamental topological thing, okay? And Okay, so it's actually, the charge is only changing because the orbital density is changing, and the orbitals get filled as they enter the system from the side. So condensed matter really has three subsystems, and here we're talking about the case where the electronic degrees of freedom have no gapless excitations. So after that, there are only two low-energy sets of degrees of freedom in the system. The lattice, which are the degrees of freedom, the fluctuations of the phonons, which are the fluctuations of the local Bragg vector fields, of which define the crystal locally, and the electromagnetic degrees of freedom. So in a usual incompressible state, where there's nothing in the middle, there's no low energy, the electrons are completely owned by the lattice. And the density of electrons is just fixed by the local volume of the Brillouin zone, so it can only fluctuate when they're longitudinal phonons. But in the quantum Hall, some of the electrons have been captured by the electromagnetic field and stolen away, and now they're controlled by the electromagnetic field. Let's see if the next, okay, okay. Yeah. So how do they get captured? They get captured by Landau quantization, and Landau quantization suppresses umklapp processes. So the electrons which have been Landau quantized have lost all knowledge of the local Bragg vector fields and have become detached from the lattice. Okay, so the quantum Hall fluid is actually quite interesting. It's a true incompressible fluid. I mean, you may mathematically work with the Euler fluid, which is a classical approximation to an incompressible fluid, but the Euler fluid is like Newtonian gravity. Pressure is instantaneously ill-equilibrated through the system by an infinite speed of sound, and so it's a fake incompressible fluid. Of course, it's great for diamond anvils and the like. The quantum Hall fluid you cannot make a diamond anvil out of because it does not support pressure. As an incompressible system, it's got a traceless stress tensor and no sound waves. So no force can be transmitted through the bulk. It can only be transmitted around the edge when you try to squeeze it. And interestingly, a maximum density droplet of quantum Hall state, a liquid, I can put it down on a surface, on a flat potential, it will not expand because there's no internal pressure. And then you can ask, what happens when you try to squeeze it? Well, usually if you squeeze the fluid, the pressure will go up and that will resist it. Here you squeeze it. The squeezing actually generates the edge current. And it's the Lorentz force on the edge current which pushes outwards, which pushes back against the confining potential without a pressure to do it. Okay. And a more careful analysis which shows that there's two actually interesting aspects to this. One is the polarization of the Landau orbit by the electric field, the gradient of the potential. That's a Landau level mixing effect. And there's another effect which is the whole viscosity response, which is a response to the gradient of the electric field, which is pretty interesting. And if you actually can project completely into a Landau level, there's no Landau level mixing. It's the only response. Okay. I guess I haven't much time, so anyway, so you squeeze it and you actually have a gradient of velocity coming from the curvature of the potential, and the whole viscosity produces stress at right angles to the flow, which is dissipationless. Okay, let me just move on. So the integer Hall effect was soon followed by a bigger puzzle, the Laughlin state. And I've got three ways to write quantization. I can use it. The usual way is just P over Q, E squared over H. But there's an integer involved, so you can. This is what Dan Sui wrote it as K times a fractional. E over Q turns out to be the fractional charge of the elementary excitation times an integer. But I can also write it as the charge of the elementary unit of the fluid, because this fluid has something like a unit cell. It's got a fundamental unit, and then there's a PQ is the product of those two numbers is the Chern index. We'll come to that. But P and Q don't necessarily have to be co-prime. In fact, for the interesting case, for the Majoranas, etc., is P is 2 and Q is 4. Okay, so the foundation of our understanding of this wave function, it apparently was initially proposed as a kind of variational wave function that was discovered through looking at three-body a three-body numerical calculation. And in fact, usually people look at that, there's nothing to, but in fact, Z is a complex structure, and its relation is just a Z star Z is a quadratic form in the plane, so Z is not necessarily X plus IY. And it turns out there's a fundamental geometric aspect of degree of freedom in the Laughlin state, which is actually its quadrupole degree of freedom. We'll come to that. So this was actually quickly shown to be work, and in fact, there's an exact model for which this is the exact ground state, and you can adiabatically change that in numerical diagonalization to a Coulomb interaction model. You see the gap stay. So, on the other hand, there's never been a proper explanation of why this works. It came out, Laughlin discovered it accidentally, again, because he was looking for something completely different when he did his calculation. And it works, but it's actually been a huge shock to theory, because up till that point, people believed that all fancy theory could be done using diagrammatic perturbation theory, and the Russian school was the kind of biggest in that. But it turns out you have absolutely zero, you can do absolutely zero with perturbation theory because there's no kind of Wick theorem in its correlations and there's no basis. So this has been, there's been no way to do pen and paper type of calculations of honest ones with the Laughlin wave function or quantum Hall state. So it's still a thing. So I believe it's actually not fully explained why it works. We know it works, and I've got my ideas now. So Laughlin state has been the source of all kinds of, people look at the Laughlin wave function and pick up all kinds of inspiration from it and put it into different words. The popular one is one called flux attachment. Initially, the idea was magnetic field lines were somehow bunched up and traveling with the particles. That's clearly nonsense. So it gets transported that vortices are maybe bound to the particles. But now with the fact we see the fractional Hall effect is found in systems with no magnetic fields at all, we actually, really, the idea of flux attachment doesn't hold water either. And so actually I have a proposal to really, maybe it's a linguistic change, but to call this orbital attachment, and I'll explain why. So what's happened, the fractional Hall effect, the integer Hall effect was found in no magnetic field by this toy model that I stumbled over again somewhat accidentally, and it's been very useful for it's the foundation of topological insulators, for example. And if you put a magnetic field on, here's a Hofstadter type picture of it. You see that zero magnetic field, there's this big gap, and if you stay in that gap, if you go down to -1 flux quantum per unit cell, you've completely emptied the band, and when you go up to +1, you've filled it. So everywhere in there, you have a quantum Hall effect. And now we've seen this physically observed in systems based on Moiré twisted bilayers and stuff. Okay, so we now pose the question, the fractional Hall effect in Landau levels, people came up with all kinds of ideas based on the holomorphic structure of the Laughlin state, etc. But there's no such holomorphic structures in the toy model, which I just showed you. And so this gives us a new opportunity to reassess our understanding of the fractional Hall effect and throw out irrelevant details connected to Landau levels, which are not part of the underlying explanation. Okay, let's move on. So since I'm about to run out of time. So in the Landau level structure, as I pointed out, there's actually a hidden metric which describes a quadratic form, and that quadratic form around any point, defines an orthonormal basis of what would be angular momentum states if it was rotationally invariant. And this kind of onion rings, and the area between each onion ring contains one flux quantum. If I look at the Laughlin state, from this viewpoint, we see that if there's an electron occupying the central orbital of that onion ring, there's exactly zero the next two orbitals are exactly empty, 100% empty. And we can then say that actually what's happening here in this non-slated determinate state, instead of each electron occupying one orbital, each electron is occupying 3 orbitals. Or more precisely, because there's a flat band where there's no energy to tell the orbitals where to sit, we can say that 3 orbitals are attached to the electron. So instead of saying the electron is occupying the central orbital, we can say the central is one of 3 orbitals attached to the electron. And this language change can be used for both the fractional, for the FCI, the case with no magnetic field, and the Landau level. So it gets rid of Landau level baggage, as in the ideas of flux attachment. Okay. So as I said, the key difference is that the Landau orbitals in a Landau level can be moved, and this leads to the composite boson picture, which is an alternative way of thinking about quantum Hall effect. Rather than filling Slater determinant in the integer Hall effect, let's think about a hole, a single empty state in a localized state in the filled Landau level. If I drag that around, which is with a coordinate w, all the other states in the Slater determinant, you could use whatever basis you want for the Slater determinant, but all the states in it have to be orthogonal to the empty orbital. So you're doing a drastic rearrangement of the Slater determinant state as you move that orbital around and pick up a Berry phase. And indeed, that Berry phase is equal to, in magnitude, but opposite in sign to what an electron would pick up, a Bohm-Aharonov phase. But this mobile orbital is a new dynamical degree of freedom of the system. It's completely, unlike the electron, it's completely confined to the two-dimensional plane. And it picks up a gauge field, which we now call the Chern-Simons gauge field, describes the Berry phase that the orbital picks up as it moves around. And 2 of these orbitals are fermions. If you exchange 2, you get a -1. So if I put a particle inside it, an electron, the object, which is an orbital filled with an electron or attached to an electron, is actually a boson. We see that because now the Slater determinant to exchange 2 filled orbitals, which is something you'd never even dream of doing in a band insulator picture, you're exchanging 1 row and 1 column of the Slater determinant, so it's clearly a boson. Okay. And we can say this is condensed. Now it's gapped, because there's this gauge field around, and Elliot's theorem tells you that when you have a local gauge field, you actually do not break any symmetries when you condense. Okay, and this generalizes in a very straightforward way to the fractional case. Instead of having 1 orbital, you have q orbitals, and if there's a background with p over q of this thing, you will get a thing, and if you put you'll get a phase factor of -1 to the p times q when I exchange these things. And then, yeah, okay. This is actually the case. This p times q number is actually the Chern-Simons index of the problem. It's 1 for the filled Landau level, where p is 1 and q is 1. But it's a general thing. So it's always an integer. And if it's odd, then I have to put in an odd number of electrons into it to make a boson, which can condense. And if it's even, I have to put an even number of electrons into it. So a Laughlin state, so the typical state would be you have p orbitals, p electrons put into this group of q orbitals to which they're attached. And we get, this is the basic elementary unit, the analog of the unit cell for the quantum Hall fluid. And you have this selection rule. This used to be called the odd denominator rule because people thought p and q had to be relatively prime. But the interesting case is the Majorana case is p equals 2, q equals 4 at the thing. So we can think of these droplets as, you've excluded the other particles from that region. So the droplet, the little void provides a region to bind the electrons, and we have some picture like this. And we can make sense of this that by the 2/5 state, the Laughlin state is the first of a sequence. There's another picture, which is composite fermions. From this viewpoint, the composite bosons are the unit cells of the quantum Hall fluid, and the composite fermions are the charge carriers. If I start to dope my 1/3 state, let's see if I got a picture here. If I add charge to it, I initially add an extra particle to one of these 1 in 3 droplets, which creates, it's no longer a condensed boson, it's different, but it can combine with 3 uncharged units nearby, 4 of them, and split up into 3 charge 1/3 local systems with local charge excess of 1/3, which are droplets of the 2/5. And in the other way around, the next state up in the 2/5, if I remove 1, it splits up into 5 droplets of 1/3, which carry e by fifth. So we have a picture here. But if I have one particle in two orbitals, this satisfies fermionic. This is a fermion by the rules I showed, and we can think of the, if I go back to, that one. So I can think of the process, if I have a dilute set of these, I've doped my Laughlin state as like in doping a semiconductor. I've got a few unit cells with extra charge. Of course, the unit cells in a semiconductor don't move around. The electrons hop between the unit cells. Here, what hops is one electron plus two orbitals, a composite fermion hops between the neighboring, hops from the 2/5 droplet to a neighboring 1/3. And so the charge transport process, when you dope these things, is given by composite fermions. So there's a kind of unity between the two different pictures. You can also think of going up the sequence of 1/3, 2/5, 3/7 by adding extra 2-in-1, 1-in-2 composite fermions, which is the Jane picture of pseudo-Landau levels. Okay. So let's just get around. The last bit I just want to mention is that of course, two composite fermions, if I actually look at them, let's go back again. At one half filling, there are actually two kinds of composite fermions. And they differ fundamentally. I didn't really get to talk about the primitive quadrupole moment, which is the second moment of the charge distribution of a charged object. But the two types, you can either put an electron in the center, or you can put a filled droplet with a hole in the center. These have opposite sign of their quadrupole moments. So they're two different kinds of composite fermions. And there's an interesting composite fermion fluid at the center at 1/2. But if they pair, you can get two of these things can pair into 2-in-4, which now satisfies the bosonic relations and can condense. And this is the one with the Majoranas. Okay. So let me quickly talk about Majorana 1 from this viewpoint. If I take this 1/2 state, which is made of a composite boson, is actually four orbitals containing a pair of electrons. So they're slightly different from just putting it the 2/5 state. There are two kind of elementary abelian defects which carry charge -1/2 or charge +1/2 for that matter. And those are kind of where I just locally add an orbital and leave it empty, or I add 3 orbitals and put one particle in it. So there are two states with -1/2 which have different fermion parity. And the thing is, I can pull these apart, it turns out, because the elementary excitation is 1/4, because it's is P. And I pull them apart, and I leave an entanglement string between the two. And I can no longer tell whether I pull them, whether they had even parity or odd fermion parity before I pull them apart. And this is where the quantum information is stored in the fermion parity. And if there's 2n Majorana modes of the Majorana 0 modes, there's a 2 to the n degeneracy, 2 for the fixes the fermion parity, and this is the origin of the qubit in Majorana 1. And now I'm out of time, but there we go. There's a picture of two states of such a qubit. You can see that there are four of these objects, and here's a particular choice of basis. They're up and down, but you can see that there's little fringes which are interference fringes which are different. They are exponentially small as I pull these things apart, and they become invisible and hide the quantum information which is stored in the interference. And I guess I'm done because I see I'm about to be evicted. Okay. I'll just say that the system of pulling apart what the Majorana thing does is much more remarkable than pulling a spin 1/2 apart into spin 1 into 2 spin halves. It's actually pulled a fermion orbital apart into 2 half fermion orbitals, which are spatially separated. That's the key of them. The Majorana 0 modes are half of an orbital, and so they're necessarily connected by entanglement. I'm going to hear about that from Matthias Treuer later, I think. Thank you.
Thank you very much. Questions? Comments?
Could you go back to the point where you mentioned that there's no umklapp scattering? And could you explain that a bit more?
Yeah, well, once you, umklapp scattering is severely suppressed. The Hofstadter, so once you're going around in a Landau orbit around the point in K-space, there's an open orbit will allow you umklapp scattering. Closed orbit, you get back, the total K doesn't change. Now, the only way you get umklapp is through by tunneling either between different Landau orbits, by tunneling between images of the same Landau orbit in copies of the Brillouin zone. And indeed, the self-similarity, all the very intricate structure of Hofstadter at low magnetic flux density is coming from the tunneling, but it's totally irrelevant because this is incredibly tiny, and while Hofstadter was mathematically beautiful, et cetera, any impurity or any little amount of interaction will destroy the very, very delicate interference that gives rise to this deep structure. So, as I say, a Slater determinant, if I fill the Landau level up, a Slater determinant doesn't actually care about what basis you use to fill it. So just as you fill this bunch of levels of Hofstadter, which corresponds to one Landau level, it doesn't, the many-body wave function doesn't know about all the kind of intricate bands which change with the rational value of the flux, etc. So umklapp is essentially suppressed, and that's why we treat Landau levels as flat, because we can treat them, the umklapp, as the band structure is still there, but it's kind of hidden. Okay, yeah. But basically it means you've lost connection with the lattice. There's no umklapp, you don't know about the lattice anymore. Yeah.
I missed whether you can write a Lagrangian for the Landau coupling.
I didn't show it. I mean,
I imagine that you don't show, but you can write a Lagrangian.
I would write the simplest Lagrangian is the Chern-Simons Lagrangian. I took it out because of time. I've got it somewhere, but I deleted it from this set of slides. Yeah, and again, it's the basic term is linear in the time derivative, so it's a topological. Okay, what I outlined here is the beginning of a theory. It actually contains only the charge. So the topological order of quantum Hall states can be written as there's this Chern-Simons, abelian Chern-Simons index p times q, which is 8 for the Moore-Read, a U1 level p times q, abelian Chern-Simons theorem times other stuff. The other stuff gives you the details of not just the charges, but the Moore structure of the topological defects, and it gets exposed at the edge where you where the thing terminates. It gets exposed to the Virasoro. There's always a Virasoro algebra at the edge, which is very interesting, and to do with its momentum flow along the edge has a Virasoro anomaly in it, yeah, so that stuff gets exposed there. The dominant bulk one, in the absence of the defects, just involves this U1 level K. Yeah.
Have a last lowbrow question. You mentioned that there's really a variational parameter in the form of Z.
Yeah.
And Z, so x plus iy is an arbitrary simple
yeah.
choice. Is there any realization of calculations with the Z in a different form?
Yeah, if the actual interaction in a projected, you can do calculations, projected Landau level calculations. So if the effective mass or the dispersion relation of the single particle structure that gives you the Landau levels doesn't match for example, the dielectric tensor involved in the Coulomb interaction, then you actually don't know. If you do everything on a surface with a 3 or 4-fold rotational symmetry, the kind of point symmetry fixes that. And so people always thought they were doing that, and so that's all. The experiments were all done on things with 3-fold symmetry on the surface of gallium arsenide, right? So it was very natural just to put Z equals x plus iy, but it took some time to realize that was an arbitrary choice.
Thank you very much. Next speaker is Sachdev, Harvard University.
This is mine too, I think.
Subir also has a long involvement with ICTP. Very glad to have him here. And the talk will be on critical quantum swing liquids, SYK models, and the qubit high temperature superconductors.
Okay. Hello. Okay, well, thank you very much, Ario. As he mentioned, I indeed have been coming to ICTP for many years. In the old days, in addition to Ario, Professor Yu Lu used to be here. And in fact, I first spoke about some of the things I mentioned in the beginning part of my talk here at ICTP. So it's really been a wonderful place for me to meet people and also for the physics that I've done over the years. All right, so I've changed the title slightly. I'm going to focus on not quantum matter in general, but on the qubit high temperature superconductors. So here's the famous example of the qubit high temperature superconductor, yttrium barium copper oxide. It's a complicated crystal structure discovered in 86, 87, and it's still really the best high temperature superconductor. There's nothing else close to the same critical temperature at ambient pressure, and it is the material that's being used in practical applications. So over 30 years have passed since the discovery, and so you might wonder, why is it that we don't have a complete understanding of the phenomena? I think we are pretty close to such an understanding, and I'll try to give you an update on where we are and really show you that this discovery led to a revolution in physics. As Duncan also mentioned in the context of the quantum Hall effect, before 1986, we were talking about essentially independent electrons, perhaps with pairing as in the BZS theory. But post-1986, really a whole new set of ideas have entered physics, all having to do with electron entanglement, and I'll talk about those in the context of superconductivity. Okay, so if you take this material and dip it in liquid nitrogen, well, it's a very good superconductor. It can float over magnets. And this is the kind of experiment today you can't do with any other material. This was the first time that you could have a superconductor in liquid nitrogen temperatures. And since this is a conference on technology, let me mention that these superconductors are recently being used in many companies for fusion energy. It's at least yttrium barium copper oxide is the material in this object that's confining a plasma, in which hopefully there will eventually be production of fusion energy. All right, so let's go back to the crystal structure. It's extremely complicated. Is my mic working? But fortunately, it turns out all of the interesting physics happens in a single layer of copper atoms. So these copper atoms are over here, and there's a square lattice of these copper atoms. And what you're doing as you're varying x is changing the density of electrons on the copper atoms. So there's a limit, the so-called insulating limit, when you have exactly one electron on a certain copper orbital. And it's this limit that was highlighted by Anderson in a very prescient paper in 1987. He said the relevant physics of yttrium barium copper oxide and related materials is the formation of what he called a resonating valence bond state. Now, that was at that time a proposal of a very simple variational wave function, but not much was understood about the structure and properties of such states. Today, we would call such a state as a quantum spin liquid in the energy gap. And again, there was no such theory of quantum spin liquids in that time. So what's happened since 1987 is that we now understand at least certain types of quantum spin liquids extremely well. And this has had an impact not only on the theory of superconductivity, but also in many other fields of physics. So I'm going to give you an update on some of those developments and also talk about some recent work where we think we are finally learning some clues on the nature of the quantum entanglement in the cuprates. Okay, so what we certainly have today, so you can put a check mark on this, is a theory of gapped quantum spin liquids in 2 dimensions. The simplest and closest to the Anderson RVB state is what's now called the Z2 spin liquid. It's a spin liquid that preserves time reversal symmetry, unlike the states that Duncan just talked about. And in fact, there are many other such spin liquids. There's a whole library of them, and they're classified by what mathematicians would call unitary modular tensor categories. And in fact, the Z2 spin liquid is closely connected to the toric code that Misha talked about yesterday, which is the key to current implementations of quantum error correction. But it appeared first in this work stimulated by Anderson's RVB proposal. Okay, so since we have a complete theory of spin liquids, well, why can't we just now solve the high TC problem? Well, it turns out, and if this is the type of spin liquid that was relevant, we would have, I believe, a long time ago. But the kind of states that are present in the cuprates are much more complicated. And in particular, I will argue that there are spin liquids, but they're gapless, and they're critical, and they have strong interactions between these essentially zero energy excitations, which are so strong that you even lose the concept of any particles. So in the Laughlin state that Duncan just talked about, they're fractionally charged quasi-particles. So they're complicated, they're due to entanglement, but you can separate them and really talk about them as objects that you could manipulate. But here, the interactions between whatever quasi-particles or fractional charges they may be are so strong that even the idea of quasi-particles break down. And only in the last, I would say, 5-10 years that we've finally started to understand different types of such critical spin liquids. The most progress has been made in things that are called conformal field theories. And here there are lots of connections and interplay from quantum field theory and string theory even, which also have interest in similar conformal field theories, as I will show you. Okay, now, so this is progress, which is still relatively recent on insulators. But now, to understand a superconductor, you have to change the charge density and have mobile charge carriers. And that also there's been a huge amount of work on. And I'm going to highlight a relatively recent observation of something called the Yamaji effect, which is in fact consistent with the particular state that I will describe, called FL star, or fractionalized Fermi liquid, that we had proposed many years ago. But still, working with this doped spin liquid is a very difficult task. And what we have found recently, a method that allows us to make quite a bit of progress, and this is the method of ancilla qubits. And it was really inspired by ideas that were floating around in the literature in quantum computing and quantum information processing. So I'll show you some of this. And then finally, if I have time, there's another very famous phase of the cuprate superconductors called the strange metal. And this will, in fact, I will argue, be related to some kind of crossover of quantum criticality between the FL star and the conventional Fermi liquid in the presence of spatial disorder. And this is where insights from the SYK model have proved crucial in our computations. Now, the SYK model, originally the SY model, was something proposed by Jin Bouillet and myself in the context very much of the cuprate puzzle. But since then, it's really had, I believe, a very significant impact on the quantum theory of black holes, and in particular, it led to a transformation of our understanding of the entropy of non-supersymmetric black holes. But I won't have time to talk about that here. Okay, so let me begin very simply with Anderson's original ideas, on quantum spin liquids with an energy gap. So Anderson and Fazekas originally considered the triangular lattice, which is in fact even today the best candidates for such spin liquids may be present, and on the related Kagome lattice. So let's take an antiferromagnet. These are spinor halves on each side of the triangular lattice with some near neighbor interactions. Now, if you treat these as classical vectors, this is the ground state. The spins form this 120-degree structure with long-range magnetic order. And this can be very well understood in some kind of semi-classical expansion. But in 1974, Anderson postulated a new type of state, which is he called the resonating valence bond state, based upon some earlier ideas of Pauling, where he said, well, if I take a pair of spins, they like to form a spin singlet. Well, so let's imagine that each spin finds a partner and forms a spin liquid with a partner. But as you can see, there's many different ways of forming such partners. So I call each such pairing of spin singlets as a dimer covering. And there's many different ways of forming dimer coverings. And the statement now is that the ground state is a superposition of all of these coverings. So here's how you should think about the ground state. It's some kind of complicated superposition of many macroscopically distinct states. So this is really the first proposal of what we'd call roughly long-range entanglement, because you have really the number of such terms in this expansion is e to the 10 to the 23. That's roughly how many dimer coverings you have in a macroscopic sample. And somehow the idea that there's some kind of coherence where these can entangle in this very complicated way. All right, so those are just words. Now we can do much more than words. We can actually describe the physical properties of such states. And how is it that this entanglement can be observed, and what are the experimental consequences of it? And there's many different things that have been talked about, but I think the heart of it is the following property, which we can call fractionalization, that these systems have particle-like excitations, but these excitations cannot be created by local operators. So in fact, there's different sectors of Hilbert space, and to go from one sector of the Hilbert space to another sector, even in an infinite sample, requires a long-range extensive. To go from any sector to any other sector requires a non-local operators. And these are sometimes called super selection or anyon sectors. So let me just show you a simple example. So if I act locally on any such component of the wave function, I can imagine breaking a singlet and making a triplet. Now that is not an elementary excitation. What will happen is that this will split into two, and the other half has gone off to infinity, and we're left with what we call a spin-on. So this is an object that carries spinor half and zero charge, and no such object had ever been found or talked about in anything in solid-state physics earlier. So this is an emergent fractionalized particle, the spin-on, and that's the essence of the structure of this, and that's a direct consequence of the long-range entanglement. So in 1990, working with Nick Reed, we thought carefully about the nature of this phase transition that I've already mentioned. Imagine going from a classically ordered state to some kind of RBB state. And we pointed out that the way to describe such a state is actually in terms of an emergent gauge field. There's an emergent gauge field, which is dynamical. And this transition is really sort of a confinement transition associated with that emergent gauge field. In this case, it's not a U1 gauge field like electromagnetism. It's just a Z2 gauge field. There's only two possible values rather than a whole phase that emerges in electromagnetism. In fact, this kind of gauge field had been considered earlier by Franz Wegener, but here it emerges naturally from the structure of the spin system. So these spin-ons in this particular theory are bosons, and they carry electric Z2 gate charges. But there's also magnetic charges, sort of vortices, which carry magnetic Z2 gate charges. And all of these objects then form the super selection sector you can also get a fermionic spin-on sector by fusing the two of these. And all of this structure was later put on a much firmer footing by Kitaev's solvable toric code model, which has exactly the same structure. And these ideas, of course, as we heard yesterday from Misha, are the key to modern implementation of quantum error correction. All right, but that's for the triangular lattice, or maybe the Kagome lattice. What about the square lattice? Well, it turns out, fortunately, unfortunately, the square lattice is a lot more complicated, and the relevant spin-liquid states are much more subtle. In fact, they don't have any particle excitations at all. But if you follow the same route that we followed for the triangular lattice, the way you do this in practice is you do a parton construction. You write your spin operator in terms of, say, bosonic partons, which are the spin-ons, which carry spin 1/2. And in this parton construction, in this case, you naturally get a U1 gauge theory. So if you look at the low energy limit of a square lattice antiferromagnet, you find, quite remarkably, a relativistic field theory, which is the U1 gauge field AMU coupled to some relativistic boson Z alpha, which are just connected to the spin-ons and the anti-spin-ons from this decomposition. But there are also certain effects that closely related to what Duncan was just talking about, which are these Berry phases. And there are additional Berry phases closely connected to the quantization of spin, which, in recent years have been related to 't Hooft and Lipschultz-Mattis anomalies, so that's what I'll call them. And these are crucial to understand the fate of this gauge theory describing the spin liquid. And so what we showed was that at low energy, the theory is always confining, and it can confine either by a Higgs transition to an AL state, which is what's observed, or some kind of valence bond solid where these resonating valence bonds resonate for a while, but eventually they crystallize in some regular arrangement. Okay. But there wasn't, so there might be some spin liquid character here at low energy, over some energy ranges, but there wasn't truly any spin liquid at the longest distance scales. So, however, a few years later, attention turned to this phase transition. It may be near the phase transition, there is some interesting spin liquid present, without quasi-particles. And there's been a huge amount of work studying the nature of this critical spin liquid, which I'm going to update you now on. But a somewhat parallel development, starting around the same time, maybe even a bit earlier, was this remarkable paper by Ian Affleck, who recently passed away, and Brad Marston, where he follows the same route and write the spins in terms of partons, but now in fermionic partons. And they found that the optimum mean field theory for these fermionic partons was one that gave you massless Dirac fermions spectrum at these 4 points. So this is very similar to graphene, where you have massless electrons, which carry spin 1/2 and charge E. You have massless spin-ons, which carry spin 1/2, but no charge. So they're not directly observable in some kind of photo emission experiment. And they postulated that there was such a low energy theory for the antiferromagnet. And if you look at the full gauge structure, if you get a theory that's very similar to quantum chromodynamics, it's got massless fermions at these 4 points, and it's got an SU2 gauge field. The number of flavors is 2 because there's a doubling of the unit cell because of a background pi flux. Anyway, so they said, okay, here's a possible state of which almost nothing was known at that time. So there, as in QCD, there are 2 possibilities. One is that the theory confines at low energies. And the other sort of analogous to the Bank-Zaks fixed point, that it leads some kind of critical state. And so what is the answer? So the first thing you can ask is, what is the what are the possible confining fates of QCD? Now, in quantum chromodynamics in 3 dimensions, we know the consequence of confinement is chiral symmetry breaking. So what is the analog of chiral symmetry breaking here? So that was worked out by Ran and Wen a few years back. And what they found, quite amazingly, that the confining states are exactly the same that you had obtained from the bosonic parton construction. Okay, so that was a key hint, although it took the community a little while to appreciate this result. But today we have some very beautiful work of a sort of a triality describing this critical spin liquid. There's really three different ways to talk about it, each of which are perfectly valid on their own, but they're all strongly coupled theories. The reality is something in between, which is present in, I believe, in the cuprates and many other materials. It's some nearly critical square lattice antiferromagnet, which doesn't have quasi-particles obeying these, and the whole structure of the field theory is constructed to obey the right anomalies. And in fact, the way the anomalies appear are, as a consequence of the massless Dirac fermions in this formulation. Then there's the bosonic spin-on formulation that was originally discovered. And finally, there's a third formulation, which is deals directly with physical observable of the Néel and VBS orders, but then it has a topological term, the Wess-Zumino-Witten term, very similar to the term that Affleck and Haldane talked about in one dimension many years earlier. And the recent progress has been that there's been just some heroic numerical work, including on the fuzzy sphere, which has really confirmed this basic picture. And so there is a nearly critical theory. It seems to confine all, at some very long distance scale, but for the experiments, I'm going to argue that's really not relevant. Okay. All right, so that's an update on, I think, very impressive progress on what's turned out to be a remarkably subtle problem of something that you would think is just very simple, the square lattice antiferromagnet with some frustration. But I think we're finally starting to get a picture of the kind of spin liquids that you get. And it's taken 3 decades of work because the ideas involved have been remarkably subtle, and also the numerical techniques required have been very innovative. All right, but now let's dope this spin liquid. So I'm going to just talk about the doping in a very simple pictorial term to begin with, although you can't take the pictures literally because they don't apply to these critical spin liquids. But they give you the basic idea. All right, so now we want to talk about metals. Well, ordinary metals, we have a beautiful theory of, and the theory is very simple, going back to Sommerfeld in 1927. There's just a nearly free gas of fermions with a Fermi surface between empty and occupied states. And of course, this is confirmed. Here's the Fermi surface of the whole load cuprates at large doping, where they do indeed behave like an ordinary metal. But a very key result in the theory of Fermi liquids, which was a bit of 20th century physics being discovered, 21st century physics being discovered in the 20th century, is the Luttinger result. And Luttinger showed, it's sort of a topological result, that the area enclosed by this Fermi surface is a topological invariant, that the area enclosed with the Fermi surface is independent of interaction, and is the same as free electrons with the same symmetry and the same density. So this was proved by Luttinger in a perturbative Green's function argument. But a very important step was made by Oshikawa in 2000, where he proved it using a non-perturbative argument and connecting it very deeply to these Etouffe LSM anomalies or Berry phases that Haldane mentioned. So it seems like there was some topological structure here, and you could really explicitly connect these in the Oshikawa argument. All right, so this means there's no chance of avoiding the Luttinger theorem. Well, not really correct. So what the Oshikawa perspective showed is that you can now get metals which do not obey the Luttinger theorem. But you can get them provided there's some fractionalization around. Roughly speaking, this anomaly can be satisfied partly by the Fermi surface and partly by some fractionalized spin liquid. And as long as the sum has the right value, you will get a Fermi surface that doesn't have the Luttinger-Oshikawa value. So this is what we call a fractionalized Fermi liquid. So now let me illustrate this with simple pictures. So here's an antiferromagnet. It's an insulator, and there is no Fermi surface. If you put in a lot of holes, then you lose the antiferromagnetism. You can just think of it as free holes. So if I'm putting density P holes, the number of holes is actually 1 plus P because you have to count the holes relative to the fill band. And so the Fermi surface, after a factor of 2 for spin, should have fractional area if the area of the square is 1, and the area of the green regions is 1 plus P over 2. Okay, and that's indeed what I showed you here, and it works beautifully. There we go. It works beautifully in the cuprates. All right, the other possibility is you can imagine you put in a few holes and you have antiferromagnetic order. So in this case, you just determine the band structure in the presence of this broken symmetry. And what you find are these 4 pockets. And now the area of each pocket now is P over 4. Why is that? Well, the density of holes is P. There's really only 2 pockets because the Brillouin zone has been halved, and they spin a half. So if you take 2 of these pockets, spin a half, you have a degeneracy of 4, so the area of each pocket is P over 4. Okay, so that's, again, an invariant topological statement about the structure of the antiferromagnetic metal. Well, how about if you have a spin liquid, and I'm just showing you a picture of short-range spin liquid of the RVB type, where the spins form singlet, and you have a few holes around. Now, the spins can resonate, and the holes can move around. And if this object that's moving now carries charge but no spin, so it's a spinless charged object, which we call a hole-on, and the density of such objects is P. And so, but however, has no spin. And if it's a fermion, it will form a Fermi surface. And now the area will again be P over 4 because you have 4 pockets. There's no halving of the Brillouin zone, and it's spinless, so P over 4. Okay, but now, so this violates the Luttinger area, so they must have spin-on excitations. That's what our theorem showed. And so they are indeed present. So there are also these excitations which carry spin, but no charge present. But now you can imagine a situation where these spin-ons, which you cost some energy to create, come near the hole-ons, and the spin-ons and hole-ons form a bound state, otherwise known as electron. So why did I go through all this trouble to fractionalize the electron and then put it back together? Well, the point is the number of electrons now, which are these green objects, which is a bound state between a spin-on and a hole-on, is P. It's not 1 plus P. So these are really electron-like excitations about a spin liquid. Now, if they form a Fermi surface, they are spin-a-half objects of density P, and there's no broken symmetry. And so the area enclosed by any one of these objects, these Fermi surfaces, should be P over 8. Okay, so to summarize, if you just do a very simple study of doping an antiferromagnet, you can get in the antiferromagnetic metal and the hole-on metal area of P over 4 in this FL star state, which we think is the most likely, P over 8. And there's a factor of 2 difference, which is really crucial and also robust to all sort of interactions. So I could just understand this just by simple counting because of all the invariant anomaly arguments associated with this structure, with these areas. All right, so now let's finally look at the phase diagram of the cuprates. So what I've been talking about really is about the pseudogap phase, which is a metallic state where it seems, I'm going to argue, there is spin liquid character. And so many people have studied, I could talk for hours about all the experiments on the pseudogap, but I'm most excited about a recent experiment from late last year on something called the Yamaji effect. I too had never heard of the Yamaji effect, but it's something quite common in the study of quasi-2-dimensional materials. So what they have done is taken this particular cuprate and studied the Yamaji effect at this temperature here. And what you do is you apply a magnetic field at some angle relative to the c-axis. So this is the angle here. And so the electron will undergo an orbit along, as shown by the red arrows. And this orbit is on a Fermi surface determined by the two-dimensional Fermi surface I've been talking about, along with some tunneling in the c-axis, which gives you the small warping. So what Yamaji showed was there were certain very special angles at which the area enclosed by this orbit was independent of the momentum in the z direction. So we essentially got flat bands with essentially no motion in the z direction. So the c-axis resistivity would have a maximum. So it's a purely geometric argument. All you need to know is the value of c, and you can read off the area of the Fermi surface from the angle. So this is the experiment, and I quote from the paper, the size of the Fermi pockets determined from the Yamaji effect is 1.3% of the Brillouin zone area. So the experiment has p equals 0.1, and the FL star is 1.25, and all the other models are 2.5%. So this is very exciting. It really gives you positive confirmation of this, this particular doped spin liquid state. And really, I think it's the strongest evidence as yet for the relevance of a spin liquid, any spin liquid at this point, for the cuprate superconductors. All right, how am I doing on time now? I start 9:50, right? Okay. All right, so that was the simple introductory part of the talk. Hopefully you all kept up with me. It's all pictures. Really, there was nothing more. And it works. And it led to this prediction that naturally we're very happy about. All right, so now let me say a bit more about the pseudo gap, and also then, of course, the big problem, superconductivity. So let's start from the pseudo gap. So I've just argued from theory and also confirmed by experiment that there are whole pockets of size p over 8 that violate the Luttinger rule. And so by our arguments here, very general arguments, there must be spin-on excitations present. So then the question is, which spin-on excitation, what is the relevant spin liquid, and have you seen them? So where is the spin liquid? Well, it turns out there is actually very good evidence for a spin liquid around. And to see that, let's look at a theoretical calculation here done by Federico Becca here at CISA. No, at the University of Trieste, excuse me, I think. Where he's looking at the square lattice antiferromagnet as a function of frustration along the diagonal, J2 over J1. So this is this perfect square lattice antiferromagnet, which has Néel order, and you see the spin wave spectrum. But as you turn up J2, you come to this border of the Néel VBS transition, which is around 0.45. And you see this very continuum structure with characteristic shape in the momentum space. This is energy and this is momentum. And these continua are basically a direct signature of the presence of some kind of gapless spin-on excitations, which are computed numerically in this paper. So I just want to show you here, there's a couple of such measurements of such continua and X-ray scattering. This is the work of Stephen Hayden's group. And what they see in the what they see as a function of doping is strikingly similar. In the insulator, you have very sharp spin waves. As you dope at these higher energies of order 2 to 3J, you see these big continua, which in fact, their broad features match these numerical calculations quite well. And I don't see any other plausible explanation for what that might be. And in fact, the numerical calculations are precisely for this pi flux spin liquid that I mentioned. All right, so that's good. Then how about going to the superconductor? So how would you go from this metallic state to a high temperature superconductor? Well, the knee-jerk reaction is if you've got a metal and you're going to get a superconductor, you've got to pair the excitations on the Fermi surface. Well, what happens here? Well, here you run into problems. So if you take the Fermi surface that you get in the FL star theory, so in addition to the Fermi surface, you also have these 4 spin-ons of Affleck and Marston. And now you pair the electron-like objects on the pockets. So you put in some D-wave pairing, just by, that's what comes out of simple calculations too. And what do you get? Do you get an ordinary superconductor? Unfortunately, the answer is no. The answer is no, because this has, nodal points, not just 4 nodal points, it has 8 nodal points, in addition to which it has these 4 spin-on nodal points, and they should all combine to give you 8 nodal points in thermal conductivity, and there's absolutely zero indication of any such thing happening at low temperatures in the D-wave superconductor. So in this case, you find, since you're not, the BCS theory, is a theory of how you go from a metal to a superconductor. So in this case, you find if you apply the BCS theory to this exotic metal, you get an exotic superconductor, which is not observed. So what do you have to do? Well, you really have to look for a non-BCS mechanism for the onset of a BCS superconductor. And it's non-BCS because the normal state is not a Fermi liquid. So, and the key idea is, of course, the spin liquid, as we've already seen, as Anderson emphasized, has all these spin singlets floating around to begin with. So there's already pre-existing Cooper pairs. You don't need to form Cooper pairs. You just need to confine the spin liquid. You need to get rid of the fractionalization. So that's what we've been working on very hard, on how to do this. And in the remaining 5 minutes, I don't think I can tell you the full details. But a very powerful method is this idea of the ancilla qubits. So the idea is the following. You start with your Hubbard model that you're interested in. And you just take a few ancilla qubits around that form spin singlets. So you take a tri-layer system with bilayer of an antiferromagnet. So this has a gap. It has a trivial ground state. And that's the system you're going to study. But we're going to use these ancilla qubits as a way to generate non-trivial entanglement in the physical layer. So in this case, we're not applying gates. We just do a canonical transformation. So if you can convert this model with a Hubbard model on the top layer and these 2 layers of ancilla qubits into a model where the top layer is actually free electrons, and they're coupled by a Kondo coupling to the ancillas. And then to get the theory of the pseudogap, what you have to do is you put the bottom ancilla layer in a spin liquid and the top 2 ancilla layers in a Kondo lattice heavy Fermi liquid, and then you get a very controlled theory of this rather exotic state, which I just showed you in pictures before. And now using this ancilla construction, you can even ask about how this state will become a superconductor. Well, become a superconductor by a confinement transition, and confinement transition is actually driven by the condensation of a Higgs boson, which is a bilinear of the spin-ons between the 2 ancilla layers. All right, so that's a very quick summary of several years of work. But just to show you, you can write down some complete gauge theory of it. So the details are very different, but the structure of this gauge theory is not so different from the theory on the board outside this room. It's got fermions. These are not relativistic fermions, but they move on a lattice, and the structure of the dispersion is strongly dictated by the symmetry of the spin liquid. And there's some gauge fields, and there's Yukawa couplings. And everything is controlled by exactly how these fermions confine and how the Higgs potential determines the fate of the Higgs field. That's really all that we're doing. So for example, here, as I told you, ran into a problem with the Cooper pairing mechanism. But now in this new mechanism, you condense the Higgs field. And what the Higgs field does is annihilate these extra nodes. And you get, at the end of the day, precisely a D-wave superconductor with all the right characteristics. So you really fundamentally used the spin-ons to get the right state. I don't know any other way you can do it. And so the answer is that the state itself, the D-wave superconductor, is basically a BCS state. And there's enormous experimental evidence for that. But the exotic state is the metal, the pseudogap, and the transition, the mechanism of superconductivity, the onset of superconductivity, is not the BCS mechanism. It's the confinement transition of the spin liquid. Okay, so that's my main message. Okay, I'm out of time. There's many other experiments we can explain with this approach. And of course, I didn't tell you anything about the strange metal. That has to do with the condensation of a different Higgs field, this Higgs field over here, and you have to put in randomness and use the SYK model, and you can understand various transport properties. That's a whole other talk, I guess, which I've given here in the past. All right, to summarize then, 2 slides. The summary is that there is an exotic state in the superconductors, which is associated with a critical spin liquid. It's the pseudo-gap state, which we call FL star. Here's a cartoon picture of it with short-range valence bonds, where you've got spin singlets and electrons, not holons, not spin-ons, electrons moving around with a smaller density. And these form pockets of area P over 8, and that's exactly what's been recently observed. And finally, you can start from this state, and by condensing various Higgs fields, get a story for the rest of the cuprate phase diagram. Thank you.
Questions? Remarks?
Is the behavior of the spin susceptibility relevant for distinguishing different scenarios in your presentation?
So the spin susceptibility, meaning the uniform spin susceptibility? Yeah, so the uniform spin susceptibility will be suppressed. It'll be given by these Fermi surfaces. So you get a Pauli susceptibility from these Fermi surface. You will also get a small contribution from the Dirac nodes, but I don't think that's the important one. But there is, the original measurements in NMR and uniform susceptibility of the pseudogap was by such means. And the spin susceptibility is suppressed because the Fermi surface is much smaller. Yeah. But it's finite, and these are spin-a-half electrons. That's another reason you don't want the holon metal. If you have the holon metal, there is no contribution of spin susceptibility. The spin gap is too large there.
More questions?
Yes.
So if I go to Marcus Greiner and ask him that he should check this theories, what can he do, if anything?
Well, okay, so of course I would love for him to also measure these Fermi surfaces. But these are very small Fermi surfaces, 1% of the Brillouin zone area, which tells me you need a lattice at least 100 by 100 to have the right resolution. So you're not there yet to really see the Fermi surfaces. So, this Chan et al. Experiment is quite remarkable that they can see such tiny Fermi surfaces in a very clean sample, but you need a big crystal. But what has been done more in Emmanuel Bloch's group are local multi-point spin correlation functions. They measure 2- and 3-body correlations, and a recent paper in 5-body correlations. So what we have done is taken this ancilla theory with the pi flux spin liquid and written down a variational wave function. This is work with Yassir Iqbal and Ronnie Tamale and Tobias Muller. And in fact, the computations of exactly those observables are in pretty good agreement as a function of doping with what they observe. Yeah, that's another slide I could have shown you. Yeah. But I think the future, I think cold atoms are a very important component of testing these theories further, looking at more complicated correlations of this state in the pseudogap, because they really have a very different set of, different lens on the same entangled state of matter.
How does the pseudogap cross into the strange metal, and is the superconducting state below the strange metal and the superconducting state below the pseudogap smoothly connected to each other?
Okay, I can give several talks on all of that. But, so your question is, how did the pseudogap go into the strange metal? Well, all right. So that has to do with, the pseudogap is due to this Higgs field phi, which is the Higgs field between the top 2 layers. And so basically, when the Higgs field uncondenses, you get the strange metal. And that uncondensation transition is well described by this 2-dimensional Yukawa SYK model, and you get all kinds of physical properties over there. Yeah, okay, so that part is actually quite under control. What's actually much harder is to take this whole procedure and go all the way to the Fermi liquid. Then you have to take both Higgs fields together, and it's still a strongly coupling problem. But I think going upwards here and going down here and going this way, I think our approach really is consistent with essentially all observable so far.
Okay. I think it's time for very last question.
Yeah, super. Which of these physics would take place in a simple Fermi-Hubbard model on a triangular lattice, or which of the physics is requiring a more richer model which has maybe next neighbor couplings and whatnot?
Yeah, so that's a very good question. So let me break it up into two questions. One is, which of this is physics of the Hubbard model, which requires further interactions? We have nothing to say about that. I rely entirely on numerical studies by Antoine George and many other people, Steve White, for answers to that question. What we are doing is we are working backward from observations and writing down some minimal theory with some physical ideas of what could unify everything. We're not at the point where what I would love to do, of course, but perhaps for the future, we have this effective field theory, which I flashed for a minute. So there's for example,
What microscopic Hamiltonian gives rise to your effect?
Yeah, so certainly I believe the Hubbard model gives this, but the details of what's TC and which state you get, a charge-ordered state or a superconductor, depends on some couplings in V of B that are hard to determine. They can take small different values. That's the other part of your question, which of these will happen on the triangular lattice? Well, so another important ingredient here is the spin liquid itself. So this pi flux spin liquid that I've been emphasizing has a property that has a very natural confinement to a D-wave superconductor. It just comes out of the theory. If I take the most natural spin liquid that people have been working with on the triangular lattice, it in fact does not have that property. So that spin, even though you might find a spin liquid in the triangular lattice, you may not find a high-temperature superconductor, as far as we know. So there's really something very special about this spin liquid that gives you exactly the type of superconductor that you see. And that's this Affleck-Marston state.
I think we're running now late, so we thank Subir very much. And we meet again at 10:55. 10:55. That makes for a very quick coffee.
Hi, there you go.
Before we start this session, there's a pair of glasses. Somebody left So we move on with the next talk by Matthias Treuer of Microsoft here, Quantum AI and the Path to Commercial Advantage.
Thank you. So I want to start by saying what brought me to quantum and what brought me to a company ultimately. What brought me there was in high school, I liked chemistry, I liked computing. And then one day on TV, there was a series on the experiments by Alias Bay, and I found that intriguing. I said, I have to study physics. Then for my master's thesis, I got a great opportunity to use this Cray supercomputer, amazingly fast, one of the fastest in the world, about 5% of the power of my watch now. And on that machine, I got a task, extend a quantum Monte Carlo simulation for the Hubbard model or TJ model from 1 dimension to 2 dimension. It should be easy on that machine. Well, until the next day, we realized there's this thing called the sign problem, and the sign problem has haunted me ever since. How can I actually simulate quantum problems, many body problems accurately? So I tried for many years to stick to spin models without frustration, to stick to bosons, but fermions always brought me back. And the reason why it's hard is for the last 5,000 years, compute technology has not changed. The abacus works on the same principles as the fastest GPU. We have not changed the way we compute in 4,500 years. So what we need is we need foundational science to new technologies. And we've seen that many times. Thermodynamics led to the industrial age, the steam engine, big revolution. Electromagnetism led to the silicon age, to the telecommunications, radio, computing, ultimately a big change. And now we're at the verge of the quantum age, and who knows where that goes. What I want to focus on is quantum computing. What can we change in computing with quantum? And there are breakthrough the algorithm ideas, starting with Feynman and Shor and Grover. The question that came up then is, where are the problems really? Well, given the fact that modern computers are so fast, where are the things that you can do with quantum computers that they can't do with classical computers? And so DARPA brought it to a very simple point. They asked, can we build a utility-scale quantum computer? For me, that was a machine that does something interesting that I can't do classically. DARPA asked for more. They asked for something where I can solve a problem, but the value of solving the problem is more than the cost of the computation. That means I shouldn't just build a machine for $1 billion somewhere in a CERN style and do something great and wonderful. The question is that worth $1 billion? We have to find out. But really, to be useful more broadly, it has to be the stage where the scientists can just use it like a supercomputer. So the cost has to also be low enough. And that's where the question we had then was, where are the problems that I can solve from quantum computers that are worth it, that are worth building it? Because when there is commercial value for it, when I can just sell a machine, then there's incentive to actually build it and get it done. So for that, I need two things. First, I need a quantum algorithm with quantum speedup, where the scaling with problem size is lower than classically, the black line being quantum, and it grows more slowly than the blue one classically.
But then we also know a quantum gate operation is much more complex than switching a transistor. And qubits are much more expensive than transistors. And so for small problems, classical machines will always be better. To assess now, where is the crossover where quantum will beat classically, we need constants. Not just scaling, but also constants. And for the first problems, when we looked into that, then these crossover times where quantum beats classically, initially, when we looked in 2011, 2012, it looked daunting. It sounded like what I read in the novel that, yes, we can build a machine that in 7.5 million years calculates the number 42. But we don't want the crossover time to be millions of years, we want it to be weeks. And so now, what are guidelines we can have? What are the problems that we can solve where a realistic quantum computer that we can imagine building in the next decade beats a classical machine? For that, I'm the quantum optimist. So quantumly, I'm taking something that I think we could build, something optimistic that I would love to have. It will take us years with 10,000 logical qubits with a logical cycle time of microseconds. Super fast, I think, is something where we could get to, but it will take us some time. That's on the quantum side. Over there on the classical side, I'm pessimistic. I'm taking a single of today's GPUs. You know, data centers, we have millions. I take a single one and assume there is no progress on classical computing. And when I look at that, then these single chips we have now, they are amazingly fast. That GPU is 100,000 times faster than that old Cray I had, a single one. And when I compare the specs, then we see the cycle time is faster classically. Transistors are just faster. They're smaller, there are more here, but here what it leads to at the end is we know much of computing is limited by loading data. The big data problems are challenged just because loading data is slow, and the GPU can only load 38,000 gigabits a second, 38 trillion bits a second. The quantum computer with these specs, with 10,000 logical qubits and 10 microsecond cycle time, can do 1 billion operations per second, and thus the absolute maximum of data it can load is a gigabit a second, assuming big breakthroughs in algorithms. That shows already that for I/O, the quantum computer, this optimistic one for the future, is about 38,000 times slower in loading data than the classical computer. So we will not use it for big data problem, no matter when people say, yeah, it will be great for big data because the wave function can store exponential data. Okay, yeah, that's nice, I just can't get it in, I can't get it out. So we're looking for small data problems. And the other criterion is the speed. That quantum computer with quantum speed up needs far fewer operations than a classical one. But if I just compare, that machine can do 2 times 10 to the 15 floating point operations a second, 2 petaflop. The quantum computer we estimate about 10 kiloflop. The constant overhead is about a factor 10 to the 11. Now when people ask me where does the 10 to the 11 come from, there is an overhead due to the error correction. There's an overhead due to the clock speed being slower. But mostly, basically, it is the digital signal processing, all of the processing I need to control the qubits. Just think about how many transistors do you have to switch to for the control. That gives you the number roughly. We estimate that for the Majorana machine, we would need about 20 GPUs actually to control it. So it's optimistic. Now with that, saying there is about a factor 10 to the 10 constant difference. I need to switch 10 to the 10 transistors per logical qubit operation. With that, if we look at Grover's algorithm, we realize Grover's algorithm has a quadratic speedup. For that quadratic speedup to overcome a factor 10 to the 10 slowdown, n has to be 10 to the 20. so that 10 to the 20 calls to the classical oracular classical function are the same speed or then later slower than the 10 to the 10 quantum calls. But doing 10 to the 10 quantum operation, 10 to the 10 or 10 to the 20 classical ones, if there's a single floating point operation in my oracle, it takes a year. If there are 1,000, a pretty small optimization problem, it takes a millennium. What we learn from that is quadratic rover speedup is beautiful theoretically, it's not enough to be practical. When you go to cubic speedup, I could maybe do a small problem. Quartic speedup starts being interesting. I can do a function with few hundred or 1,000 operations, and quantum can beat classically in weeks, potentially. That's against the single chippy, the U again. But ideally, I want like a polynomial speedup. That's where we're most likely to succeed. When I then look at all of the problems that have been proposed, from big data to weather prediction to drug design, materials, and so on, then I realize we know two application problems that are small data and an exponential speedup, and that's Shor's algorithm for cryptanalysis, and it's simulating quantum systems. With Shor's algorithm, we can't make money. So the application of quantum computer will be what we all like, simulating quantum systems. Now, when I say that, then of course I like that because that's why I came here. You like it. But people on my team were disappointed. They said, I joined the quantum team to change the world. And now you tell me all it can do is chemistry and material science. I'm so disappointed. And the reason why it works goes back to Feynman. Nature's quantum, so we need quantum hardware to actually simulate it. And when I want to know, for the question asked to Subir, for the Hubbard model, will that show that phase? I want to have a quantum computer, ultimately. But then, when people ask me, why are you interested in quantum computing if all it can do is chemistry? Then if you ask a chemist, of course, they know that. Because 96% of all manufactured goods are based on chemistry and the materials. I just don't know the 4% that are not. And it impacts everyone on the planet. So if there's one thing with which we can change things in the world, it is chemistry and physics, material science. I think we all agree there. And problems we can then tackle could be self-healing materials, PFAS-free chemicals, new coolants, better batteries, and in the end you can all help me to find more applications. So how do we solve these problems? It's not just brute force on quantum hardware. That will not work. There needs a machine that's much bigger. We do it combining supercomputing, HPC, quantum computing, and AI. And for the AI, there was one thing that I regretted stopping when I moved to Microsoft, namely back in year 2016, in my postdoc, Giuseppe Caleo, asked the questions, do AIs dream of Schrödinger's cat? And said, can we actually learn quantum states? Can we use machine learning AI for solving quantum problems? And I told him, I don't know, but let's try it. And then he surprised me that it worked much better than the best classical methods we had. And so we can learn quantum ground states, dynamics, pretty well, and that was surprising that the standard ML models, even simple ones like restricted Boltzmann machine or simple Ising model, effectively can learn quantum states much better than the fanciest the Yamaji algorithm can. we understand now why. And the reason is something that we've seen often in the AI. If we remove the human bias, we get approaches, ansatz functions, wave functions that are better than we thought could exist. So we used that recently. We trained models based on classical data, DFT data, and we said, can we actually use the AI models for forces, energies, and similar to design a new material? Then we said, yeah, let's try that. We can do that. But then my boss told me, we're not writing a paper, we're making something. So he said, why don't we make a new solid-state battery? And I said, hey, wait a moment. We are computational scientists, we are writing our codes, we're used to write a paper. He said, no paper, make it. And so then we sat down, and within about a month had the new candidate for the solid state battery material. 6 months later, we had the working a battery that uses far less lithium than standard ones. So how did we do that? In the time of a week in which I could have simulated on a big cluster 1,000 existing materials, using AI, we trained a model to predict simulations much faster. And that allowed us to simulate 32.6 million potential materials. So we took all known materials, 260,000 crystalline materials known to mankind. And then we started to substitute atoms, substituting copper by iron and so on, all possible substitutions with about 50 elements that are safe and cheap and abundant. That gave us a space of 32.6 million crystal structures containing lithium. And then we screened them using AI, checking which ones are stable. Found the 600,000 new materials. As I said, let's write a paper. My boss told me, no paper. We go on. Then we said, okay, then let's filter it for ones that have the right electrochemistry and where the band gap is large enough because the electrolyte has to be insulating. And so then we said, we want ones with the band gap of more than 3 volts. Then we found 771 materials. Most of them were new. Then those we checked with DFT calculations, and that brought it down to 583. The false positives were ones that weren't just totally off, but where the band gap was maybe 2.9 volts instead of 3.1 volts. So it came down a bit. And then we looked later, next, can we simulate the transport of lithium through them using the AI again, and brought it down to 74 materials. And the good news is that among those were the best known ones. So we said, yeah, we're on the right track. And then we looked for and found 18 where we had an idea how we could make them in the lab and went to experts. And the experts told us, no, that can't work. They get every week proposals from theorists about new materials. It never works. And now we come from Microsoft doing software, and we pretend we can do better. It doesn't work. And by the way, that material contains lithium and sodium that will always phase separate. That cannot exist. We told them, no, trust us. We simulated it. Believe us and try it. And then since we paid them, they actually made it for us. And then they said, wow, it works. And that's when they came back to us and said, the amazing thing here is not that you made it, but it takes them 4 to 5 years to find the new candidate. And with AI, we could actually get something in a month. Now, that's where it can go. But I've been cheating here. Electrolytes are insulators. Insulators are boring. No entanglement. DFT works pretty well, so that's a simple material in some way. I want to do that for all materials, superconductors and more. So for that, I need more than that. I need more accuracy than I have. For example, if I want to look at the simple chemical reaction, and here I have the ethylene reacting with ozone, and I want to know what comes out. And I look at the reaction paths. I want to find, and that's a very simple reaction, but I want to find out which path is taken. Typical chemical reactions with catalysts have thousands of steps. What is important in finding the right path in how things react are the energy barriers, because they tell us the reaction rates. Simple activation energies. And to find out which way it goes, I need thereabout to be small enough, at least smaller than room temperature. And density functional theory often doesn't give us the right energies for transition states. For ground states, it often works pretty well. For the transition states, it gets harder. So for example, in this simple case, if I do the calculation with DFT and find out what comes out, then I find this ring here. Well, actually, it's the other state that comes out. So I get qualitatively the wrong answer, the wrong products if I simulate it with DFT. And so for calculations, the more accurate it has to be, the more expensive it is. When I want to look at just a structure, protein folding, conformation, then I can do it with classical force fields, molecular dynamics, protein folding. Basically, the scaling is linear in the size. We can do that cheaply on big systems. When I want to go to drug docking, I need to include some more of the quantum effects approximately, the semi-empirical methods treat the Coulomb interaction. Classically, the dynamics, quantumly, partially, the scaling is quadratic. It's a bit more expensive. DFT, the scaling becomes cubic. Now I get the electronic structure, but it's mean field, basically. When I want to go to reactions, I have to include the correlations. The chemical bonds are entangled. When I break them, I need entanglement or I can't describe it. So I go to methods like coupled cluster methods. The scaling now becomes the 7th power of the problem size. Now it gets expensive, thousands of dollars for calculation. And when it's really entangled, then I want to solve it exactly, and then the scaling becomes exponential. And that's where quantum comes in. And with quantum, I can do the exact calculation with the roughly cubic scaling. So I can do much more accurate calculations. So I can get an accuracy that I can't achieve classically. And with that, I can then start looking at chemical reactions, new batteries, other things, much better. But when customers ask me, can I use quantum computers to accelerate protein folding? Can I use quantum computers for my drug discovery? Then in the past, I told them, no, if DFT is good enough, then don't bother about quantum computing. My story has changed to now tell them, if you want to make protein folding faster, use AI. If you want to do your DFT faster, use AI for that. And that way, by training models based on the data, and then using these AI models to predict the results, I can do things faster. But it's never better than the data I've trained it on. So it gets faster, but it still only has the accuracy of DFT. Now, with quantum computers, the calculation might be slow. It might take days for a chemistry calculation. But once I have that, I can use all of the data to further train AI models. And so the real breakthrough will come by combining quantum and AI. By using selected results from quantum computers to train better AI models, those calculations might still take a day, but the inference calls on the model I'm using just takes a second. And with that, the speed, with that second, I get results with that, I can have the breakthrough. So what we do now today is we look at the molecule or the material, I simulate it, and then based on all the data we have, we train AI models. And then we use those models to predict what the simulation would give us. And then we use that first as the stand-in, and the milliseconds, I get a force or get an energy that would take me hours to calculate. That let me screen many more compounds. What I will do when I have a quantum computer, I will find out selectively what are the cases where the classical results I have are not reliable. I would use the quantum computer there. I would then not only use it once for that specific paper I'm writing, but I would use it to refine the model. So I take the classical models as a pre-trained model, and then would refine it with selected a few thousand data points coming from quantum computers to getting a quantum refined model that then has the speed of AI and the accuracy of quantum computing. And with that, we'll have a big breakthrough in chemistry. And with that, you then also don't need the quantum computer to use it. We use the quantum computer to train it, and then we can share it with many people who can use it on classical computers. So we'll have a much bigger impact with quantum computing. Is this feasible? We can't show it yet with the quantum hardware that they can do things that we can't do classically. But we took a model, and we trained it first on DFT data and compared it to the best classical results from the coupled cluster for the barrier here. And we found the error scatters a lot by 10, 15, 20 millihartry. The room temperature is roughly 1, so those errors are just far too big. And then we refined the model with just about 10,000 data points from coupled cluster data, more expensive, more accurate, and it learns it much better. And so we showed here that when we have data that is pre-trained on 15 million approximate results, and we refine it with a few thousand good data points, the model gets much better. And with that, then the vision becomes ultimately that with that we should get AI models trained on quantum data that lets us kind of find materials and chemicals where with the high likelihood the candidate I get will work. But when I have a molecule, the next question people ask me, how do I make it? That's why I can use the same models to find the synthesis pathway, when tell the lab chemists how to make it. And then ultimately, the next question is, what is the life cycle of that molecule? How will it react with air, with water, with ozone? And that one could try out, or one will be able to simulate it. So the vision is that we'll be able to do all that in silico with AI once we have the models trained with quantum computers. So that's the vision towards technologies here and where the big impact can come. Now, what we need for that, we'll need a quantum computer with about 1,000 logical qubits, or 1 million physical qubits. That's the scale. We now have mostly physical qubits. We've entered recently what we call level 2 the first machines with logical qubits. We heard some great results from yesterday. We're making progress, but we need to reach that scale. The advances come on the algorithm side. The advances also come on the hardware side. On the algorithms, when we first looked at chemistry calculation with the best algorithm back in 2014, the estimate was that if I had a quantum computer with a logical cycle time of a nanosecond, physical operations of sub-nanoseconds, it would take me about a few million years. We said, there's a problem with chemistry. But then we used all the tricks we know from classical supercomputing to bring the runtime down, and then said we wanted to be about a month. And then in 2017, making things faster by a factor near 10 million, we said, yeah, if I had a machine with 10 nanoseconds logical cycle time, I can do it in a month. That's still hard. Then basically since then, about every 3 years, we have a progress of a factor 1,000 in the algorithm. So that now we're at the point where I can do it in a day if I have a machine with a logical cycle time of about 50 microseconds or a physical operation time of about 1 microsecond. Now it's become totally feasible. And as we improve things more, things will relax a bit more. So we are at the point now where with the improvements on the algorithms, with the combination with the AI and with new hardware improvements, we have line of sight of getting soon, meaning in years, not decades, to a machine that can do chemistry. People also ask me, how do you program that? And it was Bill Gates who asked recently, okay, who does even know how to program the quantum computers? And the answer is simple. It's AI. You go to GitHub, VS Code, you just type into the Copilot, your chat box, write the quantum algorithm for Grover search, optimize the code, refactor it. The AI models can write and test and debug quantum programs now. Not just that, they can also go just to GitHub and tell it, run this quantum algorithm on quantum hardware. And they ask me which ones, IonQ, Quantinuum, Rigetti, and then tell it use the Rigetti simulator because it's cheap and free, and then run it, and then here's the Bell state, the preparation, and then when I ask it to download results, it downloads them, it shows histogram, and looks at the data, and the AI just comments about half the time it's 0, 0, half the time 1, 1. That's expected because it's Bell states and so on. And this is what the AI just gives me as comments when I get the data. So it really helps us run simulations. So we're now in level 2. We're not there yet where we can go to chemistry, but we've made logical qubits last year with 4 logical qubits here first with Quantinuum, then we made 12, and last fall 24 logical qubits with the atom computing. And when we want to go to scale ultimately, that's where I think we can push far with neutral atoms, but to really scale, we bet on the the Majorana 1 chip, the top the logical qubits. And let me tell you why. When I look at the full stack of the machine, if you want to run a computer that does about 1 million instructions per second, but at the hardware level have about 1 million qubits, where I do an operation every microseconds, then I'm doing about 10 to the 12 instructions per second. And I can do that if I move the control, in this case, down to the cryostats. So what I'm doing is I'm sending the logical qubit operations down to the cryostat. There I have a cryogenic CMOS chip that controls the qubits. And then I send the measurement results up to room temperature, the analog signal, and they do the signal processing at room temperature. I still have to do about 10 to the 12 control operations per second. And that's a lot. The reason why I like the Majorana qubits is that I can do all the operations I need for error correction just through measurements and joint measurements. These are the 4 steps I have to do for a surface code. I'm just doing measurements, X measurements, XX, and CC measurements, and I can turn them on and off with a simple digital control pulse. So I only need a transistor for gate operation. I don't have to send in a microwave pulse or laser pulse. I can do the operations, the measurements, just with transistor switches. Because the topological qubit, due to the topological nature of the phase, allows me to do the gate operations purely through measurements. So I need no fine-tuning. But what we need is, we need really the best people in the world for it, for quantum in general. We need the global talent. We need to educate get people in there. They're in line with the mission of the ICTP. I want to end with the video we made for the launch of the Open Quantum Institute that's run now by CERN Geneva, and I like the video because it shows the vision of where quantum can take us. Thank you.
Thank you very much. Questions?
Hi. As a representative of Microsoft, what is Microsoft's interest in this? Does it want to become the provider of a platform for development, or does it want to really use the development as to make them, I mean, to create new chemicals, or what else?
Both. So we are a platform company. We want to have the cloud platform, software tools, the AI to help. We want to also make the quantum computer and use those of the others to then do the application. But we are not a chemical company. We are a platform company, so we will partner with somebody. The main value comes not from selling hardware, but from making products and chemicals, and so that's where we'd like to then partner with the thing. What I want to do, I want to finally get my master's thesis done. The topic where I failed the first one. Yeah.
More questions?
Hello, thank you for the nice talk, and I enjoyed your talk. And I know that Majorana 1 is the first topological qubit you developed, and somehow there has been the idea around in the society, and those superconducting qubits and the ion trap qubit and so on has a fidelity of the 99.99 and so on and so forth. And probably your goal to use that topological qubit will be achieving the topological stability there, right? But let me try to understand the current status of a qubit there.
Yeah, okay. So when first there was kind of in the 90s the idea of topological qubits that could give you 59 fidelities or 29s, that was the mathematician's dream. When you build something just to measure things, you will be limited to 4 nines, 5 nines, 6 nines. So the main advantage we realized recently, kind of planning for the million qubit scale, is that it's not the protection that makes the qubit that much better, because once you are at 4 nines, 5 nines, then it's good enough to build it. The real advantage is that because of the non-abelian nature of the phase, what was shown in the Duncan's talk, with that we can actually do all of the Clifford gate operations purely through measurements. I can natively do a Z measurement, an X measurement, a Y, an XX, a ZZ. So I can do all of the Clifford gate operations through measurements. And measurements allow for digital control. I just turn on a measurement and turn it off. I need no fine-tuning. I need no rotation gates, really, that do a Haldane gate or a C-naught through an analog control pulse. I can do it with just a simple digital transistor, switch on, switch off. So the scaling will be easier. That is the reason why we build it.
I see. So your point is that following the measurement, you can obtain certain quantity which is supposed to be topological in nature. So that somehow eases the process.
Yes. So I can do all of the steps needed for QSC, all of the syndrome extractions, purely through measurements. I don't need any gate. I can just do it just with measurements of the non-abelian states in the system. That makes it easier to scale.
All right, thank you. Yeah.
More questions? Not, then we thank Matthias again very much. So the final talk of this session is given by Giorgio Parisi, University of Rome. Giorgio is, of course, besides many other things, a great friend of this place. He's also been the president of the Italian Accademia Nazionale dei Lincei. This gives me the chance, actually, to mention this Accademia, which is, of course, a rather famous one, having had Galileo Galilei as a member, so one of the oldest ones, but also it's a co-sponsor and a co-organizer of this very meeting, and we're very, very grateful for that. So now Giorgio is connecting, and he talks about quantum versus classical algorithmic complexity.
Okay. Thank you very much. Thank you very much, Elio. Thank you to everybody, here. Let me, what's happening? Okay. Okay, the things that I would like to discuss is the relation between algorithmic complexity in the quantum versus the classical case. The essential idea that, let me make first a general statement. We had a lot of discussion here, especially today, about a quantum computer, but there are also some other objects which are quantum, that are quantum simulator. A quantum simulator aims simulate some physical problem, some physical object, therefore they are not computed in the standard sense, or if you want, they are analogical computer, and they have been used many times in some special in computation to solve some something that people usually call optimization problem. Now, what is optimization problem? The typical problem optimization is very clear. We have a function f of n variable, and we want to find the minimum of that function. That is easy. Now, it's clear that you can say the same things in a slightly different way. We have an Hamiltonian that depends on n variable s, and we want to find the classical ground state of this Hamiltonian. Of course, we have also some other optimization problem. We have a quantum Hamiltonian, and we would like to find the quantum ground state with function of the type Hamiltonian. Now, of course, if the value of variable n is small, everything is trivial. Things, not trivial, but relatively easy. The things that really becomes quite complex when n is very large. I mean, n is very large, I mean 100, 1,000, or if you are interested from the theoretical viewpoint, also what happens when n is going to infinity, because n goes to infinity, especially for the physical problem, corresponds to the thermodynamic limit we are all interested. Now, let me just present some classical case. And in the classical case, I will restrict only to variables which have two variables, plus or minus 1. Or, if you prefer, 0 and 1, therefore you can consider a bit. Now, there are some type of problems that are deterministic problem. And this deterministic problem is, for example, one famous problem, the following. You have n spin variable. You construct that you put on the line. You consider the correlation of this spin variable at distance k. This defines the correlation C of k. And you put as Hamiltonian, or if you want as cost function, the sum of possible square correlations. Therefore, the problem that you would like to solve essentially is to find the sequence of a chain of spin variables such that the squared correlation have the minimum 1. Now, the problem is rather complex because it's quite easy to find the opposite, to find the square correlation, the maximum 1, because you will put all spin equal to 1, and this will increase in the correlation. Decreasing the correlation to the minimum is something that is not easy at all. There are some solutions that you can do on the closed chain. On the open chain is non-trivial. And this is something that people were interested in communication, because this is related to people what called merit function in communications. That a merit function would be the inverse of h, and there are known solutions up to n order 100 to 1,000. And however, they are not the best solution, not known for higher value of n. And also, unfortunately, from the theoretical viewpoint, there is nothing that tells us what happens when n goes to infinity, because people have not been able to do it here. I mean, there is some variational theory which poses a lower bound and so on, but nothing precise. Now, this is a deterministic problem, and therefore you can ask n is equal to 156, which is the best one. This may be useful for communication and so on. And of course, when you have a deterministic problem, to discuss how long it takes to do the computation, maybe it's more or less nonsense, because maybe I arrive to some smart mathematician may find a close formula for any value of n, and the computation may be very short. For example, this is not impossible because the cyclic problem in which the correlations are taken on a closed chain, there for certain value n, there are some exact solutions that one knows, in which one uses some prime, something related to prime number theory and so on, to Lagrange symbol and so on. The problem where things becomes more difficult is, I mean, it makes more sense to discuss how long it takes to do the computation, a random problem. Random problem, we may have an Hamiltonian. The first Hamiltonian that I write on the left is that's a standard Hamiltonian for spins. And the two-body interaction. Of course, I could add a magnetic field if you wanted. The second, the one on the right, is Hamiltonian, which is similar with a twin-spin interaction. Now, if you discuss of the time that you need to solve a random problem, we would like to specify which is the probability distribution of J. Because, for example, if all j are equal to +1, all j equal to -1, you can easily solve the problem. And however, you have the problem, the physical properties of the problem depend strongly which is the probability distribution of the j's. This problem, as you can understand, is studied a lot of time in literature. And indeed, for random J, it is called a spin glass problem. The name spin glass came in the 60s, starting from some material that I don't want to discuss as a material that gave rise to spin glass. But essentially, the idea that the system were a magnetic material that behave like a glass. So someone, I've forgotten whom, suggested the name spin glass. Now, depending on the choice of J, you have a different model. You have what people call the Sherrington-Kirkpatrick model, in which we assume that all J are different from 0, a random number, and just to have the Hamiltonian scaling in the correct way, they are proportional to z n minus 1 alpha. You have some other models that people call beta lattice model, in which most of the j are equal to 0. They have to differ from 0 with probability z over n. And in this case, there will be plus or minus 1. So it's, while the Sherrington-Kirkpatrick model from the physical viewpoint is very far away in some sense. Okay, let's discuss the third model, which is a more realistic model. It's the Edward Anderson model in this dimension, you take the J at random, but different from 0 only if the two spins are nearby in the physical, on the physical lattice. Therefore, this is near-neighbor interaction. So you have a different kind of models. For physical viewpoint, the Edward-Anderson model is what should describe the physical material. Apart after you can add Heisenberg coupling and so on and so on. But for Ising, this should be the physical material should be described as the Edward-Anderson model. But you can go into more simple model from the theoretical viewpoint in which you keep in the better lattice model the fact that the each spin interacts only with a finite number of spins, or you can go to the central-Kilpatrick model, which is that everybody interacts with the other. While one can believe that the Sherrington-Kilpatrick model, the Sherrington-Kilpatrick model is a mean field model, and you can compute the properties Hamiltonian in an exact way. The better lattice model also you can write formula, variational formula for computing the free energy and so on. The three-dimensional model, the finite dimensional model, still are not completely understood. I mean, there are a lot of work can be done, a lot of theory, simulation, and so on, but they do not ever close the things. Now, the other type of Hamiltonian that you may consider, you can consider, for example, an Hamiltonian of this type with a three-spin interaction, this three-spin interaction Hamiltonian, and now you can have something where the J are completely random, or you can consider a three-spin interaction which is something that the ground state is planted. I mean, the thing is essentially the following. You construct, suppose that you take J equal to 1. If all the J will be equal to 1, the minimum will be very clear, will be all the S equal to 1. Now you can do something like a gauge transform, and you take the JKL equal to SA, SK, SL, and now in this case, you can find that the ground state, you cannot see immediately which is the ground state, but the ground state is SI given by the small s equal to the SI. So these are models in which you want to compute the minimum, and this model can be studied analytically, but one is to study analytically the model. The other problem that is more difficult is once that people give you an instance of the model to find the solution of the model. Now there is some, I mean, this type of model that are more optimization model, I mean, problem of finding a minimum, and they have there is a mathematical theory that have been developed in the case where it's easy to do mathematical theory. And the thing is the following. If we look to all previous Hamiltonian, the time to compute the Hamiltonian is polynomial in n, in most cases linear in n, and so on. But if we want to compute the ground state in a trivial way, the number configuration is 2 to the n, and therefore we cannot compute. I mean, it will take a lot of time to compute these things on a sequential computer because we have to do 2 to the n steps. And therefore, you may expect that the things goes, this simple algorithm goes like an exponential way. Now, the thing that is evident that if you have a parallel computer with an infinite amount of parallelism, the computation will be just a polynomial because you just put you make all units to go in parallel, and you will get the things in a simple way. Now, this kind of problems, what mathematician calls NP, and what people, okay, Now, the things which mathematicians are really interested, because the analysis is simple, is which is the maximum time that an algorithm must use to solve a problem to find the minimum in the worst case. Therefore, I mean, if we consider a system like this one, you can ask, first one, you can ask which the time to find the minimum will depend from the formula J, given the algorithm, and the mathematician is interested to the maximum time that takes over all possible instances. This is something that we are, most of people, as physicists, also for practical application, is not more interested in the worst case, but what is interesting is the typical case. So this is something that is for most of the mathematical analysis that have been done is useless if you look to the typical case. Now you see that just because the first observation that if you could run two n processes in parallel, you would find the solution at polynomial time, you may think that this can be done on a quantum system. Because in a quantum system, if you have n qubits, and you could run essentially the phase space is 2 to the n, and therefore when you do the evolution, you could, in some sense, gain this factor 2 to the n. Okay, now let me just now go on to quantum annealer, which is the general idea. The general idea of quantum annealers, that is something that people realize experimentally. The most famous one is the D-wave quantum annealer. And let me sketch very fast the theory. The theory of quantum annealer is that suppose that I take an Ising case, an Ising spin, which is equal to 1 alpha in transverse field. Now we have the people were discussing before, Haldane was discussing of adiabatic theorem. Now I don't think that I'm simply not interested to the very phase, but they said that it's just the old-fashioned adiabatic theorem, maybe on 1929 or something like that, that if we started on the ground state at equal to 0, time equal to 0, and we evolve the Hamiltonian with time, if we are going sufficiently low, we remain always in the ground state. And therefore, the idea, okay, now how can you compute use these things? Well, you can think of taking an Ising spin with a transverse field. Therefore, an Ising spin with a transverse field, we have, for example, we have an Hamiltonian. We contain the spin in the z direction, and one term, if you want, contains a transverse field. Therefore, you couple the spin in the z direction, and you put an external field in the x direction. Now, it's clearly that if you look to the Hamiltonian, there are two cases in which you can find the ground state. If the field in the x direction becomes very, very large, it's clear that the ground state is essentially all the spins aligned to the external field. If you remove the transverse field, everything becomes trivial from the quantum viewpoint, because all sigma z commute, and therefore the minimum of this quantum Hamiltonian becomes just the minimum of the classical one with the sigma z. Therefore, the idea is therefore that you can take some kind of a machine, and once that you take, you can, not a machine, I mean, you construct a physical system which have this type of Hamiltonian, and therefore you say, well, I put at time zero large value of the transverse field, I remove slowly the transverse field, and okay, I found the minimum of the classical Hamiltonian. Of course, what happens is that in the meanwhile, while at the beginning and the ending, everything can be computed classically, in the meanwhile, everything is quantum, and the things becomes really is a quantum part. That the quantum part is interesting. Now, the crucial point is that sometimes when you have a theorem, the theorem says that you have to do the things sufficiently slowly. Now, sufficiently slowly, well, what means in practice that you have to do slowly? The real point is that sometimes if you have a quantum system and you look to the evolution of the quantum system, of the levels of a quantum system, you may have what we can call a quasi-level crossing. The reason is the following, that if you have, let's consider a very simple system, a system which essentially in two wells, one on the right, one on the left, with a some barrier in the middle. You change, if you change the level, and now if you would change the level and you would neglect, if the barrier would be infinite, what you will have that one level will be the ground state in one well, and the other level will be the other one. If you now, the barrier is not infinite but finite, you get that just near the point where the two levels are nearby, you have the two levels become hybridized, and therefore you have this type of okay. You have this type. Okay, well, it's not okay. You have this type of behavior here, where you have this part which is more or less an analytic continuation. This part an analytic continuation, and now in order to do this, therefore, if you go very fast, the moment in which a wave function starts to be a superposition of the two-wave function is something is very short, and therefore the system, you think to go on the ground state, and you jump from this state to another state, and you miss the fact that the ground state here is changing. Therefore, if you look, let me do the things in a very simple way. I mean, the theory may be slightly complex, but what you can say, essentially, well, the typical energy, there is an energy gap here, which is delta, and if I don't stay here for a time that is order of delta to -1, certainly I cannot resolve one state on the other state, and therefore I do not give the time to the system the possibility of going from one level to go from here, jumping from one to the other one. And once that, therefore, this type of, when you decrease the transverse magnetic field, you will have a very, very large number of this type of level crossing, and therefore you have to wait enough time to avoid this type of level crossing. Now, therefore, this means that this annealing system, this quantum annealing system, may be useful in solving some problem, but this depends exactly on the structure of the levels, and also this type of system may take a lot of time. Now, which is why? Now let's try to see the reasons why you may expect the classical system have a problem. Because suppose that the Hamiltonian, suppose that I try to make a graph of the drawing of the Hamiltonian as function of the configuration space. If the Hamiltonian as function of the configuration space has a shape like the one showed in the figure, it's quite clear that it's very difficult to find the minimum, because if you just follow a steep descent route, you will be trapped in one of the minimum. And if you use this technique like Monte Carlo simulation or other type of technique, you are going to take a very large time, because you have to jump for barriers that are forbidden by free energy barrier, and also you have to explore all the very large number of valleys. Now, what is nice is that for the system that I described before, one has some information on how the shape it is. And for example, the typical things that one finds, that if you one of these typical problems, I don't want to discuss which problem, is that depending from the parameters, and you find, for example, you're looking for solution of the problem that have zero energy, the set of solutions of the problem from, in certain cases, they're linearly connected, and therefore minimal descent we just bring there. After, depending from the type of solutions, you may have some difficulty, and what happens in a certain situation, that a very low energy configuration is here in configuration space, and another is far away, and therefore in this type of situation where the minimum that you're looking for are very far one from the another one, standard classical algorithms do not find the solution, and apparently they take an exponentially large number of large time. Now, this was an example that I worked with other people 4 years ago. I was taking the very simple Hamiltonian, the three-body Hamiltonian, which have a three-body coupling, and I was considering the case where this three-body coupling was constructed by the product Si, Sk, Sl, which means that the ground state was trivial, because I have to just put a small s equal to big S. Now, suppose now that we have a computer to which we do not give the information on the value of the big S, but we give only the information of this coupling. The problem is to find the ground state. Now, this problem is something that is absolutely not simple. And of course, what is very interesting is that the typical result that you get strongly depends from the type of algorithm. And for example, there are a lot of classical algorithm, and this is the time. This is the time in second. Now, you see the time in second goes to minus 10 to minus 4 to 10 to the 4, therefore there are 8 order of magnitude. And this is the number of variables. And now you see that depending from the type of algorithm that you use, you still have an exponential increase. No one has been able to find classically something that increases non-exponentially. There are some analytic arguments that you can use to find why you have this slope and so on. Now, depending from the, more or less the slope is not so different. And if depending for the ability and for the type of things that you use CPU, GPU, you may have a very large prefactor. Now, this was in 2020 or 2019, the result from a quantum simulator, the wave. So also what you can see is that the result from quantum simulated delay was also an exponential time, and the slope was different. But you see, because the things, the type of problems that you have, depending on your algorithm, if you have a classical algorithm, the problem is how you go from, is how you use thermal tunneling to go for one things from one valley to another valley. And the same problem reflected in the quantum case is the size of quantum tunneling during level crossing. And there is no reason a priori that one tunneling should be bigger than the other one. In other case, the thing seems to work very better. For example, I was very impressed that if we take the case of spin glass, or this type of problem, we take a three-dimensional spin glass, and people were able also on a new version of the wave to find the ground state of spin glasses in 3 dimensions with 5,627 spins, which is more or less 10 to the 8. You may ask why you have this number, strange number. Essentially, I think that they had a big number of spin, about 6,000, but some spin broke down. So this was where the number of spins or qubits that were still working. And they find the ground state and also some excited state with the time that going on exponentially in n, but the prefactor is quite small, is order 10 to minus 3, fraction on 10 to minus 3. Now, if you want to understand if this things is better than the classical computation, it's clear that one has to do some kind of state-of-art computation with modern computer and so on to do some kind of comparison. One thing, when you compare classical and quantum computations, there is something that one has to be very careful. When you do classical computation or minimization, you have one way, there are two types of algorithms. Algorithms which are, if you want, they give the guarantee that you have found the right result. Therefore, it's an upper bound. You use essentially linear programming and so on, and therefore it's an algorithm that give you the certain that you find the right result. However, you have what you do, the other algorithms that are heuristic algorithms. Heuristic algorithms are, for example, just a Monte Carlo, annealing. You take the system, you make the evolution, and you look for the ground state. Now, the typical things that you are doing, and also typical things that you are doing when you use this heuristic argument that you do 10 times, 100 times, if you find always the same result, this is quite likely that you have found the correct result. This is the same things that you do with quantum annealing. With quantum annealing, people were doing this type of changing the magnetic field, and they were doing 20 times. They were satisfied that every 20 times they find the same result. However, it's clear that you cannot compare the things of quantum annealing with the result, a classical result, that where you give you a guarantee, but you have to find that the best classical way that you give a reliable result. And therefore, the conclusions is that this quantum annealing have a potentiality for doing useful computation, and now from problem to problem, you have to do a careful comparison, because in certain cases, a classical method will be the best. In certain cases, the classical method, the quantum will be the other one. And what happened in many cases that once happened that sometimes people claimed that the quantum one was better than the classical things, and this stimulated people to find a new classical algorithm to go in better. Therefore, I believe that a long time quantum computation, also with annealing and annealer, may have some kind of ecological niche to be useful, and it may depend from time to time, and may depend from the problem and from our ability to understand, to do better classical. I do not believe that quantum annealing will break the exponential barrier, that for this problem will be probably also exponential in many of them, but let's see, in the same way the classical one. Now, one thing that is, I think that is important, that I would like just to close on this point, starting from what I said before. One question that one would like to ask after all this, for example, computation and so on, now quantum science, this kind of things is going to change the society. Now, this is a national question to ask here, but I have to recall something that Niels Bohr was saying. Prediction is very difficult, especially about the future. Now, it's clearly that in the past we have seen something that were practically unpredictable. Transistors were practically impossible to predict if you will not have the theory. And also after that they were discovered, it was impossible to predict the use that we are doing these days. Also topological quantum bit, topological quantum computers that we had this morning were something that before the fundamental paper, Haldane and so on, was something completely impossible. Therefore, I think that one can try to discuss some of the possible useful in the society on part of this type of achievement, but it's quite likely there will be a new one that we are going to. How much time I do have?
Very short, yeah.
Okay, just 30 seconds. Okay, so I will just close saying that in this kind of game, international cooperation is fundamental, that we should go on as in the past doing international cooperation, because everything comes from exchange. And I think that there are few systems, few points where greater progress can be done. I just try to mention, but maybe it will take 10 years to see if this list is correct. Okay, thank you.
Thank you very much. Questions?
You mentioned that work by Alex Kamenev with the exponent alpha 10 to the minus 3. That's for the two-spin interaction, right? P equals 2.
That was done for two-spin interaction.
For that case, aren't there also good classical algorithms, this belief propagation and all of that? What is the scaling for that?
Well, in 3 dimensions, belief propagation really does not work to find the ground state. I mean, people, if you want to take 2 real 3-dimensional system, I mean, belief propagation is an algorithm which works when the number of closed loop is small. In the case of 3-dimensional compact things, there are so many closed loop, and no one has been able to use belief propagation or survey propagation for these things. I do not say that it's impossible, but I only say that.
Classical value of alpha so far. What is the best classical value of alpha for that?
Well, the point is that if you look on certified system, the coefficient certifying algorithm is the coefficient may be order 0.1, or so much higher. But if you do heuristic things, what I say, I remember that we were 20 years ago being able to find the ground state for 2,000 spin in a few hours of a computer 20 years ago. Now, what we are trying to see if how much this type of algorithm are able. Therefore, we are taking old code, cleaning, because they were written in Fortran, and nobody now understands Fortran. And we are trying to see, and we would like to have a comparison on the best classical algorithm with the computer algorithm, possible on the same configurations, and to see what happens, but it will take some time.
More questions?
Okay.
Maybe I can just volunteer, not a question, but a statement, like you said. 20 years ago, Giuseppe Santoro and others simulated did the quantum annealing of the Ising model spin glass in 2 dimensions, and very similar picture of Landau-Zener cascade came out. I think in that case, there was a comparison with the classical case, and the advantage came out at very long times. But it was just evaluating the error. So it was just a statement.
Yes, I remember the paper.
Right.
Okay.
More questions?
So quantum annealers, obviously, in the first place, are good for looking for ground states. What about the thermal states and phase transitions? I mean, in particular, what is the status of Edward Anderson in 3D phase transition, critical exponents, the nature of spin glass state, and things like that?
Well, okay. I know I have. Yes. Well, in 3 dimensions, we certainly have. A phase transition for spin glasses. There's no doubt about that. And what happens below the critical temperature is something that is replica symmetry breaking and so on. I think that there are some numerical simulations that point in that direction. Not everybody is convinced, so we will take half an hour to explain where we stand, what we will open in the future.
More questions? No more questions, and we thank Giorgio very much again. Thank you.
You're welcome.
Now the chair goes over to Gabriele Beccaria for the panel on the international scientific collaboration in the next quantum century.
Glielo accendo già.
Sì, accendi pure, grazie.
Aspetta che sono al controllo. Ok, lo metto qua nella tastiera.
Dove vuole lei? Aspetti che tolgo gli occhiali, aspetti. Quanto tempo abbiamo?
Siamo un po' in là, parliamo con aereo.
Sì. Sì.
Siamo un po' in là, possiamo sforare.
Quanto tempo abbiamo?
Teoricamente alle 12:50 c'è il lunch, che diciamo, siccome partiamo molto tardi, probabilmente si può arrivare all'1.
diciamo
Stando caldo, quindi
sì,
potrebbe mezz'ora.
mezz'ora, ok.
Yes, 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 yes.
At that moment, I will need your microphone.
Okay.
Okay, thank you very much. I say that we could start now with this final session for this morning. It's as you know, the panel discussion on international scientific collaboration in the next quantum century, as it was suggested by Professor Parisi, who emphasized the necessity of the international cooperation. And we can say that this issue is for sure an issue of strong debate in this historical moment of, I would say, of both opportunities and threats. So we are all aware that today science and technologies are a collective enterprise, and so also quantum physics can be an iconic example of this international and also multidisciplinary collaboration. And so I'm very happy to have this panel of distinguished hosts which can give us different points of views, I would say from institutions, from universities, from foundations, from industry as well. So I would start to introduce them, and of course we don't need to introduce Atish Dabholkar, the ICTP director, so welcome back to your institution.
Thank you.
David Spergel, who is president of the Simons Foundation, welcome. Alessandro Curioni, vice president of the IBM Europe and Africa and director of the IBM Research Lab in Zurich. Robert Dijkgraaf, who is president-elect of the International Science Council and former Minister of Education, Culture and Science of the Netherlands, and also former director of the Institute for the Advanced Studies in Princeton. And last but not least, Anne-Louise Hillier, professor of atomic physics at Lund University, Sweden, and as you know, 2023 Physics Nobel laureate. So I would like to start from Atish Dabholkar, and I think that we are in the right place to discuss about the necessity of the international collaboration and the possibility of implementing the correct strategies. I'm sorry, I would like just to suggest that since we have about half an hour, if you agree, you could answer for about 3-4 minutes, so that then we'll have a final remark of 1 or 2 minutes for the conclusions. Thank you very much.
Okay, thank you. So I think we've heard a lot about this astonishing progress on the quantum and really breathtaking view of the past and what is going to come. And ICTP, in terms of the science, ICTP has always been a part of this first quantum century. For example, particle physics, which are really fundamental constituents of the quantum. That was our portfolio. But now, in terms of science, we are already expanding it to include quantum information, or even climate science, or in my own field, this very fascinating connection between entanglement and space-time geometry. But let me come to the mission of ICTP, which is more relevant to your question. Our fundamental mission has been for the last 60 years, we celebrated our 60th anniversary, is to make science globally available, ending the geographic isolations. And it takes inspiration from this very nice quote of our founding director, Abdus Salam, that science is a common heritage and creation of all humankind. And I think we heard many talks on Bose-Einstein statistics, condensation, and this correspondence between Bose and Einstein is a wonderful example a century ago of this philosophy. And true to this philosophy, we bring in something like 6,000 scientists from all over the world. We have been doing this. And our fundamental mission is excellence, inclusion, and international cooperation. And excellence is really important in that it's not a charity, but it's a partnership. And work done, therefore, at ICTP has contributed to many breakthroughs. So now the question is, how do we view this wonderful infrastructure that we have and the mission of ICTP in the next century? In fact, when I took up the directorship 5 years ago, I asked myself this question. Because the frontiers of science are, and also the geopolitics is radically different now, including in quantum science. We are no longer looking for the Higgs boson. Also the notion of what is a developing country and a global south, I mean, these words are no longer, it's almost becoming problematic to use these terms. So what is the mission of ICTP? What is the vision for ICTP in the next years? And after some introspection, I'm convinced that ICTP is even more relevant today. It's a unique organization, one of a kind, for doing frontier science in the quantum is, of course, the main component of it, to reach out to a global community. And the role of fundamental science, both for its intrinsic value and as a powerful agent for social development, should be re-emphasized in what we imagine as ICTP 2.0, the ICTP for the future. But we have to remember that, things have really changed. So Salam, for example, himself was not very optimistic in the 80s that he would be able to create another ICTP. Because what the policymakers want, I mean, nuclear energy and particle physics was very close in the past, but that's not the case anymore. So based on this, we have identified in our new strategic plan 3 main priorities, and I will just very briefly mention. One is an international consortium for scientific computing, which is to accept that, understand that computing is going to become a very fundamental part of science. And that, of course, includes AI and machine learning, which depends on the old quantum, but also quantum computing and quantum information, which is going to come. In that, we have partners like IBM and Chineka and national centers in South Africa, JESDA, SECAM in Switzerland. So that is our approach towards creating a consortium for computing so that these quantum tools become globally available. And we want to do it through an international science alliance. So this is, again, a bit different from how Salam was envisioning it. Now we are really looking for equal partnerships. I mean, it's really not, it's kind of doesn't make sense to think about India and China and Brazil in the same way as we used to do in the past. And in that respect, ICTP has already signed some very nice agreements with South Africa, Brazil. We are working on India and China. We have a very nice agreement with IBM, which we will talk about later in the day. And the final thing is to make the ICTP core strong. I mean, we look at ourselves as a kind of a lighthouse for global science, but then the lighthouse has to really have a shining bright light. And to make that happen, we really need to emphasize the core strengths in fundamental science at ICTP, keep true to our core competencies, strengthen our resources and physical infrastructure. And we are relying on that, on the scientific community at large, but also on foundations and countries and corporations. And in this respect, I just want to add, I'm very happy that Professor Spergel is here as the president of Simons Foundation. They have been a long partner for the last 10 years, but they recently gave us a 15 million grant for the Adriatico, for a science complex. And I would like to actually acknowledge the Fondazione Compagnia di San Paolo, President Marco Gilli and Secretary General are present here. They will be our partners in this respect. So maybe I can give you, maybe you want to say, let them say a minute, you want to make a statement in this collaboration. So this is an example of an international cooperation between an international foundation and an Italian foundation and ICTP, a UN organization, to make resources available for all the 4,000 scientists who come to ICTP for a wonderful world-class facility in the Adriatico.
Yeah. Well,
thank you for your kind words, and thank you also for the invitation. You know, in a previous life, I was a researcher in electrical engineering, so it was very, very nice for me to attend this conference, and very inspiring as well. But now, well, I am here as a representative of the Compagnia di San Paolo, which is probably the oldest foundation in Italy. It was founded, you know, in 1563, you know, and we are very much aligned, you know, with the UN goals and the UN agenda. Our main goals are people and prosperity, planet, and culture. And, you know, our main goal, of course, is to reduce inequalities, is to contrast poverty, but we have been done it since the beginning by promoting the growth of the country, the growth of the territory. That's why, you know, we invest a lot in science, technology, and in education. Through many tools, of course, some philanthropic grants, but also some innovative financial tools. Especially we invest a lot in capacity building and in special projects involving universities of our territory, of course, but also of the country, including and especially focusing on young researchers, young talented people. And we have many special projects with a kind of international perspective. Some of them were already mentioned. We are part, of course, of GESDA, the Geneva Science and Diplomacy Anticipation, and also we participate in the Open Quantum Institute that was already mentioned before. We also participate in the UN Scientific Advisory Board to the Secretary General, and of course, we are very, very pleased that now we have a special project in connection with the Simons Foundation and with ICTP. You know, we are very pleased because ICTP is, for this area, for this country, for the world, you know, a crucial hub for scientific cooperation, for international cooperation, for excellence, as it was mentioned. And so it's a pleasure to be involved in this project, which is just to try to secure the building, the Adriatico building, in partnership with the Simon Foundation, to transform the building, to renovate the building in such a way that it will become a kind of infrastructure, really a crucial infrastructure for science and for international cooperation. And of course, also, we are very, very pleased that it's also for us the beginning of a long-term partnership with ICTP and with the Simon Foundation. So thank you very much.
Okay, thank you. Yeah, so I would like to also, I will just take 1 minute that I would also like to acknowledge we have representatives from the Kuwait Foundation, Professor Khalid Asad Alfanzi, who have been very long partners with ICTP. Once again, an example of international cooperation for science. Alessandro Curioni with IBM and with Matthias Treuer in Open Quantum Institute, we have close collaboration. So let me just close by saying that one more thing that we should really bear in mind is that the quantum century might actually come to a halt in the middle. I mean, there are global problems that we need to address, which require a global response. Climate challenge is only one of them. And this is really an unprecedented time in the history of humanity that we have this kind of amazing control over the quantum, but we are not able to solve some of our difficult political problems. And I think international cooperation is going to be very fundamental. Keeping the channels of dialogues is going to be important. It will be, of course, naive or even a bit arrogant to say that science diplomacy is going to solve difficult political problems. But we have seen that, for example, Sesame is an example where ICTP did play a role, that it is possible to have dialogue and cooperation even in difficult times. And I do believe that organizations like ICTP have a very critical role to play. And considering the promise of the quantum and the importance of the quantum, I think this is where I see the role of ICTP.
Thank you. So, David Spergel, we are talking about the global responses and the science diplomacy. I think that when we think about the science in Europe and in the US, we are thinking about a very difficult moment. And I know that you are particularly careful and attentive about this fundamental issue of keeping this bridge between the two continents and the two coasts of the Atlantic?
So I think what has been and will be essential for the ongoing advance of science is that the conversations we have. This is actually one of my metrics when I think about things we support as a foundation, is what conversations happen because of things we support. And we do this in a number of different ways. One is a global conversation we support through the support of the archive. Another, the conversations we support through our collaborations that we support that span fields. And a key part is our support of institutions like ICTP, right? And, you know, I really like Atish's metaphor of a lighthouse. We often refer to institutes as jewels. Jewels are something you stare out and are pretty. Lighthouses light up the world around them. And with the investment that we're making together in the Adriatico, I think of it actually as, you know, we are assuring the structure on which that lighthouse sits. Because that, you know, all of us who've been here over the time know how important it is. And securing and establishing and modernizing it for the coming years is going to enable those conversations. And having these conversations, I think this is, you know, particularly as an American in the midst of the moments we're going through right now, where, like in many ways, other places with the rise of ultranationalism, and these ultranationalists want to limit conversation. They want us talking only among our own country. I think it is very important that we continue to make efforts to maintain and sustain international collaboration. And I actually want to make an appeal to my European colleagues to do two things at this moment. One is to make every effort, as we're trying to do as a foundation, to increase opportunities for young people. I think this focus on luring senior people to Europe is putting money in the wrong place. We need to make sure that we do not lose outstanding junior scientists because of lack of opportunity, and that's when we need to put their resources. And then let me appeal to you to continue your foreign travel and continue to visit the United States. There's been, you know, unfortunate incidents, though I think they have more to do in a particular well-published case about data that shouldn't have been on the computer. But I think one has to make the effort to keep coming. I know people canceling visits to the United States for conferences this summer. I'm going to Ukraine this summer for my second trip to lecture in a summer school. There are times where you need to show a little bravery to keep the conversation going, and that's something that I think I want to really appeal to everyone here as something you can do as individuals, is go to those summer conferences. So let me stop there.
Thank you. So Alessandro Curioni, we are going on with this fundamental issue of international collaboration, but we know that there are many different aspects and nuances when we talk about collaboration. We know that science is different from technology, for example, and all these issues intertwine with governments, with geopolitical equilibrium. So it's a very complex scenario that we have to face, right?
Yeah, indeed, very, very complex, and I should not be the one to say it we see every day. But let me spend a couple of words. We are here for this International Year of Quantum Mechanics, and the past 100 years, we have to be very, very, very clear. Quantum mechanics has really been the base of most of the transformational technologies that we created this century, starting from IT, okay? And our world in business, as a society, and in science, without quantum and without the technology that has been enabled by quantum, will not exist. It will be a completely different one. Everything, all the sciences, right? So now we are really at the age to do an additional steps. It's not, quantum mechanics that help to understand and design instruments. It's really to using quantum mechanics for computing and to, let's say, work on information and knowledge. Yeah, creating a new representation, a real new representation that allow us to do things in a different way, maybe better, maybe less complex, maybe faster, but in a different way. And every time we have an instrument that allow us to do things in a different way, the impact in all the fields, again, business, society, and science, is all to be discovered. So that is why collaboration is especially important now. There is a full world of theories, algorithms, applications, additional technology that needs to be done and developed now if we want really to bring the promises and sometimes the hype that is around to become reality, okay? So collaboration is super important. So now go back to what I was telling you, were telling me at the beginning, science and technology. Look, one thing that we need to defend at all levels is collaboration in science. Science doesn't have border. Science is universal, and science needs to be one. Okay? So without collaboration across the world, science doesn't exist. It becomes something that very, 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 very sterile, right? On the other hand, so collaboration is part of the DNA of science. Yeah, it's not something that without that, science doesn't exist. Without that, you don't have a peer review system. Without that, you cannot understand what is right, what is wrong. Then move on to technology. You can say technology is about competition, and competition and collaborations, sometimes they don't go very, very well together. I would say yes and no. And by the way, also in science, you have collaboration and competition. But in the technology, collaboration is a must, even if we don't want, even if we want to compete. In technology today, there is not a single company, organization, country, system that is able, for example, to control or to create information technology alone. The US, without MSL in Netherlands, cannot design the computers. The US and the Netherlands and Europe, without having TSMC in China, in Taiwan, we don't have the scale. And that is across all the things. So in one case for a vision, for a DNA, and in other say for a must, collaboration is essential.
Okay. So, Robert Dijkgraaf, collaboration is a must, and we know that collaboration is very important to build bridges also between, let's say, the rich world and what we call the developing countries. And one of the issues is the basic research that probably is the first glue that can unite the planet and the different experiences of countries and the regions of the world. What do you think?
Yeah, so it's kind of paradoxical time, because I think this meeting shows how tremendous the opportunities for science are. But if you look in society and politics, we see, I think, both basic...
I think this would be good for everyone. And also it is important to... I really hate this idea that no one understands quantum. I think since 100 years we have shown that we can understand things, we can do things, we can control really the very, very small things. So I think it's important to communicate to the public a kind of reasonable view about science, quantum science. So thank you.
Thank you. So I would say that as final remarks, I would start from this point of communicating with the public opinions and try to, to balance the hype and not to be utopian or dystopian, but to find the right balance. And so if we want to think about the close future, I would like to know from each of you if you have, let's say, a dream, a target, something that you would like to see with quantum mechanics and quantum sciences and computing that can become, a sort of daily reality for each of us, as it was said in a talk before, that can, I would say, benefit humankind and help us to go through these quite difficult times. So, Atish.
Yeah, I think I would sort of echo what Giorgio said, that it is hazardous to make predictions, especially about the future. It's clear that we have reached incredible levels of sophistication in our experimental tools like lasers, or also theoretical tools like quantum field theory. So it's evident that what is past is prologue. I think there's clearly more to come. It's going to be exciting. But I would not, rather than making some specific prediction, which I think is really never usually works, I just want to make two general points. One is, of course, the quantum promise, which is really going to be important. It's an amazing power that we have over understanding nature. But I think, it's so, science is power, but I think one should guard against extreme concentration of power, which is the direction in which we seem to be going more and more as the quantum is taking off. And I think institutions like ICTP can play a role, and we together, I think, as scientific community. And the second issue is about, it was referred to also by Anne and also yesterday by Sir Jahosh, that about trust in science, which has to do with communicating science in an appropriate way, re-emphasizing the scientific method, the values of enlightenment, let's say, which underline it, the facts about objective truth, but with a kind of emphasis on confidence level, because for a common public, it's really hard to understand that black hole mergers are emitting gravitational waves, and I don't know, red wine is good for your health. Both of them seem to be almost on the same level of understanding, and that we need to communicate. So I think I agree that we should avoid this quantum hype and quantum scare, which can, in fact, create barriers because then the governments think that national security concerns are around the corner. So I think these are the two comments I would make from the point of view of an institution like ICTP.
Thank you. David Spergel.
We've been talking about applied and basic research. I'd actually like to distinguish between targeted and curiosity. Targeted when you want your pilot to fly you to Frankfurt. Study things like the microwave background, which I've been involved in. You want to launch an experiment and get it to work. You have to be very targeted. Another form of research that I think we all understand is valuable, but we need to communicate. That's curiosity research. Listening to some of the talks, and there's very much, I think, that one of the underlying themes in Duncan's talk this morning, that people went to look for one thing, discovered some wave function, discovered something that was valuable for something they hadn't thought about. Right? And I think all of us have had this experience in our research of being curious. Sorry about that. Fortunately, I'm pretty loud. Of being just finding things and pursuing other directions. And I think this is something we need to, articulate. Now I'm saying this as a funder, but more broadly to the funding community, that in order for research to advance, in order to have really great discoveries, curiosity-driven work is going to be important. And if I'm going to make one prediction about the upcoming advances in quantum computing, is while it will be driven towards solving certain problems, along the way, as we go to do that, we will discover things that surprise us. And exploring with curiosity things we discover along the way may lead to things and that will be even more valuable than what we imagined.
Thank you. Alessandro Curioni?
Maybe something that is very, very selfish, but I think that applies for a lot of the people that are here. I would like, in the next decade to eliminate the frustration that I had for 30 years as a computational scientist that needed, to translate the theory to equation, to algorithms, to try to solve real problems that benefit the society. And I failed trillions of times, most of the time, exactly because, we didn't have the right computational instruments that eventually, as I was telling you before, with this new representation and joining classical quantum representation with AI, as we have said, make that real, so that what, I was dreaming for 30 years become a reality.
Okay. Robert Dijkgraaf?
Well, perhaps in a short words, I hope quantum makes the world more entangled with each other. But literally, I feel quantum is a very specific, in a very privileged position to make sure that in our whole community, the whole is more than the sum of the parts. And that means that we have to work together, but also in an atmosphere of trust where I hope we'll see many centers. They will not all do the same. I think it's very important to believe in the principle of distribution of labor. So I hope that each of the institutions will feel that they can have their own character and they can work together. And coming to your remark about trust and science, I think there's a lot of research being done on it. And one of the amazing results is that people trust science not so much because they understand it, because what they see is something very difficult being done by a large community that actually agrees on those results. And I think, the quantum community can be a perfect example to show the world that, these very difficult things can be solved.
Yeah. So, Andrew,
yeah, is it working? Yes, okay. You were talking about dreams. I think I have one dream, which is we should save our planet. And hopefully quantum will help at least many, at least the beginning of the quantum, I would like to say. So hopefully, but I think it's our responsibility as scientists to also say this mission, that this is really important. At the moment, the politicians are forgetting this issue, but we have this responsibility. Second dream, stop the wars. I don't know how we can help, but I think, yes, we can help by showing that we can talk to each other and we disagree with having walls between ourselves. And yeah, I don't know. Yes, that's my dream.
So I really want to thank you all for these different messages. Anyway, there was like a fil rouge, I think, of trust, of optimism. And so let's really hope that we can live and enter a new era of a more entangled world, as you said. Thank you very much. Thank you.
Start this session. It was a short lunch break, so people are getting in, but I hope you can take your seats. And just before the session, we have a short announcement by Yasser Omar about this year of quantum. Please, Yasser.
Thank you very much for the opportunity. I think you can put the slide, please. So I just wanted to share with you this initiative in the context of the International Year of Quantum Science and Technology. We would like to have at least one event dedicated to quantum in every single country of the world. So this is a crazy initiative, but not impossible. And the reason for this intervention is to invite you, since there's such a diverse audience in terms of nationalities, to invite you to join this initiative. We have plans of how to implement this crazy project. So I'm around all day, or just contact us through this website. If your country is already there, so there's also the project for quantum cities, so you can also do that. It doesn't work. Okay, doesn't matter. Okay, I don't want to take more time. So thank you very much for the opportunity.
Thank you, Yasser, for this nice initiative. So let us start the afternoon session. We will move to organic chemistry. We have the special pleasure to welcome now Maurizio Prato, who is from Trieste, and who will be telling us about empowering clean fuel production with artificial quantasomes. Here's Maurizio.
Thank you very much, Mark, for the kind introduction. First of all, I want to thank the organizers for inviting me to this very interesting workshop. And this is my contribution to the quantum topic we are discussing these days. And in particular, I want to focus now on a phenomenon which is very important in our lives. The natural photosynthesis is the phenomenon that makes our planet livable. And we should always think that if photosynthesis finishes on Earth because we destroy all the plants and forests, then we have to find another planet to live. So in practice, what happens in the photosynthesis is that the carbon dioxide and water are transformed through the help of light into oxygen and sugars. And this is a very important phenomenon because it generates oxygen, which is vital for us. And there is a very wide research field which is called artificial photosynthesis, where people try to imitate nature in their phenomena. And in particular, the first step is similar to what happens in nature. Water is oxidized to oxygen and produces 4 protons and 4 electrons. And then these 4 protons and 4 electrons can be used, for instance, to reduce the protons to hydrogen. And so in this way, we would produce a phenomenon, a process which is called splitting of water into hydrogen and oxygen. Or the 4 protons and 4 electrons can be used to reduce carbon dioxide to useful chemicals, including methane, for instance. So this is a series of processes which have an enormous importance. And in particular, we will focus today on the splitting of water to produce hydrogen in principle, hydrogen can be considered a clean fuel, especially for hydrogen fuel cells. And so if we split water into oxygen and hydrogen, then hydrogen and oxygen can be recombined to produce water. And so the circle is very virtuous because we don't have any pollution. And so, for instance, BMW promises to produce hydrogen engines, but the main problem is that hydrogen today is produced in a very polluting way because it's produced through the steam reforming process, which consists in a very high temperature process and uses methane as a starting material. And so, and of course, it produces carbon dioxide. The prototype has already been made, and of course, hydrogen cannot be considered the only fuel useful for this type of mobilities, but according to the CEO of BMW, is one of the possibilities that we have today for improving the situation of zero-emission mobility. And so if we analyze the splitting of water in terms of reactions, we see that we have two half reactions. One is the oxidation of water to oxygen, and the other one is the reduction of protons to hydrogen. Of the two processes, the oxidation of water to oxygen is very much more difficult because it has a very high, needs very high energies. And so, of course, the most straightforward way of doing the splitting of water would be the water electrolysis, in which we apply voltage and we reduce water to hydrogen on one side and oxygen on the other side. But let's say the cost of energies in using these batteries is not compensated by the production of hydrogen. So it is much more expensive. It's much more expensive way. So one way of improving the electrolysis would be to use catalysts. And for some time, we have collaborated with Professor Paolo Fornasiero in Trieste by using carbon nanoforms on which we adsorb the catalyst, in this case, palladium on titanium oxides. Or we can also collaborate with Professor Marcella Bonchi in Padova for the oxidation side. So the two parts of the electrolysis can be improved by using different catalysts, but what we want to do is to make use of light. And as a matter of fact, the process will be called photoelectrochemical splitting of water. And the first example was dated in 1972 when Fujishima and Honda found out that by doping the electrode with titanium oxide, they could facilitate the process by using light. And of course, one possibility is to use solar panels to help the electrolysis, and in this way, we would use the solar power to oxidize water and reduce water. One of the most important achievements in the area is by the group of Nocera at Harvard, and he was able to connect the solar cells together with the electrodes, either wired or wireless, in order to produce a device that produces splitting of water. In this case, of course, they had to use a triple junction silicon solar cell to have enough power to power the process. So now, what we want to do, you remember, we want to do artificial photosynthesis. So we want to imitate nature, and if we look at the processes occurring in leaves, we see that in leaves we have two different systems, photosystem 2 and photosystem 1. And they have different properties and duties. And the first event that occurs when a photon reaches the leaves is the oxidation of water to oxygen. And then the 4 protons and electrons can travel to the photosystem 1 in order to produce the sugars. And in the oxidation of water to oxygen, one relevant role is expressed by the catalyst, which is formed by 4 manganese atoms and 1 calcium atom. And in this process, we have the so-called Koch-Joliot cycle, in which the 4 manganese atoms, the catalyst should receive 4 quanta of light, so 4 photons, in order to reach the state 4, in which then water is oxidized to oxygen. So the photosynthesis, the nature of photosynthesis is quantized in the sense that it needs 4 photons in order to activate the catalyst and produce oxygen. So if we look at more into detail into the photosystem 2, we see that the photosystem is formed by a series of antenna compounds, which are usually the chlorophylls, and one center, which is called reaction center. So in practice, what happens is that these chlorophylls and carotenoids, they take the light, and there is a series of electron transfer reactions for taking the electrons into the reaction center. And then the reactions occur here. In some cases, it was also detected, this type of structure, in which we have the series of chromophores, the antennae are around the reaction center. So in this way, in practice, all the light will be captured by this antennae and converted into chemical energy in the reaction center. And so this can be called the quantasome, which is a structure that identifies the minimal photosynthetic unit responsible for the quantum solar energy conversion. And it goes beyond a simple photocatalytic diode in the sense that now we have the light harvesting components together with a specific spatial organization according to the catalyst requirements. And so in practice, we wanted to imitate nature in the sense that we wanted to create an artificial quantasome. And so in order to make this type of structure, we need one catalyst and the antenna that will be around the catalyst. And so as the catalyst, we decided to use this so-called ruthenium polyoxometallate. And here you can see the structure. And in practice, this was prepared in the laboratory of Professor Marcella Bonchio in Padova. And this is a polyoxometallate in the sense that it contains many oxygen bridges with 10 tungsten atoms and 4 ruthenium atoms. And there's a negative charge of 10. And so in practice, the core of the complex is formed by these 4 ruthenium atoms, which are the active atoms in terms of catalysis. In practice, this is the core where we have the 4 ruthenium atoms, and this resembles very much the natural catalyst, which is formed by 4 manganese atoms. And what happens is that according to the same principle, we need to have 4 photons to activate the 4 ruthenium atoms in order to have oxidation of water to oxygen. And we can follow the the evolution of oxygen. And this process is formed with 500 turnover numbers and very high turnover frequencies comparable to what nature does. We can also use electrochemistry to generate oxygen. But now that we have the catalyst, which will be the center, the reaction center, we need to have the right antenna. And the antenna should, first of all, absorb light, so it should be a light absorber. And then it should be a strong oxidant because we want to oxidize the catalyst. And so we decided to use this type of compounds, which are called perilimbisimides, because they have a wide absorption range, they are fluorescent, their HOMO-LUMO energies can be modulated, and they are very strong oxidants in the excited state. And so why we chose this type of compounds? Because these compounds, as you can see here, this is the visible absorption spectrum, and by changing the structure of these compounds, we can cover the entire visible region in order to capture the entire types of photons. And so, and here is the photocatalytic system that we want to use. So the catalyst has 10 negative charges. So we needed a positively charged photosensitizer in order to have electrostatic attraction. And as you can see, the ratio between this and this is 5. So we will probably need 5 photosensitizers for one catalyst. And so this is what we want to achieve. We have this photosensitizer which absorbs light very efficiently in the visible region, and then once excited, it will oxidize the ruthenium atoms. With 4 photons, we will have 4 electron transfers, and we will have the 4 ruthenium atoms which become active, and in this way, we can oxidize water to oxygen. And so this type of compounds are peculiar and because they have a very intense, as you can see here, absorption spectrum and also a strong fluorescence. But they have an aromatic core that makes them aggregate. So if we, for instance, increase the concentration, we have that this band decreases, and so the monomeric species decreases in order to generate the aggregated species. So in practice, the aromatic cores will aggregate in this way in order to optimize their interactions. And so in practice, we can distinguish by using visible absorption spectroscopy, we can see the difference between the aggregated species and the monomeric species. And so when we used our chromophore here in water solution, we see that we have aggregation based on the absorption spectrum. And when we place the catalyst, don't forget that we have positive charges here and negative charges here. So in practice, there is an electrostatic interaction. And so when we place the catalyst, we can see changes in the absorption spectrum, which means that we are changing the conformation, the configuration of the chromophore. And you can see here that we have a ratio of 0.2, which means 1 to 5 in terms of ratio between the two components. And here again, you can see that we have 0.2, which means that the optimal ratio between the catalyst and the chromophore is 1 to 5. And so this is the type of structure that we expect 5 perilimbisimides around the catalyst. And in addition to this, we expect to have pi-pi interactions at level of aromatic systems. How do we know that this is the structure? Well, we ran Sachs X-ray experiments, small angle X-ray scattering together with Heinz Hamenisch at Elettra-Synchrotron in Trieste. And what we see is that by looking at this slope, we can understand that we have a 2D lamellar superstructure. And also we have these peaks that are the distances, horizontal distance and vertical distance between the heavy atoms. So we know that we have a structure with this type of characteristic, and there is aggregation between the aromatic system, but also there is a distance of 2.3 between the layers. So in practice, we have a 2D hierarchical structure assembly. And what we believe is that we have the catalyst, which is surrounded by 5 chromophores in order to reach neutrality. And then this is more and more aggregated in order to form these structures. And eventually, we have a structure of nanometer length with this interlayer distance of 2.3 nanometers. And what is impressive is that we have a structure which is identical to the natural chloroplast membrane, which is found in the leaves. And so what is the confirmation that we have in terms of electron microscopy? Then you can see here, by using high-resolution electron microscopy, we can see that we have the layers that we were postulating. And also we can see the single catalysts. The heavy atoms have a very strong contrast in electron microscopy. And so we can see the single catalysts, even though, of course, we don't see. But we can see the arrangement, the spatial arrangement of this system. And so now we have our quantasome, which is prepared and is suspended in water. And so we are ready for the experiment. And we can see that, as a matter of fact, when we irradiate the solution, we have evolution of oxygen. And the evolution of oxygen has a plateau when the ratio between the two components is 1 to 5, as we expected. And also, we could deposit the quantasome onto an electrode. In this case, we used a nanostructured tungsten oxide. And in this case, we have an absorption photon-to-current efficiency of 1.3%. So in practice, what we have achieved is an electrode which works with, of course, this is in absolute, this is very low value, but it compares efficiently with the other systems which are state-of-the-art. Even the photosystem 2 deposited on the electrode is not as efficient as our system. And so in practice, we can also detect, in collaboration with Margherita Mariuri and Giulio Cerullo at Politecnico di Milano, they carried out experiments of fast spectroscopy. And what they found is that when the system is irradiated, we have a symmetry breaking. So there is a charge separation of the different chromophores. And then there is a fast charge separation generating positive charge in the catalyst and negative charges in the chromophores. And then there is a migration out of plane or in plane. And eventually, the recombination is higher than 1 nanosecond. So we have an improvement of 3 orders of magnitude in the charge separation with respect to the charge recombination. So the system seems to be working very efficiently. And so we can say that we have generated the artificial quantasome, which works very efficiently and promises to be a good possibility for oxidizing water to oxygen. And so what can we do to improve the quantasome in the future? We can, well, first of all, we want to improve water solubility because we have problems in solubilizing the species. We want to improve especially water accessibility and transport. As a matter of fact, we need water to penetrate in the system and reach the catalyst, and so we have to improve the accessibility of water into this system. Then we want to improve light harvesting in the sense that we want to broaden the absorption spectrum of the quantasome in order to reach the entire visible region, and this can be generated, this can be produced by using different chromophores with different absorption spectra in the visible region. So this is the work that we are carrying out now. This is the evolution of the original quantasome to improve the properties of the quantasome. This is my group in San Sebastian, where I'm currently working. As you can see, a number of talented students and postdocs. And this is the funding that we had. And I have to thank especially Marcella Bonchio in Padova for performing with us all the work on water splitting, Carlo Bignozzi and this group in Ferrara for the device, and Heinz Samenisch in Trieste synchrotron for the Sachs measurements. And I wish to thank you for your kind attention.
Thank you very much, Maurizio. Maybe I have just a first question. You mentioned that in your system you need to absorb, for the reaction, you need to absorb 4 photons, which is also the case for the photosynthesis in nature. Is it possible to imagine that one could do it with less number of photons absorbed? Are there classes of molecules that would be candidates for that?
The thing of the number 4 is due to the fact that in order for the catalyst to work, you need to oxidize the 4 ruthenium atoms, and so you need 4 electrons from this system. And so in our case, the aromatic compound will extract electrons. So each photon needs to extract one electron from the catalyst. Only when the 4 ruthenium atoms are all oxidized, the oxidation of water will occur.
But would there be catalysts with 3?
In principle, yes. In principle, yes. There could be different catalysts, but then you have to change the geometries. And as a matter of fact, this is a very stable catalyst, and so this is why we decided to choose this one. But in principle, yes, you are right.
Okay. Questions from the audience? Giorgio?
Do you have any idea of when this can be used industrially? On a large scale,
Yes, as a matter of fact, we are collaborating with a small industry that plans to apply this system for commercial reasons. But for the moment, the system needs to be, as you have seen, we are still improving the system. In principle, it can already be used, but the catalyst contains ruthenium atoms, which are kind of expensive. So another line of research tries to change the atoms involved with less expensive atoms like cobalt, for instance.
5 years, 10 years to have a mature system?
I would say maybe 3 years, yes.
Thank you for the nice presentation. I have a question and more another curiosity, let's say. So regarding the slide where there was like the absorption panorama with all of the different substituents to the organic ligand or is it on the same ruthenium center different organic substituent, or are all the same and are used in combination? Because that to me is not super clear.
Thank you. You are talking about this, right?
Yeah.
I mean, this.
Yeah. The sense is clear. But.
Yeah, I mean, depending on the substituents on these aromatic rings, we will have absorption in the different regions. Sure. So one idea is to use different chromophores with the same catalyst in order to cover the different regions.
In the same device?
In the same device, exactly,
okay,
yes.
Okay.
In fact, one problem could be maybe exchange of ligands, but this is a problem.
Are there some evidences that the self-assembly or the final assemblement hold when you have different substitutions?
We haven't done yet what we call the panchromatic quantasome. We have used all the chromophores separately, but we haven't combined them. Yeah. What we see from the experiments is that once it is formed, this complex is stable. Mm-hmm. So they should not be able to exchange ligands. But we haven't done yet the experiment, yes.
Okay, and one very quick curiosity. I saw like a byproduct when it ruins, when you have only ligand. Is it there a chance that it seems chiral or not? There is a slide where you have... Is it chiral or not? Because I study cis effect and...
Yeah. This is, I mean, for us, this is very interesting thing. And what we did, which I didn't show, if we place chiral ligands on the aromatic core, we get chiral helices. Mm. So let's say, well, it's at the beginning. This one.
Yes.
So this is the type of structure. This is the conformation because we have positive charges here. So the system tries to optimize the much distance between the positive charges. So if we place chiral ligands there, then this helix, it becomes chiral. And as a matter of fact, we see active circular dichroism with opposite sign depending on the chirality of the complex. We performed we were trying to understand if we have cis in this case, and so we performed let's say, current, the oxidation of water with these chiral complexes. And what we found is that in some cases we have an enhancement, but it is not clear yet if it's due to a better structuring of the complex or it's due to cis. In principle, we wanted to study this with Roberta Sessoli, but we see.
Maybe one last question.
Yes. Maurizio, very, very quick question. Do you have an idea of the comparison of the efficiency of the conversion of your process with respect to do solar photovoltaic, then electrolysis to oxygen? So if you compare one with respect to the other.
In principle, the solar panel electrolysis is more efficient because in that case, the efficiency is around, I think it's about 20%. Yes. It's a different system, of course, and it needs silicon solar panels, and so with all the problems, yes.
Another last question.
Richard, another route I heard to have hydrogen is to produce ammonia via the Haber-Bosch and then ship ammonia to somewhere and then decompose it away. Which way would you regard to be more efficient or more hopeful for the future? I heard this from Parina.
Hydrogen is used for fuel cells, and this is let's say, the idea that the BMW is exploring for making the hydrogen cars. And so, but of course, this needs to have a tank of hydrogen. And of course, you need a tank which has properties that guarantee. So another way would be ammonia. Another way would be formic acid, because formic acid also decomposes into hydrogen and carbon dioxide. So these are alternatives that could be explored for the use of hydrogen. To ship hydrogen, of course, it's much easier for a liquid like formic acid rather than pure hydrogen, yes.
Okay, the last of the last questions.
Maybe a naive question. Can you make a comparison between the efficiency of your process and the process that occurs in the plants?
That occur?
Yeah, that occurs in the leaves of plants.
The efficiency of the leaves is very low. So we are more or less in the same range. So the capture of photons is very efficient, but then there is a main problem with the leaves, which is that the photosystem is made of proteins, and the proteins are not stable under the strong oxidizing conditions of nascent oxygen. And so in practice, every half an hour, the leaves have to stop their activity and rebuild the protein. So they have a self-healing ability, but it's very slow. So one way that botanists are trying to understand is whether the photosynthesis can be improved based on an improvement. And of course, this would be a genetic modification that the system becomes stronger and then less labile and more efficient.
Thank you very much. Okay, now we'll change field and move to particle physics, and we have the pleasure to welcome Silvia Pascoli from the University of Bologna, and she will be talking about neutrino oscillations from quantum mechanics to physics beyond the standard model.
Thank you. Thank you very much. Thank you very much. So I'm going to talk about particle physics, and in particular an application of quantum mechanics to neutrinos. That is the phenomenon of neutrino oscillations, and it plays really a crucial role in our understanding of particles and interactions, because as I will show you towards the end of my talk, this is the only particle physics evidence we have at present that the standard model of particles and interactions is indeed incomplete. And I will briefly discuss how we can extend it and what neutrinos can tell us about the new physics beyond the standard model. So neutrinos are fascinating particles. They are the most elusive of all the standard model fermions. We still need to understand many of their properties, last but not least their nature, and this is related to the fundamental symmetries of nature. I will have no time to discuss that in great depth, but neutrinos carry lepton number, and if they are Majorana particles, then lepton number is broken. It's a broken symmetry in nature with consequences, for example, for the generation of the baryon asymmetry of the universe. Importantly, they are the most abundance of fermions in the universe, at least known fermions in the universe, and as you can imagine, then they play a key role in various stages in the evolution of the universe to the one we observe today. So let's start by inscribing neutrinos in the Standard Model. As you know, this is a theory which is based on the gauge group SU3 cross SU2 left cross U1 of hypercharge, and this symmetry is broken by the Higgs scalar, which acquires a vacuum expectation value around 100 GeV. So this is the electroweak scale, and this sets the scale of the masses of the gauge bosons associated to the SU2 left and U1 hypercharge, as well as the masses of the fermions, except possibly for the neutrinos. I'll come to that later. Also, in this sense, neutrinos are special and can give us really new insight into this problem. The other key element of the Standard Model is its particle content. So, of course, we have the gauge bosons associated to the gauge group, the massless gluons and photons, and the Z boson and the W boson. I will focus mainly on these when I discuss neutrinos, because neutrinos feel the weak force, and therefore they couple to these gauge bosons. And then we have the Higgs that breaks the symmetry SU2 cross U1, and then we have the fermions, which come in two types, quarks and leptons, and even in 3 generations, so 3 replicas of exactly the same quantum numbers. In particular, in the lepton sector, we have the electrons, the muons, and the taus. Neutrinos are associated to these charged leptons. They belong to the same doublet, so they interact together with the W boson, for instance, and this is the way we define the flavor of the neutrino. So an electroneutrino is a neutrino which is associated to the electron, and so for the muon neutrino and the tau neutrino. This is an important concept that I will use when discussing neutrino oscillations. So as I said, neutrinos come in an SU2 doublet with the charged leptons, and because of that, they couple to the W and the Z as described here. These are the terms in the Lagrangian which describe the interaction, for instance, between charged leptons and neutrinos. So when you have a W, decay, virtual or real, then we'll produce, for instance, an electron and the corresponding neutrino, in this case antineutrino, an electron antineutrino. The same for the muon and the tau. They carry lepton number. Lepton number is a U1 symmetry under which charged leptons and neutrinos acquire a phase, the same phase. And this, as I said, is an accidental symmetry of the Standard Model, so is respected by the Lagrangian, but actually we don't know if it is a fundamental symmetry or not, and in this neutrinos can give us very important information. If they are Majorana particles, then lepton number would be a broken symmetry of nature. So, because of the interactions that I showed you, these are the only interactions that neutrino have, at least in the Standard Model, and this means that they interact very, very weakly with matter. In fact, if we go and estimate the cross-section, here. This is an estimate of a cross-section for a GeV scale neutrino. Is it tiny? In fact, if we go and look at the mean free path of the neutrino of GeV energy in a matter of typical density, for example, water, 1 gram per centimeter cube, this would be in the kind of range of distance of light years. So essentially, neutrinos can go through matter, us, the Earth, the Sun, nearly unimpeded. So neutrinos, the history of neutrinos goes back to the 1930, when Pauli proposes the solution to the missing energy in beta decays, proposes the fact that there might be a particle which is neutral and is emitted in beta decays. We cannot detect it, but carry away the energy available in the process that is not taken by electrons and positrons. This was a puzzle in the 30s, and in fact, neutrinos were discovered in 1956 by the experiment by Cohen and Rain. At that point, it was already understood that wherever you have lots of weak interactions, you will have lots of neutrinos. And this is the case, for instance, in stars. The sun produces huge amounts of electron neutrinos. And so there were experiments starting from the Homestake experiment that you see here that tried to detect them. What they were consistently finding is that the flux of neutrinos we observe is much lower than the flux that you predict. So And for a long time, it was unclear if this was a problem of theoretical predictions or really a physical effect. The other kind of piece of information came from atmospheric neutrinos. When a high-energy cosmic ray hits a nucleus in the atmosphere, then this produces lots of pions and kaons, and pions decay into neutrinos and muons, and subsequently the muons in muon neutrinos and electron neutrinos. So you expect a significant flux of, in particular, muon neutrinos as well as electron neutrinos from the atmosphere. And what you can do, you can measure the ones which come from above, that have traveled only few kilometers, from the ones which come from the other side of the Earth, because as I already said, neutrinos can travel through the Earth without being stopped. This was done. In fact, I'll show you the results of that in a minute. Neutrino comes also from other astrophysical environments, for instance, supernovae. And by studying these astrophysical neutrinos, Davis and Koshiba got the Nobel Prize in 2002 for these results. But the key point, for me, the defining point in the history of neutrino physics is 1998 and 2002, when we discovered that neutrinos oscillate. This comes first of all with the results of atmospheric neutrinos, where we see really, as I will show you, this dependence of the flux of neutrinos from where they come from the atmosphere, and by the Super-Kamiokande detector. And similarly, in the solar neutrino sector, we also have observed neutrino oscillations, and this was confirmed in 2002 by the SNO detector, and Kajita-san and Art McDonald received the Nobel Prize in Physics in 2015 for the discovery of neutrino oscillations. And what is important is that in the Nobel Prize nomination, it explicitly says that this implies that neutrinos have masses, and this is really the key information from a particle physics point of view. So, but let's look at neutrinos, neutrino oscillations in particular. This is a change of one flavor to the other. You can start with muon neutrinos at production and detect electron neutrinos, tau neutrinos very far away. When I talk about very far away, here I'm talking about at the very least hundreds of meters, but more typically thousands of kilometers. The idea of neutrino oscillations, albeit in a slightly different form, was put forward by Bruno Pontecorvo in 1957, and it relies on the fact that we have two bases which can describe our neutrinos. One is the flavor base. This is the one I discussed, the one where I associate a flavor neutrino to the corresponding charged lepton. But there is another one, that the massive bases. These are the eigenstates of the free Hamiltonian, so they have a specific mass. And the two are related by a unitary matrix, 3 by 3, which goes under the name of the Pontecorvo-Maki-Nakagawa-Sakata matrix, and enters the charge current Lagrangian, and from here into physical processes. This is a parametrization, as I will talk later about the values of these mixing angles. This is how we parameterize this matrix in the lepton sector. This means the sine of theta 23. This is the cosine of theta 23. We have three angles, theta 23, theta 13, and theta 12, that have been measured with really great accuracy in experiments. And I should remark, in the past 20 years from discovery, now we have really very precise information. We have also these CP violating phases, so this change sign when I go from neutrinos to antineutrinos. This is called the Dirac phase that enters in neutrino oscillations, and these two are physical only if neutrinos are Majorana particles. If neutrinos are Dirac particles, like all the other fermions in the standard model, then one can reabsorb these phases in a redefinition of the field. They are unphysical, they disappear from the Lagrangian. If instead neutrinos are Majorana particles, we can think of that in quotation marks as real particles. Particles and antiparticles are indistinguishable, so any rephasing of the field would reappear in the Majorana condition and in a Majorana mass term, and from there into the physical processes. We have no information whatsoever on these phases. We have some controversial hints on what the delta phase is, in the sense that different experiments point in different directions. The situation is not yet very clear. So, how do neutrino oscillations come about? So, in a production, let's say, pion decay into muon and muon neutrino. Then the muon neutrino is a coherent superposition of the massive states with the corresponding elements of the mixing matrix. I put the emphasis on coherent because this is very important for the oscillations to develop. Then here we can use just quantum mechanics to explain this phenomenon. The evolution of the state will be given by the solution of the Schrödinger equation, as we know, and by expressing nu mu in terms of the mass eigenstates, then here the Hamiltonian will pick up its corresponding eigenvalue. And then we can do just a back-of-the-envelope quantum mechanical exercise. We can go and compute what is the probability of this neutrino, nu mu, at production to be detected much farther away as a different flavor, for instance, a nu tau neutrino. So we project the evolved state over nu tau, we make the computation, this is what we get, and then we point out the fact that neutrinos are highly relativistic in all the type of experiments that I consider for oscillations. So I can Taylor expanded first order in the mass squared, and this is the final formula. This is kind of the master formula of neutrino oscillations in vacuum. Here we have the mixing angles through these mixing parameters, and what is important is that when I take the difference of the energies, what I will get is this delta m squares. So delta m squared, that I will use also later on in my talk, this is mi squared minus m1 squared. Why this formula is so important? This formula is so important because the fact that we have observed neutrino oscillations implies that neutrinos have mass and that leptons mix. You see it from here. If masses were 0, this would be 1, and this is just the unitarity condition for an off-diagonal term of UU dagger, so this would be 0. And they mix. In fact, if there was no mixing, this would be the identity matrix, and again, the probability would be 0. This is the key point. Neutrino oscillations imply neutrino masses and mixing. So this is what happens in vacuum. Now, let's go and look at other situations in which neutrinos oscillate. And in many cases, neutrinos go through medium. For instance, if you produce a neutrino here on the surface of the Earth, and then this travels to the detector, it will go through the Earth. Or a neutrino produced in the center of the Sun will propagate to the surface. So in this case, neutrinos will see the background. And in these kind of situations, the background, it contains only electrons, protons, and neutrons, not the corresponding antiparticles. And this will give rise to matter effects, so to a change, an effective mass due to forward elastic scattering. If we describe this in terms of Feynman diagram, these are the two relevant ones. This is an electron neutrino which interacts with an electron in the background via the exchange of a W, so this is a charge current interaction, or all the neutrinos can interact with the protons, the neutrons, and the electrons in the background via a Z. This is a neutral current term. This modifies the neutrino dispersion relation, so gives a contribution to the energy that you see here. It's a weak process, so at very low energy, so it depends on the Fermi constant, and depends on the electron number density of in the Earth or in the Sun. Notice the plus or minus sign, the plus for neutrinos, the minus for antineutrinos. And then before we used quantum mechanics with the Schrödinger formulation to understand and describe neutrino oscillations. How can we modify that formulas to take into account these matter effects? We do that by adding to the free Hamiltonian the term which comes from here. These are called potentials. This is VE, U mu, and U tau. And this is now the Hamiltonian in the flavor basis. We use the flavor basis because, as you can see from here, we don't change the type of neutrino. So if I start with a nu E, I end up with a nu E, and here, well, there's a mu and tau here just outside. So they don't change flavor, and so we have an Hamiltonian better described in the flavor basis. And this is the new Schrödinger equation. This is for a two neutrino case, as is simpler. Here we have the nu E, the nu mu, and here we have the matter potential which comes in. if this is a constant, then it's very simple to decouple the two differential equations. We do that by diagonalizing the Hamiltonian via a mixing angle. Now, this is not anymore the mixing angle that I talked about earlier, the theta 1, 2, theta 2, 3, theta 1, 3, the ones in vacuum. This is a mixing angle which fills the matter effects and is given here. In particular, I want to draw your attention to the denominator here. Then this mixing angle will enter in the oscillation probability, nu A to nu mu, nu E to and so this will depend on sine square of 2 theta m. So let's look at possible situations in which experiments happen. So one case is the case in which this term is negligible. So in that case, we recover the vacuum. So oscillation happen as in vacuum. And notice that this depends on the energy. So if I'm at low energies, this term becomes more important and matter effects will be subdominant. At high energies, or where the densities are very, very high, the opposite is true. Now, matter effects dominate, and they will suppress the mixing angle, because now this is negligible, and this big term here dominates in the denominator. This suppresses neutrino oscillations, and physically is related to the fact that when I produce a neutrino of a given flavor, for example, an electron neutrino, it starts propagating and starts to oscillate. But there is this very important background where with which it interacts and realigns it to the same flavor, to the nu E. So this kind of counteracts the effects of oscillation and suppresses them. There is a final particularly interesting case, which is the one in which the two terms exactly cancel out. Keep in mind that typically we have sometimes a kind of varying densities, sometimes a broad spectrum of energy. So this can indeed be satisfied for part of the neutrinos. So if this is true, then you see here, this goes to 0, the theta m goes to pi over 4. And therefore here, this goes to sine square pi over 2, which is 1. So you have maximal oscillations, and this is independently from the value of the angle theta. So you could have very small mixing angle in matter and still end up with large oscillations because of this resonance. Notice also that this can happen only if delta m square is positive. This is a mass square difference, so it depends on the ordering of the masses. If m2, as in the case of solar neutrinos, is larger than m1, then this resonance can be satisfied in the neutrino channel, which is what we observe actually in solar neutrinos. If instead delta m square is negative, the enhancement of the oscillations will be in the anti-neutrino channel. And this is the physical effect which is used by experiments like Dune or atmospheric neutrino experiments, which try to deduce the ordering between the masses m1 and m3 by using exactly this effect. Just a comment, in situations in which the number density changes with time, things are much more complicated because we cannot decouple the two differential equations, and then we need to solve essentially the problem numerically or with some apt approximations. Of course, the case can still be treated semi-analytically if these terms are small, and so if the evolution is adiabatic. In this case, this will, so if you can neglect these two terms, the states nu A and nu B cannot jump one to the other. They will stay whatever they are. This is the idea behind the MSW effect for Mikhaev, Smirnov, and Wolfenstein. And this explains the oscillations of neutrinos in the sun. So in the sun, one produces large amount of electron neutrinos, and because at high energies, this happens in a very dense environment, the neutrino nu E is mainly the one which has the heavy eigenstate, the heavy eigenvalue. So it's the heavy eigenstate. You can see it from this formula here. So you have the nu E. If this term dominates, you can neglect the other terms, and so nu E is aligned with the heavy eigenstate, which is the heavy eigenvalue. Now, the evolution is adiabatic, and so you start with a heavy eigenstate, and as the neutrino propagates, then it will change because the mixing angle changes, but it will remain the heavy eigenstate till the surface. And on the surface, this will correspond to the heavier mass eigenstate, which conventionally we call the nu2. And now if I go and project the state nu2 onto the flavor nu e, because I want to see the survival probability of nu e to stay nu e, then what we get is actually sine square theta. So this is counterintuitive. You could start with a very small mixing angle, so you would not expect any oscillations, and what this would tell you is that most of the nu e's instead of oscillating into nu mu's and nu taus. In reality, experimentally, we know that this angle is not too small, is around, this value is around 0.3. At low energies, you remember that m squared divided by 2e is large, so we are back in vacuum. And so this is the vacuum survival probability for electron neutrinos. And you see this very interesting shape that actually I will show has been at least tested experimentally at some level. Matter effects matter also in other situations, in particular very interesting in atmospheric neutrino oscillations. And here things are particularly complicated by the fact that we have this profile. So this is the Prem profile for the Earth. So there's a core, mantle, and crust with all these changes in the density and these kind of sharp drops. So this introduces kind of complications in the treatment of this type of oscillations, but that is possible, and I would like to highlight that indeed here in Trieste, most of the works in this area have been done by Professor Petko, who is in the audience, and Professor Smirnov and their collaborators. Very interesting is also the oscillations in supernova. Supernova emit most of their energy, 99% of their energy, in neutrinos. And these neutrinos coming out from the core see a very rapidly changing density, very, very high densities, even with kind of neutrinos interaction with neutrinos themselves that we have not included in the previous picture. And so these are extremely complex oscillations, but what is important is that they can give us information about the dynamics of the explosion and on how really the inner part of the supernova functions. So this is the theoretical framework. Now, have we seen oscillations? Well, I already told you, yes, 1998, the discovery of neutrino oscillations, and this is the beautiful plot. This was presented at the Neutrino 1998 conference, and here you see, this is the number of events, this is the nu mu events, and these are the downgoing, so the ones which come from just above. They've been produced at roughly 10 kilometers or so from the surface of the Earth. These are the downgoing. While these are the upgoing. These are the ones which have been produced on the other side of the Earth. These have traveled hundreds, thousands of kilometers. And you see, these are the Monte Carlo predictions, which match perfectly for the downgoing ones, but fail significantly for the upgoing ones. So you see that there is a suppression of the nu mu flux, but then this suppression depends on the distance they travel. This is really kind of the smoking gun for neutrino oscillations. And this was kind of confirmed at 6.2 sigma in 1998. Since then, there has been, an amazing experimental program which has measured the relevant parameters with great accuracy. So this is the MINOS, the latest MINOS results, and this is the ratio to no oscillations. So ones correspond to no oscillations. Well, here you really see this dip and rise. Is a beautiful confirmation of neutrino oscillations in the nu mu sector. And other experiments, we have IceCube information, and these two experiments which are running at present, NOVA and T2 Hyper K, to give you an idea of the size of these experiments. NOVA is in the US. The beam is produced at Fermi Lab, so you have a beam of protons which impinges on a very heavy target, produces lots of pions and kaons. They decay, producing a muon neutrino beam. And then you go and study the beam 800 kilometers away with a huge detector. These are 20 meters by 20 meters by several tens of meters. And similarly in the US, in Japan, this is the T2K experiment where the baseline is 295 kilometers. ORCA is a different type of technology. ORCA is an experiment in the Mediterranean, which looks at these type of atmospheric neutrino oscillations. And by studying these probabilities, you can then deduce the parameters which control the oscillation probability. So in particular, the delta m square, something happened to my microphone. Yeah. Okay, is it okay now? Okay. So the delta m square and theta 2,3, the mixing angle. And you see how these are kind of very nicely measured at present. We have then the solar sector. This is the picture I showed you earlier. This is the new E survival probability. This is in vacuum. This is the MSW effect. And you see the experimental points, how nicely they lie onto this theoretical prediction. Some of these have been obtained by the Borexino detector, which was at Gran Sasso till very recently. And we have also important information from reactor neutrinos, in particular the Kamlan experiment till a few years ago, and currently Diabei, Reno double show, and the new big experiment which is starting in China, the Juno detector. We are also testing this framework with shorter baseline experiments where the distance between production and detection is for only a few hundred meters, and this is, for instance, the SBN program at Fermila with Microboon, Icarus, and SBND. How much time do I have left? 10 minutes, great, thank you. So this is the current situation. So we have 3 mixing angles measured quite well. So theta 1,2 is around 33 degrees. Theta 2,3 is close to maximal, and theta 1,3 is around 9 degrees. So they've been measured quite well. I cannot expand on this here in this talk, but I want to point out that the mixing in the lepton sector is very different to the mixing in the quark sector, and this kind of might tell us something about where this mixing originates from. And we have the 2 delta m squares. Delta m square 2,1, the one measured in solar neutrino experiments in Kamlan, which is around 7.5 10 to the minus 5 eV squared, and delta m square 3,1, which is around 2.5 10 to the minus 3 eV squared. For this one, we don't yet know if M3 is heavier than M1 or vice versa. This is called the ordering of neutrino masses. This is one of the key questions we have to answer in the coming future. So, and here I would like to point out that the scale of these masses is really very, very small. So we are talking about sub-electronal masses, and this is key in understanding where these masses come from, as I will discuss a little bit later. So this is the, what is still to be understood. And most importantly, I just want to mention this question here, the nature of neutrinos. So if neutrinos are Majorana particles, they are equal to their charge conjugate. So they are indistinguishable from their antiparticles. And this is really key because it relates to, as I already mentioned, the violation or not of lepton number. And this is crucial information to guide us to understand where these masses come from. And then we want to determine the values of the masses, if there is CP violation, measure precisely the mixing angles, and check if this standard picture that I discussed so far is actually correct. So before moving on to the last part of my talk and the issue of neutrino masses, I want to highlight some issues, some quantum mechanical issues in this description of neutrino oscillations that I did. And the first point is energy momentum conservation. So hidden in my description of neutrinos, I had the assumption that the neutrinos have all the same momentum, exactly the same momentum. And this kind of is contrary to energy momentum conservation in this process. For instance, this is a pion decay, and the pion energy needs to be equal to the mu1 energy and the energy of the neutrino. But E1 and E2 are different because the masses are different. So is here a fundamental contradiction? Not really, because my assumption of exact momentum, which is a plane wave assumption on neutrinos, is actually not correct. Neutrinos are produced in a given region of space. They are detected in my detector, which is kind of a finite region of space, and they travel in between. which means that I cannot describe them as plane waves, but I have to go beyond, as I will describe next, in terms of a wave function description with a given size, but also an uncertainty on momentum and uncertainty on energy. If the uncertainty on the energy is larger than the difference of the two energies, E2 and E1, then I can produce coherently the three mass eigenstates when I produce, for instance, a muon neutrino, which I highlighted earlier on. So, as I said, we need to go beyond the picture I had earlier using a wave packet description, which takes into account the localization of the production and detection regions. The thing is that once you do all this, you end up with an oscillation formula which is exactly the one that I showed you earlier. So indeed, it's a complication of the formulas that usually we don't take into account because the final result is the same. The only relevance could be due to the fact that now we have a wave packet which is the superposition of the wave packets of the three massive neutrinos. They have slightly different masses, so the group velocity is slightly different. And so if one waits a sufficiently long time, the three wave packets will separate, suppressing neutrino oscillations. And so we would have to kind of modify the oscillation probability by this damping term, which depends on the coherence length. The coherence length is the kind of the ratio between the size of the wave packet and the oscillation length given by delta m squared divided by 2e. So the point is, and not just to mention, there are situations in which neutrino travels extremely long distances, for example, supernova neutrinos. So how do we estimate these size of the wave packet? Well, this is done looking at what are the typical time scales relevant in the process. For instance, if I look at the pion decay in vacuum, then this pion would have a lifetime, and then I can relate this lifetime through Heisenberg principle to a uncertainty in energy, momentum, and distance. So this would set my sigma x for the wave function, and I can estimate this would be in the order of meters. It is to say, and this is something that I know is currently under study, that pions are not produced in vacuum. They are typically produced in a very, very dense environment where they can interact with the surrounding matter. This tends to localize them much more efficiently, and this leads to a much larger spread in energy, as well as a much shorter size for the wave packet. There have been estimates, for instance, also in the sun. Here we get very short scales, and there has been kind of some analysis of data. So if you have this term that I showed, then oscillations will be suppressed, will be damped at a given energy. This can be looked at in the data to see if indeed this is the case, and this allows to put bounds on lower bounds on the size of the wave packet. For example, this has been obtained with the Diabet reactor data, and I want to highlight this because these are extremely recent results. This is a Nature paper which came out last February. This is the first direct measurement of the lower bound of a neutrino wave function in electron capture done by the best experiment, which finds here a lower bound of around 6.2 picometers. Compare then, these are kind of theoretical predictions. Remaining to the topic of neutrinos and quantum mechanics, are neutrinos really behaving quantum mechanically? But I think that by now I've convinced you that that is the case, but you can actually test it quantitatively by looking at the violation of the Leggettgard inequality in neutrino oscillations. So you construct a correlation of measurement at different times. In particular, this will depend only on the difference between T1 and T2, and so we'll end up depending on the energies. So then one looks at this correlator at different energies, and in particular construct this Leggettgard quantity, which depends on the oscillation probability. Here I'm looking at the mu because this has been done for the Minos experiment, which looked at the muon disappearance probability. So you take different energies and the sum of the energies. Now, if you have a classical behavior, then he would have 1, 1, and 1, and this would give you, then the k needs to be equal and smaller than 1. And then here you have, this should be 2 actually, and you can go and test it. So you take many different combinations of energies here, which give you these kind of bands for the value k3, and you see very clearly that they lie in the quantum region at a quite high value indeed, while the classical region is down here. This was done a few years ago using the Minos results. So I'm going to use the last few minutes to discuss about the information that neutrinos give me about nature. And this really, neutrinos are crucial in this because the neutrino masses cannot be explained in the context of the standard model. And so, and as you see, this is where neutrino masses lie. Here. And this is at scales much lower than the ones of all the other fermions. So why neutrinos have masses, and why are they so much lighter than all the other fermions? Now, let me start by going beyond the standard model. So what is the simplest thing I can possibly do? This is to introduce a right-handed neutrino. This is a pure singlet of the standard model, and it can couple to the leptonic doublet and the Higgs. When the Higgs gets a VEV, then this will induce a Dirac mass like all the other fermions. Now, what is, well, first of all, is SU2 and U1 lepton invariant, so it can be added to the Lagrangian. But the first problem is why we would get a coupling which is so tiny in nature. If I plug in the mass of the neutrino and the VEV of the Higgs, I get a value which is around 10 to the minus 12, so extremely tiny, and this kind of calls for fine-tuning of the theory. Now, the other reason why I think this solution is unsatisfactory is this new right is a pure singlet of the standard model. So it should have a Majorana mass term, and this should be included in the Lagrangian. Now, if I don't want to do that, to retain this Dirac picture, then I have to impose lepton number as a conserved symmetry of nature. And this is a major departure from the standard model. We are promoting what is an accidental symmetry of nature to a fundamental one. There is another possibility instead, is that to have Majorana masses. And this is the dimension 5 operator, indeed the only dimension 5 operator that I can add to the standard model Lagrangian, where I couple a leptonic doublet, which contains a neutrino, to the Higgs twice. And then when the Higgs gets a VEV, this will give a Majorana mass term here. Now, what is this mass scale? I need to introduce it because this is dimension 5. So in the Lagrangian density, I have to divide it by a mass scale. But it's very important. This signals the existence of a new theory at the scale m, which induces neutrino masses. What type of theories I can have? Typically, this is the way in which I can open up this effective operator. As you see, here I have a spin 1/2 particle, and here I have a scalar. So it needs to be a fermion in these two cases, and I'm combining two SU2 doublets, L and H. So their combination can either be a singlet or a triplet. So I will have the fermionic singlet, this goes under the name of CISO type 1, or this is the triplet, CISO type 3. I can also combine it in a different way. In this case, this will be a scalar triple, and this goes under the name of CISO type 2. The standard picture, let's say the vanilla explanation of neutrino masses, is the CISO type 1 mechanism, in which, as I said, as we did before, we introduce a right-handed neutrino. Now I call it N because I have in mind a very heavy particle. As before, it can couple to the Higgs and the leptonic doublet, but moreover, now I don't impose lepton number as a symmetry, which means I will have this Majorana mass term. When the Higgs gets a VEV, I will get a Dirac mass, and I need to diagonalize this mass matrix which gives me light neutrino masses. In particular, neutrinos depend on the Dirac mass squared here and the heavy scale. So if I plug in a Dirac mass like that of all the other fermions of the Standard Model, for instance, the tau mass, 1 GeV, and I put here a gut-inspired mass for the right-handed neutrinos, I get exactly these sub-EV masses which explain the data that I observe. And so this is a beautiful picture because not only is explained neutrino masses, but also why they are so small. And the result of this will be Majorana neutrinos. So actually we can test this in experiments, in particular in neutrinoless double beta decay, at least their nature, not the origin of the masses entirely. So how do we go beyond? We have to decide what is the new, or we have to explore what is the new physics scale. Typically, we go to high energies, where we can, for example, inscribe the seesaw type 1 mechanism that I showed you in gut theories, for instance, in SO10. Or we can lower it to the TV scale, so that, in principle, the new particles could be accessible in experiments like colliders, LHC, for instance. Now, there have been no hints of new physics at the TV scale, nor we have seen proton decay. So we have now exploring a broader range of mass scales, and very interestingly, it's possible that the new physics could be even below the electroweak scale. This is the case of dark sectors, also called hidden sectors. Yesterday, Professor Cornell called them too sly, and I call them too shy. They are too weakly coupled to the Standard Model to show up in experiments. So we need very sensitive experiments to really find these particles. We can implement the seesaw and its minimal formulation of time 1 or with extensions also at this scale. So neutrino masses could be generated here, and this scale would be just around the corner. So it's very interesting to search for it. So I come to my conclusions. Neutrinos are the most elusive and mysterious of the known particles, and neutrino oscillations really play a crucial role in our understanding of particles and interactions, because they tell us that the Standard Model is not complete, and we need to extend it to a new theory. Then, combined with the problem of dark matter and the baryon asymmetry, we can try to understand what is the new Standard Model. And in this sense, neutrino physics helps us really open a new window on the fundamental laws of nature and understand the evolution of the universe. Thank you very much.
Survey of the very fundamental process of neutrino and very quantum process of neutrino oscillation and what it teaches us. There is a question there.
I'll try to speak loud. Are weakly interacting, and therefore, when they are produced, they are entangled, and since they interact so little, most likely they remain entangled. There are theoretical works that try to combine many-body quantum physics with a certain other peculiar effects.
Okay, so they are entangled between themselves in the sense of the coherent superposition of states. They are also entangled with whatever produces, in particular the muon, which is produced in, for instance, the pion decay. So for standard neutrino physics, where the mass square differences are very small, some works have looked at the possible consequences and are not particularly, they would not be visible in experiments. At some point, there were some indications which are still controversial and not excluded of possible sterile neutrino in the EV range. And in that case, for example, what the muon does, so after the decay, so the pion decays typically in a decay pipe, and then the muon can either escape or most likely interact with the walls of the decay pipe, and that can have consequences on neutrinos. So this has been studied. Till we don't see EV sterile neutrinos, this remains a purely theoretical issue. If we were to see them, then this would become interesting from a quantum mechanical point of view to be studied in this type of experiments. Okay, that is even, okay, maybe we can discuss this later. Now, that is more exotic.
Sandro?
at some point you mentioned the importance of understanding the question of PC symmetry violation. Are there connections with the question of neutrino oscillations?
Neutrino oscillation and symmetry breaking of?
Parity symmetry violation.
Yes. See, this is fundamental. So this is really very important. So we know that CP is violated in the quark sector. We don't know yet if it is violated in the lepton sector. As we don't really have at least a vanilla explanation where CP violation comes from, seeing what happens in these two sectors is indeed very, very important from a purely theoretical point of view. In fact, models, for example, of symmetries might induce or might predict or not CP violation depending on the properties of the flavor symmetry one uses, etc. There's another reason why that is so important, because this is one of the three key elements to explain the baryon asymmetry in the universe. So if we start with a universe which is symmetric, baryons and antibaryons have the same number, and then we can generate an excess of baryons, which is what we observe, the baryon asymmetry, via dynamical processes. And for that to happen, we need to have baryon lepton number violation, out of equilibrium, and most importantly, CP violation, which manifests itself as complex couplings in the Lagrangian. So that is very, very important, and that is the key physical goal of the next generation of long baseline neutrino experiments, T2 Hyper-K and Dune.
Thank you. Sal?
Major source of decoherence you mentioned there.
Dimension is mainly the separation of the wave packets because of the different group velocities, the different masses of the three components. Neutrinos travel, interact so weakly that really they don't really see, they don't interact with the rest. So that I would say is it's dominant.
Okay. No more questions, so we thank Sylvia again.
Thank you.
And we are slightly late. Let us reconvene at 3:55.
So this is the last scientific talk, right?
Yes.
And so I have an hour and 40 minutes, is that? No, I'm just.
Try to start your time. You can.
No. This is.
You know you have.
I always. This is. No. I supposed to be 40, but I know I always go.
But that will be fine. Because people want to listen to you.
That's okay.
Well, people are coming back.
Then there's the prize thing.
I don't know what this is. It will be I think the
IBM is
announcement.
A prize.
Yeah, maybe. Yes.
Yeah.
They've announced them, but they don't need half an hour to do that, so they will squeeze this.
No, this is IBM, huh?
ICTP and IBM.
But are they giving a prize now? What's the future?
Okay. It's time to get back for the last session of this conference, and we managed to get through nearly 3 days of quantum mechanics without getting into quantum field theory. Well, it was there a little bit in Subir's talk this morning, but now we'll get into the full glory of quantum field theory, and there could not be a better speaker for that than David Gross, and it's my great pleasure to give him the floor.
Thank you. Well, it really is a great pleasure to be here once again at the ICTP and to give the last scientific talk. This has been an amazing conference. This has been an amazing century of quantum mechanics, my God. And we've seen a lot of its glory and accomplishments. As Mark said, there has been very little talk about quantum field theory. So I'm going to try to give you a quick history of relativistic quantum mechanics, and which in non-gravitational theories appears to be described by quantum field theory extremely successfully. I'll just describe the evolution and the constitution of a comprehensive theory of matter and force, a standard model of particle physics, triumph of quantum mechanics, quantum field theory. I'll discuss some of the challenges we now face in extending our quantum understanding to gravity and string theory. And then I'll discuss some of the hints of an upcoming radical modification of our basic conceptual framework, especially the emergence of space-time as a quantum phenomena, and then a few brief speculative words about beyond quantum mechanics. So briefly, a history. Of course, quantum mechanics started with the properties of a relativistic quantum field, classical field, electromagnetism, whose excitations are light waves. And that's where Planck's constant and the quantum nature of light first emerged. By Planck and really as interpreted correctly by Einstein, that light appears to exist in finite bunches of energies which have particle-like nature. And the energy is quantized in units of a fundamental constant of action, Planck's constant. When the structure of the atom was revealed by Rutherford, who discovered the nucleus of atoms and constructed a solar system model of the atoms, it only took 2 years before his postdoc, Niels Bohr, applied crude approximation, a semi-classical, what we now understand as a semi-classical approximation of quantum mechanics to construct a stable, quantized version of Rutherford's model of the atom, which was qualitatively extraordinarily successful. He could calculate the Rydberg constant and begin to understand the atomic structure of matter as was put forward in the previous century by Mendeleev and others. With the insight of de Broglie that not only light but matter had wave-like characteristics, and the discovery, in fact, of the electron spin and its quantization, the stage was set for the development of quantum mechanics. Now, remarkably, it only took about 10 years, very little experimental input. Theorists were presented with this, lucky for us, integrable system, the hydrogen atom. So much progress could be made with what was inherently an inconsistent model. And when the inconsistency were resolved, in the period that began in 100 years ago, quantum mechanics in its form that, truly speaking, hasn't changed. Our understanding has greatly deepened, but quantum mechanics, in some sense, in its original form, has persisted for 100 years. Of course, this started with Heisenberg's matrix mechanics, then the uncertainty principle, Schrödinger's wave equation, Dirac's understanding of the quantization, how to quantize a classical system. And then, of course, Born, Jordan, Heisenberg, understanding of the probabilistic nature of quantum predictions, complementarity of the classical, or the classical limit of quantum mechanics, Pauli's discovery of fermions, von Neumann's discovery of Hilbert space as the correct mathematical framework that replaced classical phase space. And by 1927, quantum mechanics, as we still know it, was in a sense complete. The Solvay conference in 1927, all of the actors appeared. Here they are. Planck, Einstein, Born, Heisenberg, Pauli, Schrödinger, someone else. Bohr. What a conference. The color was added. These people were black and white. Okay, when quantum mechanics was complete, it really was in a non-relativistic setting, although, of course, describing light is always a relativistic setting. But the challenge immediately was to marry quantum mechanics and relativity, the two pillars of modern physics. And that happened, again, extraordinarily fast. No surprise, because one, in describing the atom and light, at least, was relativistic, although the Bohr model was not. And Dirac rapidly discovered a marvelous equation that described accurately the properties of electrons in hydrogen, and greatly successful, but led to a phenomenon which he was actually trying to avoid, namely the existence of antiparticles, or in his language, negative energy states. And people realized very quickly that relativistic quantum mechanics required that for every particle there exists an antiparticle with opposite charge, and since one could create pairs, particle-antiparticles, from nothing, from the vacuum, relativistic quantum mechanics was necessarily a many-body problem, which made it much harder. However, electrodynamics was there as a relativistic theory of light, and so Dirac had told us how to quantize any classical theory. It was straightforward in a way. Dirac, Heisenberg, Pauli, Weisskopf, Jordan, and others were able to write, in principle, quantize electrodynamics. However, the problems of trying to use that quantization as a calculational tool to calculate quantum corrections was long and plagued by technical, what we now would regard as technical difficulties, how to preserve gauge invariance of the underlying theory, and how to deal with the ubiquitous ultraviolet infinities that occurred when one tried to calculate any quantum correction to scattering or to the magnetic moment of the electron. The inventors of quantum mechanics, by and large, over the next many years, Dirac until the end of his life, as far as I can tell, were willing to give up on quantum field theory. And they were revolutionaries, after all. So if there were problems, in fact, as we all know, that was not necessary. Quantum field theory was then tried to be applied to the emerging experimental evidence for the structure of nuclei, nucleons. By that time, it was clear there were kind of two nuclear phenomena, forces that were happening, the weak nuclear force that was responsible for beta decay. And Fermi came up, 1932, I think, with what we would call today an effective field theory, an approximation, a model for beta decay, for fermion interaction, very different than electromagnetism. And I don't think it was ever thought to be a fundamental theory, but a very good model. Yukawa hypothesized that since the strong nuclear force was short range, mediated by some field, he conjectured that it would be mediated by a massive vector boson, like the photon, but massive, and the pion. He thought it was a vector meson because, after all, the photon was a vector meson. So all force carriers should be vector. It was discovered, it turned out to be a pseudoscalar. And there were many attempts over the years, from the 30s onward, from the 40s, to construct a field theory with the heavy pion playing the role of the electromagnetic, of the photon. Didn't work. After the war, the theorists returned to the study of quantum electrodynamics, spurned by experiments. They really wanted to understand the precision experimental measurements of the properties of atomic levels and the magnetic moment of the electron, of which we heard about here. And that took a few years. Feynman, Schwinger, Tominaga, and Dyson especially. And what was necessary to deal with the ultraviolet divergences was a primitive understanding of what we would call today renormalization theory, where they understood that the parameters that appear in the microscopic description of a quantum field theory that you write down in the Lagrangian or the Hamiltonian are really not what you measure. They refer to, in a local theory, to the charges or masses as measured at arbitrarily short distances. Whereas the things we, of course, measure are at microscopic distances. And in quantum field theory, these parameters are distance dependent and can be infinite, as occurs in quantum electrodynamics, at arbitrarily short distances, and finite, as observed. Rewritten in terms of physical observables, quantum corrections could be calculated with finite results. Along the way, Feynman discovered a marvelous way of representing the perturbative calculations of a quantum field theory in terms of diagrams, Feynman diagrams, which greatly enabled physicists to picture what was going on in quantum field theory, perturbatively around free particles, and calculate. And the calculations yielded, of course, immediate agreement with the experiment at the time, and have continued to do so for the last, what is it now, 75 years, with unbelievable accuracy, achieving some of the most precise agreement between theory, fundamental theory, and incredibly precise, careful calculations. Both are miracles of human achievement. And for example, the calculation and observation measurement of the magnetic moment of the electron is now in agreement to 12 decimal points. Physics should really be proud of that continual search for precision, which drives, stimulates incredible developments in experimental methods and technology and theoretical methods of computation and of theory. One of the inventions of Feynman that led to Feynman diagrams, and it had a profound influence on our understanding of quantum mechanics, is following Dirac, the understanding that you can calculate amplitudes of quantum mechanics by path integrals. The amplitude for a particle to move from x1 to x2 in time t in some potential, with some interactions, is gotten by summing over all possible paths weighted by the exponential of the action divided by h bar. This explains how the classical limit emerges as h bar goes to 0, or the action of a physical phenomena is big compared to h bar. Then the sum over all paths is dominated by a classical saddle point where the action is extremal and fluctuations about it. The same method has been applied years later, and actually not by Feynman particularly, to quantum field theory, and has dominated the way we think about quantum field theory, the way we calculate semi-classically, especially the way we understand how to quantize classical field theories. Enormous impact. Now, in the following years, people tried to write down a quantum field theory of elementary particles, neutrons, protons, and force carriers, pions, and do what Feynman and Schwinger had done for electrodynamics. Total failure. To a large extent, then a focus on what are the observables of the interaction of elementary particles, protons, neutrons, and dozens and dozens of new particles that were discovered originally in cosmic rays and then in particle detectors at colliders, where people smashed particles together to see what was going on, much like Rutherford did. The S matrix. And that's what we still do in particle physics, except now we smash them together in 1,000,000 times higher energies, enormous machines like the LHC with unbelievable detectors. These are amazing, amazing experimental instruments. And we, once in a while, detect new physics, like this is a Higgs particle event, where the final cornerstone of the standard model, particle physics, was discovered about 10 years ago. theoretical point of view, there were a lot of developments from quantum electrodynamics, even before till the success, till our present understanding. Some of the most important, and I don't have time to discuss the whole history, of course, is the realization, the close connection between statistical mechanics, classical systems, and quantum field theory. Because, of course, quantum field theory can be formulated on any background space-time. And if you make time imaginary, so you go to what we call Euclidean quantum field theory, and compactify time, then the time evolution operator of the quantum mechanical system, either the IHT turns into, T goes to IT, turns into the Boltzmann factor that weights configurations in statistical mechanics. So if you can control quantum field theory in d spatial dimensions and one time dimension, you learn something about the statistical mechanics of a d-dimensional system. This has led this and other connections between many-body theory, used to study ordinary matter, condensed matter physics, which is the theory of 10 to the 23, if not infinite number of particles, and quantum field theory has been so productive over the last 40, 50 years. The renormalization group, the understanding of the true meaning of renormalization in quantum field theory, the scale dependence of quantum phenomena in a many-body system, and, oops, there's an N missing, and the fixed points of the renormalization group, which are theories, quantum mechanical theories, quantum field theories, which have no scale. As you scale things down to discuss, or up to discuss physics in these limits, you approach often a fixed point described by a theory with no scale, which has a larger symmetry and formal field theory. These are the best understood points in the space of possible quantum field theories. Another very important development, which began very early on, was the generalization of the one classical field theory we had, electrodynamics, to a non-abelian gauge theory, Yang and Mills theory, who tried to generalize electrodynamics from a abelian phase rotation, local phase invariance, to SU2, motivated by an approximate SU2 symmetry of the nuclear force, isotopic spin symmetry, and imagined using this as a dynamical basis for describing nuclear forces. But this approach, which attracted much attention, didn't really materialize for 30 years, 20 to 30 years, because in the case of the weak interactions, the symmetry that would underlie the weak interactions was badly broken, like isotopic spin, and it is truly inconsistent to couple a gauge symmetry to a non-existent symmetry. This was eventually understood, the so-called Higgs or Braut-Angler-Higgs mechanism, which underlies our understanding in the standard model of the weak nuclear force. And in the case of the strong interactions, well, the proton and neutron were not kind of elementary sources of some kind of non-abelian gauge symmetry. The symmetry certainly wouldn't be exact. The sources were hidden. They were, as it turns out, quarks, colored quarks, 3 colors, And they were hidden. Nobody had ever seen a quark. So it was not at all clear how to construct a gauge theory of quarks. Everything else was tried. In the case of the strong interactions, the insight came from experiment, deep inelastic scattering, which was a precision microscope using electrons to probe the structure of nucleons and to see at short distances over short times freely moving quarks, fractional charges, but they never got out. No matter how fast, you could not ionize nuclear matter. Then inside there, and I'm not going to go through the history of the Standard Model in detail, don't have time. I'll just say a word about my favorite part, the strong force, which turned out to be described by a non-abelian gauge field, much like electrodynamics, except the gauge symmetry is SU3, not U1, mediated by the chromodynamic field. In a classical vacuum, a classical theory of QCD, quantum chromodynamics, a quark and an anti-quark would have a force which obeyed Coulomb's law. It would fall off like 1 over r squared, and you can ionize the proton. And the force gets stronger when you pull the quarks together. What was discovered was that the quarks don't live in the vacuum. They live in the quantum vacuum, where the vacuum is full of virtual pairs of quarks and the non-abelian charged quanta of the chromodynamic field, vector mesons, gluons, which dominate. And in that medium, it turns out that the flux lines are squeezed to a tube, if you want, much like magnetic flux lines are squeezed in a superconductor to a tube. This is the magnetic analog of superconductivity, if you want, the chromodynamic magnetic analog. And in a tube like that, the force between the quarks is constant. It does not decrease as you pull the quarks above. As this describes a force that does not decrease at large distances, and therefore you can't pull the quarks out. It would take an infinite amount of energy to ionize the nucleon. But most importantly, it explains why the quarks are freely moving. The force decreases at short distances. And that is the basis of quantum chromodynamics, which is by now extraordinarily well confirmed by experiment. So we now have been in a situation for 50 years. Thousands of experiments have been done. No quarks have ever been seen. And since the force between the quarks becomes weak at short distances, and most what goes on at CERN is seeing interactions of the quarks at the core, where we can calculate and predict what happens, and those predictions have been verified to extraordinary accuracy. QCD, the theory of the strong interactions, is a remarkable theory that would have been hard to imagine 100 years ago. I like to say it's a perfect theory. It achieves 3 phenomena which are really unusual and place enormous constraints on doing better in the future. First of all, it really has no infinities. In the case of QCD, the coupling constant in alpha, the analog of the fine structure constant, vanishes at arbitrarily short distances, the opposite of QED, and varies with scale, becomes stronger and stronger as you move the quarks apart. No infinities. There's also, it's the first time we have a microscopic theory of matter which has no place where it breaks down. There's no new physics as you go to shorter and shorter distances. Unlike the problems in electrodynamics, which even exist classically if you have point-like electrons. At higher and higher energies or shorter and shorter distances, the theory becomes more and more trivial. Eventually, asymptotically free, a theory of free quarks. And finally, in a sense, there are no adjustable parameters. QCD is, if we forget about the quarks, has only 3 parameters. The velocity of light, Planck's constant, and a coupling. Now, there's no parameter of length, but of course, in the theory, the coupling depends on length. That's the essence of the phenomenon of renormalization. Or, if you want in many-body physics, screening or paramagnetism, there's a dependence on length. The theory, because of confinement, creates stable particles of a given mass and size. And in the end, all observables are determined in terms of the 3 fundamental constants you need in nature so far, C, H, and the mass of the lightest particle, say the proton, the one that we used to use in Paris to determine the standard of mass. Everything else is calculable. Now, of course, in real world, there are 3 colors, SU3. We don't know where that comes from. They're the quark masses, which are not determined by strong nuclear force, but by the Higgs mechanism. We don't know where that comes from. Then there are other forces in nature, including, most importantly, perhaps, gravity. But in and of itself, QCD has no adjustable parameters. Therefore, we can't do a good approximation a priori calculate the complete mass spectrum of the theory, and that has been done because you can solve the theory in terms of an infinite dimensional integral. It's hard to do infinite dimensional integrals, so we approximate by a finite dimensional integral by putting the theory on a lattice and taking a continuum limit. And in fact, unfortunately, that remains the only a priori precise controllable first principle calculations of static hadronic properties. But it's amazingly successful. And it's received in the last decade a new level of maturity due to 2 things. One is Moore's law, and the other is theoretical ingenuity. So this is a slide that shows calculation of some of the dozens of particles that have been discovered over the years, including neutron, proton, rho meson, pion, lots of particles, including particles made out of the more recently discovered very heavy quarks. These are now at the level of less than 1% accuracy. And as I said, to really get that kind of precision, you need to put in the mass of the quarks as parameters. But aside from that, there are no parameters. Remarkably, that took 40 years. We've had a lot of talk about computation and precision, 40 years. And it really required the factor of 1 billion that Moore's law has achieved over the last 40 years, but also the factor of 1 billion that theorists have achieved by a lot of hard work, knowing how to take the continuum limit, knowing how to deal with the spontaneous symmetry breaking of chiral symmetry, et cetera, et cetera. And now this is a powerful tool, which is used to calculate the predictions of QCD in the standard model, looking for new physics or violations. For example, comparison of the standard model with experiment in the case of G minus 2 of the muon. So we've ended up with a standard model, discovered along the way many new quarks, but the theory doesn't really change. Well, it changes, but. And no more new quarks after about the 70s, early 80s. 3 forces, all gauge forces, all cousins of electromagnetism, with, in the case of electromagnetism, 1 charge, U1, gauge theory. In the case of the weak interactions, 2 charges, the charges being so-called flavors, up and down. And in the case of the strong interactions, 3 charges, the charges being the so-called colors of quantum chromodynamics. And the final cornerstone, of course, is the Higgs mechanism that breaks the SU2 weak gauge theory and was discovered 10 years ago. Whose properties we still don't truly, have not been measured completely at all, a lot to do, and whose property and whose mass are still certainly not understood and may be more complex than we usually assume. This model is not much more than a model. It works from the Planck length to the edge of the universe. And all these thousands of tests over the last 40 years works, much to the disappointment of all my experimental colleagues and many of my theoretical colleagues. So it really should be called a theory, for God's sakes. This is the most complete theory of matter and force than we've had. What have we learned, in essence? I tried to summarize what we've learned onto one slide, not easy. So we've learned that matter is made out of charged, 1, 2, 3 kinds of charges, spin 1/2 fermions. We've learned that the forces are described by quantum gauge fields. We've learned that quantum gauge fields come in 3 phases, some of which you've heard now from Subir's talk, talking about. I think all 3 phases appeared in his talk. Electromagnetism, we're acquainted with for almost 150, maybe 200 years, described by a UN gauge field. The force is long range, Coulomb. The gauge symmetry is not broken. The weak interaction is described by a SU2 gauge field with 2 charges, a chiral gauge field. And it's broken by the Higgs mechanism, screened. The Higgs part, the breaking, from our point of view, is somewhat unnatural. There are many mechanisms, there are many things that could have happened instead to break the symmetry. Still the least understood part of the standard model by far. And finally, the strong force is unbroken gauge field, but confining. Now, beyond the standard model, of course, there are lots of things that experimentalists discovered or are not answered by the standard model and remain the main focus of ordinary elementary particle experiment and theory and will for many, many years to come. Neutrinos, we just heard about, and their wonderful properties. They're hard to detect and measure, and they're very weird. Neutrino masses, we still don't understand. Baryon, and then a lot of the other things we don't understand, we've learned about from astronomy and astrophysics and from observing the universe. Baryon asymmetry of a symmetric universe, presumably, can be generated theoretically. We believe that could, most likely, if we knew enough about neutrinos and maybe other additions, we could explain it. But astronomers have discovered a new form of matter. Most of the matter in the universe, we call it dark because it doesn't radiate or couple to standard model easily, so it's hard to observe on Earth. We haven't yet observed it on Earth or produced it, but astronomers have mapped out the dark matter in the universe. They've also discovered that the universe's expansion is accelerating currently, and that, in Einstein theory, is explained by a cosmological constant, which is a form of a fluid filling the universe with energy and negative pressure. The negative pressure makes the universe accelerate its expansion. We do not understand that. I mean, it's part of Einstein's theory, but the parameter is so small that it makes no sense. Theoretically, we theorists have other reasons to go beyond the standard model. It appears obvious from the structure of the standard theory that these gauge forces fit together so beautifully, the form matter fits together so beautifully, that it's easy and compelling to unify them. We don't understand a lot about the Higgs, why it's so light, what it really is. We don't understand how the masses and mixing of the quarks and leptons are generated, or what they are. And we certainly don't understand dark energy, dark matter, and the microscopic nature of quantum gravity. Some of these answers we hope will be provided by ongoing and current experiments that are being prepared, like the FCC at CERN. And some of them we're informed by looking at the universe. This remarkable connection nowadays between fundamental questions in cosmology and fundamental questions in particle physics and field theory. Indeed, it's always been necessary to understand what goes on at short distances and high energies to map out, as astrophysicists and cosmologists have done over the last 100 years, the complete history of the universe. Because early on, the universe was very hot and energetic, and if we didn't have the standard theory, we couldn't extrapolate very far back. But from the other point of view, now we're really interested in using the largest or earliest nature of the universe to explore beyond where we can measure, through the earliest times of the universe where new physics will definitely arise. Theorists were drawn immediately after the emergence of the standard model to extrapolate the theory. In the case of the strong nuclear force, you could easily do because it got weaker and weaker. And remarkably, crudely, these forces vary logarithmically at these very high energies and converge. They converge because it's a logarithmic dependence at very high energies. This, to me, remains the strongest clue we have as to where possible unification of all the forces of nature occur, remarkably, all because that also includes the force of gravity, which is negligibly weak at macroscopic or low energies unless you pile together 10 to the 25 atoms or more. But, the force of gravity gets stronger and stronger when you consider more energetic or massive objects. And at the same enormous energy scale or very short distance, identified already by Planck, the Planck scale, everything seems to converge, all described by gauge interactions. gravity is a gauge theory of diffeomorphism of space-time. Now, we've known for many years, in fact, this was one of the things that accordingly bugged Einstein. One of the reasons he was so not willing to accept quantum mechanics, and ignored all the developments that happened roughly after 1930 or so. For 25 years, tried to unify all the forces, non-quantum mechanically, was that nobody ever came up with a consistent quantum theory of gravity. It's notoriously hard because at very short distances, at the Planck scale, the characteristic scale of gravity, the fluctuations of geometry are violent, uncontrollable. And it's clear that, well, one answer is throw away quantum mechanics. There's no problem, maybe. But if you include quantum mechanics, the quantum fluctuations of space-time itself become uncontrollable. And to quantum physicists, quantum field theorists, particle physicists, it was obvious you'd have to modify Einstein's theory, which he tried to do as well. So, in this extrapolation, we've been led to a new kind of theory, string theory, in which at first seemed to be a radical departure, not from quantum mechanics, but from quantum field theory, from particle theory, to the quantum theory of extended objects. First appeared in the three-man quantum mechanical paper, by the way. And that's not too surprising, in a way. String theory, which had been discovered before the Standard Model. It wasn't real understood that it was string theory, but in trying to construct a theory of the strong nuclear force, there were features. For example, like this feature of quarks. You pull them apart, these flux tubes emerge. So the object here looks a lot like a string, a fat string. And that's how people stumbled once again upon a very simple theory, luckily. Otherwise, string theory might have taken 100 or 200 years to discover, which looked like a quantization of an extended one-dimensional object, a string. And that sort of looks like a meson. You attach labels. It's where the quark charges are to the ends of the string. In fact, now we really understand that gauge theory and string theories are dual representation of the same physics in many cases that can be analyzed, not yet for QCD, but probably will come. But the remarkable thing that was discovered in trying to develop this theory of the nuclear force was that in the case of fundamental strings, when you close the open strings, consider excitations of closed strings, they have the properties of quantum gravity. So in trying to describe the fluctuation, the quantum dynamics of extended one-dimensional objects, you're led to many things: gravity, extra dimensions of space, which have to be compactified to agree with the experiment, of course, and supersymmetry. Question remains, are particles now, all of them? These vibrating superstrings describe all of the kinds of particles we've ever seen, the quarks and leptons and gauge particles and Higgses, everything is there to be used to construct a top-down theory of the Standard Model, including, hopefully, the calculation of all of its parameters. Okay, long story, has not been successful, as you all know. But one of the great insights that has emerged, especially in the last 20 years is the duality, originally between closed and open strings, now between two dual representations of the same dynamics. You must have heard of ADS-CFT, the mathematical equivalence, which is undeniable, now between ordinary quantum mechanical theories in 4 dimensions, just like we see around us, rigid geometry, no gravity, and string theories, or quantum gravity, in a 5-dimensional space with negative curvature, anti-de Sitter space, which has a boundary on which the dual theory lives. These theories, many such dualities are exact and have, to a large extent, solved one of the fundamental challenges to quantum mechanics that was raised in the last 50 years. And that is the properties of black holes, which appear to swallow information, violate the unitary time evolution of quantum mechanics, and Hawking claimed that this would mean that quantum mechanics has to be modified in a fundamental way. However, this duality enables us in some toy models, special cases, and more of them, and in much more detail now, to replace the quantum mechanical black holes in, say, anti-de Sitter space with ordinary heavy ion black balls, in quark gluon fireballs that are created in Brookhaven and at CERN when you collide heavy ions together. Their evaporation does not violate unitarity, and they're dual to black holes whose evaporation in ADS or other dual spacetimes does not violate. And that was the point where Hawking gave up and said, okay, quantum mechanics is okay, you don't have to modify it. But that has led this duality between ordinary quantum mechanical systems with no gravity and quantum mechanical gravitational systems and string theory has led to the conviction of many of us, if not all, that space-time is an emergent concept. These two descriptions have very different space-times. Gravity is emergent. You have a description of gravity from a quantum mechanical system with no dynamical space-time, no gravity. We have many examples now of emergent space, where all or some of space emerges, if you want, from this duality. The extreme example is where you have an ordinary quantum mechanical system of dynamical variables, matrix variables, and what emerges in the bulk is all of 10 dimensions of space and gravity. Not time, however. The interesting thing about that duality, which I unfortunately do not have time to describe, is the deep connection between the geometrical properties of dynamical space-time and the entanglement properties of the quantum states, which correspond to the other, the ordinary non-gravitational representation of the same physical situation. Time is harder. We do not really have good examples of how time, which Einstein unified with space, emerges. These examples, they share a common time. This is the focus of current speculative theory about quantum gravity and the frontiers of quantum field theory. And it has clearly something to do, we believe, with the fundamental problem of cosmology. String theory, or any theory of quantum gravity, is a theory of the universe, which is the history of space-time. It has a beginning, it has maybe a boundary and an end. And any understanding or final solution of any theory of quantum gravity would have to explain not just what goes on nowadays around us, but at the beginning and at the end, the whole thing. That's pretty hard. We don't know what the rules are. We've never had to explain the initial conditions. So I'm just going to end with where we are in fundamental physics and what the challenges to the quantum mechanical framework of physics are. And he's been indulgent. So the framework we have today is a mixture, a mishmash, but it's an incredible framework that includes point-like particles, strings, higher dimensional objects, brains, includes all consistent quantum field theories. They're all part of this framework whose extent, and we don't really understand, we're still exploring, and quantum gravity. So what is this framework? Well, originally, quantum field theory led to the standard model. Quantum field theory is really a framework. It includes many different possible theories. The standard model is one of them. String theory was discovered along the way to construct a quantum mechanical theory of particle physics. Now we understand that they're the same. They're dual often. We have so many examples of string theories which are completely dual to quantum field theories. In fact, the ADS-CFT one that Subir talked about a bit, it's the best understood. The quantum mechanical non-gravitational theory is a cousin of the standard model. It's an SUN gauge theory, supersymmetric to be sure, which makes it easier to understand. So these are part of one framework. The standard theory is actually a real theory. You can make predictions. That's what's required of a theory, not a framework. But there are many other possible theories. String theory, from the beginning, was attractive because it appeared there were no parameters, nothing you could modify. All parameters in string theory are dynamical. However, much study, many years, it's clear that there are no parameters in the theory, but there are maybe 10 to the 500, many, many vacua, many ground states. Each one presently defines a theory we can calculate perturbatively to all orders around that vacua. So in particle physics, to my end, the fundamental issues are, one, unification, as hinted by nature, and two, uniqueness. What QCD is an example of a theory with almost no parameters. What picks the particular theory with, what fixes all those parameters from all the ones that are possible in the general framework? In cosmology, the main issues are, how did the universe begin? What are the initial conditions? How is it going to end? That's necessary to understand if you want a solution of quantum gravity. I think these are related. All of the so-called vacua of string theory make no sense if you go back far in the past. Have the same problems that ordinary Einsteinian gravity has. So it could be that the uniqueness of the world we see around us is dictated by the initial conditions. Who knows? Clearly, all of this has to do with the nature of space and time, the beginning and the end of time. And so all of these problems are related, and in fact, people working in this field are switching between these different ways of looking. What about quantum mechanics? Will quantum mechanics be modified? Well, one answer is Of course, every theory we've ever had in physics is modified, is tentative. That's how, except, of course, for thermodynamics. That is a consequence of statistical mechanics, the law of large numbers. That will survive, I think, forever. How will quantum mechanics be modified? Well, people have been trying to modify quantum mechanics forever, from the people who wanted to, and many still do, return to classical determinism and a real world. But no modification of quantum mechanics has emerged for 100 years. A lot of complaints, a lot of philosophy, but no model. So when people say they've tested quantum mechanics, I would argue, by the way, that most of the tests have come from particle physics. These literally thousands of quantum mechanical predictions. But there's no way we could parameterize a violation of quantum mechanics. We don't have an alternate formulation. Many people have tried. That's consistent with everything we know, including relativity and logic. So I do kind of believe that, in some sense, we're not going to modify quantum mechanics in the way we often modify simple models or theories. But certainly, if space, and especially time, is an emergent concept, quantum mechanics is going to look very different at the fundamental level. How do you formulate quantum mechanics with no time? These are difficult questions. They will occupy us for at least another 100 years. We, of course, would like to get information from experiment, from high-energy colliders, from cosmology and astrophysics. But theorists, of course, can proceed. And I always like Einstein's encouraging words. He said, the successful attempt to derive delicate laws of nature along a purely mental path, which he followed unsuccessfully for 35 years, the end of his life. By following a belief, however, in the formal unity of the structure of reality, encourages continuation in this speculative direction. The dangers of which everyone, however, must vividly keep in sight who dares to follow it. So I end with optimism because, in the end, history of science, which isn't that old, once a fundamental question becomes a well-formulated scientific question, like how did the universe begin, is now a well-formulated scientific question, and can be tested experimentally, approachable by experiment, observation, and modeling, mathematical theory, it will be answered in your lifetime for the young people here. Maybe by the 200th anniversary of quantum mechanics. Thank you.
Thank you. Thank you very much, David. Beautiful talk, going all the way to the challenges, the main challenges for quantum mechanics. You ended by talking about the end of time. I'm sorry to say that it's a bit of the end of time for your talk, but there will be certainly many discussion afterwards. And maybe it's time now to gather the round table that was planned now. Sandro? Yeah, thank you very much, David.
Thanks for generous.
Thank you, Mark. And my name is Sandro Scandolo. I'm head of research here at the ICTP, and I'm fully aware that I'm currently standing between you and a well-deserved glorious weekend. but be patient. We're going to have a big announcement now. In fact, as we approach the end of the conference, it's time to make plans for the future. And I guess there is no better way to make plans for the future than to ensure that we continue to support excellence, recognize excellence in these exciting and interesting fields, but at the same time, we also ensure that we transfer this knowledge and excitement to the newer generations. So this is exactly the spirit of a collaboration we would like to announce today between ICTP and IBM. And I'm glad that we have here with us Alessandro Curioni, IBM Vice President for Research Europe and Africa, as well as connected online from New York, Jay Gambetta, IBM Vice President for the IBM Quantum Initiative. So the collaboration will consist of an annual prize, which we decided to name after Richard Feynman. Can I have the next slide, please? So this is a prize recognizing excellence in quantum computing, broadly speaking, of course, which means theory, algorithms, applications, but also simulations. And I think there is no better way to recognize also the legacy of Feynman by naming the prize after him. And I'm actually glad that Peter Zoller, not only a top scientist in the field, but also a member of our scientific council, has kindly agreed to be the chair of the panel that will select the winner of the first prize. The prize will be next year, so we will open a call for nominations soon. If you have any candidates, people you want to nominate, or maybe you're interested yourself, please, just be patient, and we'll open a call for nominations soon. There will be also an annual school or conference organized annually in which, together with IBM, in which the award ceremony will take place. So it will be an opportunity for all of us to meet again next year to celebrate the first edition of this Richard Feynman Prize in Quantum Computing. And I would like now to perhaps what time is it? Because I know that Jay is very tight. Maybe I can just ask Jay to say a few words. Jay, please go ahead. You have the floor.
Sure. First of all, I apologize that I was not able to be there, but I'm very happy that we're co-announcing this prize with ICTP. Obviously, ICTP is one of the cornerstones for theoretical physics, and this prize, the Feynman Prize for Quantum Computing and Simulation, as you described, I think it's going to be important as we encourage the work that has to get done. This is definitely, our partnership with ICTP is gone on for a while. This is the second one. Last year we recognized in the AI, now adding quantum to that is really making sure we recognize the directions of where innovation is happening in the field. Why now? I think everything was covered in, would have been covered in the conference, but like, it's the 100 years of quantum, as I just heard as I was listening to the end of that talk. Much more has got to go forward. We're excited by quantum computing and what quantum simulation can be done. And so I'm really looking forward to seeing exactly how people recognize in this prize, the conferences that get done. And I really hope that by accelerating this work on theoretical physics, coupled with where the systems are going by various different builders of these machines, including IBM and others, we are going to start to see quantum computing hopefully matter and change what is possible in the theoretical physics. And as I said, there's not too much time, and I'm here between you and weekend, so I'll stop there, and I will say once again, I'm very much looking forward to this partnership.
Thank you. Thank you so much, Jay, for all this. Now, I would like to ask the ICTP director, Adishta Bolkar, to say a few words. Please. Yeah.
Thank you, Sandro, and thank you, Jay. So we talked in the morning about international cooperation in the next quantum century. And as I described, ICTP's thinking has been to look for an alliance, an international science alliance and partnerships for the next century. And also we started this idea of an international consortium for scientific computing. So to really, one of our goals is to recognize that along with theory and experiment, which was beautifully described in David's talk, we are also using computing now as a third pillar of science. And if ICTP is committed to open science, we must make computing resources open and available. And this is certainly one of our obligations as I see it. And I'm very glad that major corporations like IBM, they have come forward quite generously last year. So I would like to thank, first of all, Alessandro Curioni, who is here, and Jay Gambetta, and also your CEO, Arvind Krishna, for really coming forward very positively with no strings attached. And they want to support basically two major prizes, one in AI and machine learning, and the other in quantum computing and simulation, as was described, coupled with two major schools, which again will be available to the scientists coming from all over the world. So this is the kind of partnership that ICTP talks about, that we have this huge community of scientists around the globe, and we are very happy that we can increase our reach and our impact through a partnership with a major partner like IBM. And I'm very happy that so we decided we were thinking of suitable names in consultation with our IBM colleagues. And of course, for quantum, Feynman is a perfect, we agreed all that this would be a perfect prize to recognize somebody by. Surprisingly, actually, there are not many. I was surprised that there are not any other Feynman prizes so far. We are the first one, it looks like. The other one we decided in line with ICTP's philosophy, and again in consultation with IBM by Brahmagupta. So it will be called the Brahmagupta Prize in Machine Learning. And the reason is Brahmagupta was a 6th century mathematician from India. I mean, one of the great figures, I would say, in world of mathematics. He formulated not the idea for zero, but not only for the place value system, but really zero as a concept and thinking of numbers as a field and algebra as a separate notion, kind of mathematics. So without Brahmagupta, we would not really have the notion of zero as an element in an algebraic field which you add. And so he gave an entity, zero, an identity. And this was a very major contribution, but also he was actually a very eminent mathematician making contributions to number theory. There is a famous Brahmagupta composition law, which later on was picked up by Lagrange and Euler, and Gauss had a much generalization of that, leading to class field theory and many important developments in basically founding the modern algebraic number theory. And subsequently, I think even more recently, I think one of the Indian mathematicians who got the Fields Medal, Manjul Bhargava, had yet another generalization of it. So we thought that this would be just a perfect way to recognize zeros and ones, which is at the heart of computing. So thank you once again, IBM, and I now give the floor back to Sandro.
Thank you, Atish. By the way, the AI prize will be awarded on the occasion of a ceremony on the 10th of July here at the ICTP. Alessandro, now the floor is yours. From
But I would like really to thank ICTP for joining us on this. To me, you know, creating these prizes to recognize researchers and young researchers is super important, especially in this field. Quantum computing is another, and is going to be another super powerful instrument, but you know, behind this and what we have to do, there are people that, researchers, scientists, that will have to dedicate their life to make all these things real. So that is why this is very important, and I cannot think about a better institution in the world to join us to create this prize for the history, the interdisciplinarities that this institution has always been pushing, but also for the diversity and the creativity from every individual in the world that ICTP has always put together. So I'm very, very happy to this, and looking forward to see, you know, the work that each of you is going to do, and that will be recognized in the future for this prize. And thank you again to everybody.
Thank you, Alessandro. And now, while we proceed to the signing ceremony, actually, so Alessandro and Atish, could you please just sit there, and these are the agreement. Can I kindly ask, so Peter Zoller has actually kindly agreed to say a few words about Feynman's legacy, and actually the reason why we thought it was important to name the prize after Richard Feynman. So maybe you can, while they're signing.
This one, does it work? Pick this away.
Yeah. Need a pointer? No.
No, don't need it. So Sandro asked me to say a few words about Feynman and why this prize was named after Richard Feynman that we have now quantum information. So I guess it's clear to all of you that Feynman was sort of not only a brilliant physicist, think of the work in quantum electrodynamics, but he was also a visionary, who saw earlier than most of the other ones the profound implications of quantum mechanics for the future of computation. And if you look at the publications, that Feynman had, very early on, of course, there was his 1960 paper. It's called "There's Plenty of Room" at the bottom, which was maybe more sort of a visionary nanophysics or nanotechnology paper. And then there was the 82 paper that was called "Simulating Physics with Computers." And this is the one that most of us actually refer to in this context. Even if you read it, I mean, it's kind of a very more visionary than it has actual content, I would say. If you go to the 85 paper, there's much more detailed in there, and it's really starting to outline, even though, things that we know so well, like, qubits, entanglement, and all of these things, gates, quantum gates are sort of, formulated there in a way which is, not there yet. But I would say that the important question that he was asking in these papers was always, can a classical computer efficiently simulate quantum physics? And gave right away the answer, no. And I like very much, if you go to this paper of 82 on simulating physics with computers, where he says at the very end of the paper is the conclusion, nature isn't classical, and if you want to make a simulation of nature, you'd better make it quantum mechanical. And this is sort of, the notion of let's build a quantum computer. And isn't it a wonderful problem? And well, it is a wonderful problem. It's a problem that's sort of keeping us busy since then, I would say, even though maybe the motivation has even increased. And you might not find the word entanglement in any of these papers, but basically what his finger does, it's pointing, at these sort of, resources that are behind in quantum mechanics and what it takes with classical computation to describe quantum mechanics and all of these kind of things. And I think that this was very early on, and I would say really in this sense very visionary. Of course, today what we have is this: we are trying to realize Feynman's vision by sort of building quantum machines. And you also heard here at the conference, several talks that will talk about this context. I was very impressed, of course, by Misha Lukin's talk yesterday on quantum computing, including error correction, all of that. And of course, these things exist with different platforms, across from superconducting. You heard about atomic platforms here, and so on and so on. And it really goes back to Feynman saying, let's build a quantum computer. We are doing that actually here right now. The big challenge, of course, for the future that we still have to do is to scale these things up, and to fight things like, coherence, decoherence, all of these problems and so on. And this will occupy us a very long time. But at the end, I would also say that, what we have to do is this, that these coming generations of efforts have to do, first of all, we would like to really demonstrate that we move beyond classical computations in this context. And of course, the everlasting story of identifying interesting or useful quantum algorithms not only physics, but also maybe beyond physics and corresponding applications. And of course, the big challenge at the moment is error correction, fault around quantum computing that you heard about. But I have to say that I'm immensely impressed about this program. Some time ago, I thought that, well, when people talk about error correction, fault tolerance will come maybe 10 years, 15 years from now. It's actually happening right now, and I find this really, to say, amazing. Feynman is very often reduced to sort of, having invented a quantum simulator. He actually talks about the universal quantum simulator, and of course he always had physics applications in mind, like, maybe quantum materials design, and this is for David here, of course, fundamental physics and high energy physics. But I would say that what he really had in mind is that we should use nature as it is, as quantum physics, to do then also computation, and it really goes beyond the quantum simulator per se. Let me sort of conclude that Richard Feynman was a visionary in physics, and he was a founding father in quantum computing. And so sort of in this general discussion, we felt that this would be a great name also to give a prize and a deep meaning. Feynman is really a physicist, but at the same time also this founding father in quantum computing that also put the effort in the corresponding direction. And with my final statement, I just want to say that in the meantime, quantum information has developed very much also on the theoretical side, and sort of provides, I would say, almost like a unifying language in the meantime for all quantum physicists across different disciplines. And at the same time, it also promises new applications and moving all the way to quantum technologies. And maybe future discoveries, as we heard now, maybe in the context of quantum, might be based on quantum sensing and all of these things. So every time we generate a technology, this thing at the end comes back and becomes then a new tool to discover new physics. And so I would say Feynman is just the right name for these kind of things. Thank you very much.
Thank you so much, Peter. And we're now going to the end of the conference. Closing remarks, I guess. Mark, up to you.
Very, very quick, because we want to go on. I think personally that this has been an extremely thrilling conference, really very, very nice by the breadth of topic which have been addressed, by the depth of the presentation. So in name of all my colleagues who have co-organized with me this conference, I want to thank particularly all the speakers, because I think that it has been a wonderful level. So, and it was a great pleasure to organize that together between Lincei and ICTP. As I said at the beginning, we always thought that ICTP would be the right place to organize such a thing, because it can also expose all these thinkings and the future reflections on the future of quantum mechanics studies to a broad audience. And the word diversity has been pronounced. I know that now it is banned in some places, but let's keep it alive. And so in name of my colleagues, Massimo Inguscio, Roberta Sessoli, Sandro Stringari, Luciano Maiani, who is not here, but who was with us. And of course, last but not least, Rosario Fazio, who's here. Rosario, as always in an organizing committee, there is someone who does the job and who really pushes the thing to the very end. And for this, we are all indebted to Saro. Thank you very much, and to you and to all the ICTP people. Thanks a lot.